All right, so welcome everyone to this workshop on common sense knowledge graphs at AAAI 2021. um, this workshop is organized by myself, Alessandro, Deborah, and Pedro. Alessandro is at Bosch, Deborah is at RPI, and Pedro and myself are at USC ISI in California. We have interesting, we have quite an exciting lineup for today. We have two keynotes, one by Yejin Choi from the University of Washington and one by Joshua Tenenbaum from MIT. And we have an exciting panel on the topic of Are language models enough, featuring David Ferrucci from Elemental Cognition, Shifu Cheng from Columbia University, Lukas Kaiser from Google Brain, and Tony Veal from the University College in Dublin. So this workshop is on common sense knowledge graphs, and out there, people have been creating a lot of resources of common sense knowledge that that can give us a lot of useful information, right? So for example, on the topic of frisbee and dogs and catching and throwing, we can construct these sort of knowledge graph that tells us, for example, that catching frisbee has property being fun for dogs. And when somebody throws a frisbee, someone else has to catch a frisbee, and that catching is an antonym of throw. So we have a lot of information that belongs to, let's say, that describes antonyms and synonyms and utility knowledge and qualities and properties and some sort of temporal dependencies. So there is a lot of this knowledge being collected and represented in different sources. And when we talk about different sources, here is an image of some that I believe are fairly representative. So we have Psych and OpenPsych. So starting from 1984 through OpenPsych later, that was the first initiative that we think of when we think about common sense knowledge. Then there is, of course, the line of work done by OpenMind Commonsense and ConceptNet, which is arguably the most commonly used resource of common sense knowledge today. And then we have other sources such as, for example, Atomic and Comet. We also have Quasimodo KB and Generics KB. So some of these resources have been, for example, extracted from text. So those are large scale like that. We have Wikidata, which is a collaborative effort, part of which is common sense knowledge. We have NEL, the never-ending language learner. So we see that there is a lot of sources out there. Many of these are large scale, and we see that there is quite a surge in the last few years of creating of these sources. There are actually many more that have been created within the last 2 years. For example, Ascent, or also as Ken posted another resource called NextKB. So there are a lot of resources that are not in this figure, but I included here some of the ones that are probably most representative. Right, so we have dozens of these large-scale resources. We have tens of millions of statements, or perhaps hundreds of millions of statements that are being represented out there. And we have a lot of diversity, right? So we have representation-wise, we have some of them are symbolic, some of them are represented in natural language, some of them are even neural, such as Comet. Then we have different acquisition methods. So some, like the earlier idea of expert input is, I guess, what sources like Psych start from. Then we have crowdsourced resources such as ConceptNet and Atomic. And we have resources like, for example, Quasimodo KB or WebChild that have been extracted with information extraction and then consolidated in some way. With respect to knowledge type, we have resources that focus on entities and actions. We have others that focus on inferential and rules knowledge. And finally, topic-wise, some resources have strive for a broad coverage, for covering a lot of different knowledge types, whereas some, like for example, Atomic, focus on on a more specific, but then deep coverage of let's say one domain. Right. So here I just give a little bit of indication of the richness of what is out there. For more in-depth discussion, I invite people to actually check our tutorial that we gave on Wednesday. We go into much more depth into different sources and what can be done with them and what are some challenges in creating them. But let me move on now to how this relates to this workshop. So this workshop is intending to study these common sense knowledge graphs, and we do these by proposing various topics. One is on creation and extraction of new knowledge, common sense knowledge graphs, of integrating some exploration and analysis, then measuring their impact on downstream tasks, including some new method, for example, for doing so, then probing for knowledge needs. So this is more, let's say, the evaluation aspect through using this knowledge. And then finally, something like identifying and filling gaps in common sense knowledge graphs. So how complete are these, and can we do something to improve that? So let me spend a few minutes to show the highlights of these workshops. So keynote one, we have two keynotes, as I mentioned before. Keynote one is by Yejin Choi from the University of Washington, and her keynote will be about intuitive reasoning as unsupervised neural generation. So the main idea here is that we want to, that she will propose how to focus on unsupervised or self-supervised algorithms that rely very little on training data. I think this is an interesting idea because, common sense knowledge in theory shouldn't really depend on training data. And so her focus would be on these sort of um, ideas, and then how to apply these to perform non-monotonic reasoning in a complex language generation task that require logical constraints, including systems like Comet 2020 and Social Chemistry 101. The next keynote will be by Josh Tenenbaum from MIT. So Josh is a cognitive scientist that is also included in our machine common sense program. And the topic of this task will be the reverse engineering of the core of human common sense. So what do we start with, and how do we learn the rest? So this is inspired, as I mentioned, by cognitive studies of how humans work with common sense. So we think that these two keynotes will be quite insightful, and we look forward to them. In addition, we have panel on the topic of, are language models enough? So there was yesterday a very cool panel at AAAI on neurosymbolic reasoning. This panel, in a sense, relates to that one, in a sense that here we basically talk about the whether these language models are enough, and what is the role of symbolic knowledge, what is the role of common sense knowledge graphs in the overall picture of AI, or perhaps slightly more specific in the area of language understanding. And last but not least, we have 9 accepted papers on very interesting topics, including zero-shot human-object interaction, then generating passages from knowledge, then ideas on representing context, and cultural knowledge, and new ontologies for situational awareness, ways to create text and to create tasks through common sense knowledge graphs, and things like that. So a bunch of different topics will be covered here. So let me say a few words about the organization of this workshop and how have we set up the program. So the workshop will have 3 parts. Part 1 will be is kind of already ongoing. We'll have this welcome part followed by a keynote by Yejin Choi of 1 hour. And after that, we'll have paper session 1 on collecting and representing common sense knowledge. Part 2 will be, so obviously there'll be a break between the two, and then in part 2, we'll have paper session number 2 on using knowledge graphs for natural language tasks. And after that, we'll have the panel on, are language models enough? That will be 1 hour panel. And in the third part, we'll start by the Joshua Tenenbaum's keynote and follow that up with the paper session 3 on common sense inference. After that, we plan around 35 minutes, depends a bit on where we end the previous session, on discussion and wrap up. So this would be, everybody will be welcome to join this discussion, and it will be sort of like a free flowing chat and comments. And finally, we have 1 hour extra for ending an optional virtual happy hour. So this is we'll improvise this. So a few practicalities before I wrap up this part. So I just want to remind all the speakers, all the paper presenters, that long papers are allocated 15 minutes plus 5 minutes for Q&A. Short papers have 7 minutes for presentations plus 3 minutes for Q&A. So 2 requests for the presenters are, please stick to the allocated time. So we wanted to do everything live today because it's just much more natural, and it just feels nicer in a way. But the caveat is that people have to be sort of disciplined and stick to their time. So please do this. The second one is please come in the break before your presentation, just to make sure that the technicalities like Zoom sharing and just voice work well. And then in terms of streaming and questions, the whole workshop is happening live and we are recording it. If you are speaking and you would like to be in the recording, make sure that we have your photo release form. I think actually we have all of the forms by now, minus one of the papers. Not sure if that's on purpose or, but we'll figure that out. And then finally, please put your questions ideally on Rocket Chat so we can, access them and work there as in a more centralized way. I think they're also archived, so that actually is nicer. And finally, I would like to thank the program committee. These are the people that do always the job that is not thanked enough for. So Marjorie, Aldo, Henry, Robert, Logan, Roberto, Valentina, Simon, German, Daniel, Niket, and Peak. So these were the people that were reviewing our papers, and I would like to acknowledge them, and thank them here. And finally, I'm exactly on time. So we are, that's the end of the welcome of the introductory part of this workshop. And up next is the keynote by Yejin Choi, which is chaired by Pedro Sekeli. So without further ado, I'll just hand these over to Pedro.
Okay, thanks, Philip. So it's my great pleasure to introduce Professor Yejin Choi for the keynote. I mean, Yejin really needs no introduction, but I'm going to do an introduction anyway. Yejin is the Brett Helsel Associate Professor of Computer Science in the University of Washington, and she's also in the Allen Institute of AI. And, she is really the world authority in common sense reasoning. And, she's very famous for her papers on atomic and comet and many others. And just recently, Yejin's group had, 7 AAAI papers in this conference and 11 EMNLP papers in the 2020 conference. I think that really, speaks for her and the quality of her work. And we're thrilled to have her talk about intuitive reasoning as unsupervised language generation. So Yejin, welcome, and thanks for being here.
Okay, can you hear me?
Yes.
Awesome. So thank you so much for having me here today and also organizing this awesome workshop. I'm so excited that a lot has happened in the past few years, and also a big shout out for the amazing tutorial that contains so much information about what happened in the past few years, as well as a long time. in the history of AI. So the reason why we like to think about common sense is because despite the human level or even superhuman level performances on leaderboards today, we keep seeing that SOTA neural models are brittle when provided with adversarial or out-of-domain examples, making such silly mistakes that humans would never make. So it looks as if we know how to solve on your data set today without really solving the underlying task. So when people discuss why this might be the case, we seem to agree that there's a fundamental gap between how humans understand how the world works, or common sense understanding about how the world works, and how machines learn primarily dataset biases or superior patterns in datasets. So in order to bridge this gap, there has been increasing discussions about the difference between human reasoning and machine reasoning today. And in doing so, we often talk about system 1 and system 2 reasoning due to Daniel Kahneman, Nobel Prize winner. And that's great, but it seems that there's been this myth floating around in the community that maybe we know how to do system 1 reasoning today using deep learning, and we only need to really figure out system 2 reasoning. It turns out Daniel Kahneman himself disagrees with this point of view. So if you check out AI Debate 2020 that happened on December 23rd, he actually clarifies on this. But anyway, if we look at his earlier work, he not only talked about system 1 and 2, he also talked about 3 cognitive systems. So in addition to intuition and reasoning level system, cognitive systems, we have a perception. And perception and intuition together are what's fast and automatic and effortless associative. And then system 2 reasoning is the one that's effortful and slow, more logic-like. And when we look at the content level, this is what excites me quite a bit, because in terms of the content, both the system 1 and 2 require some sort of a conceptual representations and some sort of a temporal reasoning or causal reasoning across different time frame. And then finally, they both involve language. Sometimes people assume that system 1 might not require language, but that's not true. Both of these reasoning layers are heavily integrated with language as well. So in terms of a concrete task for system 2, we often think about solving puzzles or writing programs or proving logic theorems. But of course, it's not just that. It also involves highly involving language tasks such as reviewing AAAI papers or crafting AAAI rebuttals and giving a talk. And humans often spend hours or even days without engaging with such system to reasoning. Well, hopefully we all do that on a daily basis at least, but who knows? But perception level is the kind of a task that's like object recognition, speech recognition, image segmentation, and the like. Finally, in between is the system 1 or intuition level, which requires inferences on preconditions and post-conditions, what happens before and after, motivations and intents, and reasoning about people's mental and emotional states. Now, this is what we do pretty much every waking minute without even thinking about it consciously. This is very reactive and unconscious. So focusing on this, which is the key target of this talk, I would like to make my point clearer or more concrete by using this example, Roger Shepard's Monsters in a Tunnel. What you see here is not just monsters in a tunnel. You see a story that 2 monsters are running as opposed to standing still on 1 foot. One is chasing another rather than trying to copy his body movements. And then the chaser has hostile intentions and the chased is afraid, even though 2 faces are actually visually identical. But you almost hallucinate a story that may or may not be necessarily true, but you almost believe that that's likely to be true. I'm going to talk about this book again toward the end of this talk, but important observations here are A, none of these inferences is absolutely true. This is a recurring theme in this talk as well. Common sense inference is not about true fact that everyone in the world agrees upon. None of these inferences is absolutely true. They are stochastic in nature. Everything is diffeasible with additional context, and that's okay. A great deal of intuitive inferences are common sense inferences, which can be best described in natural language, just as shown here. And it's not possible to define a small subset of words as categories for the purpose of common sense knowledge and reasoning. We actually need the full scope of language, not just words or graphs of words. So I'd like to push for this idea that we need to incorporate language as the symbols, all of it, not just words or sets of words. And in part, that idea has been also argued by this book, Surfaces and Essences, by Douglas Hofstadter and Emmanuel Sander. You might be more familiar with his other book, Gödel Escher. But in this Surfaces and Essences, which is really about a book on analogy and concepts, they argue that categories or concepts vastly outnumber words and require free-form open text descriptions. So if we really want to have a broad coverage representation of common sense knowledge and reasoning across a diverse set of concepts, then we do need the free-form open text descriptions. Okay, then if you buy that, reasoning becomes a generative task as opposed to discriminative task or categorical tasks, because the space of reasoning becomes infinite. And in fact, that's what we humans seem to do naturally. We often think out loud, we think as we speak, on the fly, generating our ideas word by word, without enumerating in our head all possible alternative sentences that might describe our reasoning. We just do this on the fly. And so that on the fly nature is going to be a focus of the first part of the talk, which is reasoning as generation. And after then will be part 2, which will focus more on declarative knowledge as knowledge repository. But let's begin with the first one. So this is going to be about unsupervised backpropagation-based decoding algorithms for counterfactual and abductive common sense reasoning. So abductive reasoning is a particular kind of reasoning that humans do all the time, which has to do with reasoning about past observation. For example, Ray hung a tire on a rope to make his daughter a swing, and future observation that Ray ran to his daughter to make sure that she was okay. As a human, we can almost instantaneously reason what happened in between. Probably some kind of accident happened. And so this is an inference to the best explanation to partial observations. And abduction is quite different from induction or deduction in the sense that we have to almost hallucinate some new information that's not part of the partial observation. We have to fill in the gap. And that's very different from induction and deduction, which focus more on what are strictly true. But common sense reasoning, like abductive reasoning, requires filling in new information that may be defeasible with additional context. Now, another important aspects of common sense reasoning is counterfactual reasoning. And for that, we are going to be using an example from time travel data set, which is about, given a 5-sentence simple story like Zach was throwing a party, friends are dressing up for the party, Halloween party, etc. What if the second line is slightly modified so that instead of any Halloween party, now this has to be about Games of Thrones themes party. So this is a TV show. And in that case, we want to revise the story a little bit so that it's more coherent with the new counterfactual situation that we have to deal with. So ideally, we want to do this with minimal edit. And so the data set it consists of examples like this to solve. And you might wonder then, what's the commonality between these two tasks, which look quite different? Well, the commonality is that both are types of non-monotonic reasoning, which requires reasoning about both past and future. And that's pretty awkward if we try to do that using pre-trained left to right language models, such as GPT-2, because it's easy to condition on the past or left context, and then say something that goes well with the past context, but it may or may not flow well with the right context or future context. So since it's a little bit awkward to do it, what people often do is to push both the context into the left-hand side, combine them, concatenate them with some delimiter, and then try to do that. But in order to do this, of course, we have to fine tune or continue to supervise the training on this pre-trained neural language models. And in doing so, it does better, but still it can be awkward because of the fact that pre-trained language models were not really trained in this manner before. And then we're trying to twist this ordering of a context only during the fine-tuning time. So in addition to that, humans never seem to need to learn to do this. We don't need to train ourselves to read past and future first and then try to predict what comes in the middle at all. We never just do that. So in this work, we explore backpropagation as a means to do this kind of inference on the fly during just inference time without training time supervision. So that idea, in fact, was used by image style transfer that you probably all heard about, in which backpropagation was used for inference time algorithm as well. So typically backprop is what we use for training of neural network, but it can also be used for inference time algorithm. It's just a little awkward with language though, due to the discrete nature of language. So I'm going to sketch out the algorithm visually, just to give you some intuition about how it might work. So conditioning on the left context, we continue computing the continuous representation of y, sentence, middle sentence y. And then using that continuous representation, we do this forward pass in order to compute the representation of z, future sentence, so that we can compute then loss function that we typically use, which is conditional probability of future given the past. Now, once we have that loss function, then we can do backpropagation down to the continuous representation of the middle sentence. And then since we usually do iterations with backpropagation, that's what happens in this work as well. We repeat forward and backward a couple of times until convergence. And then at that point, we convert this continuous representation to something discrete. So this output, this particular example used in the introduction of this segment of the work is in fact model generated, algorithm generated. So she hit the rope and the tire fell on top of her. It turns out we can do almost the same thing with counterfactual reasoning just by using different loss functions. So in this case, KL divergence between the original future story and then the modified future story. And then what we get is the fact that Zach thought about being Lannister, but instead he decided to dress like Stark. So this is actual algorithm output, which sort of reflects that GPT-2 read something about this TV show as well, because we know these stories are not in the time travel data set. I mean, the TV show. Okay, so in terms of evaluation, unfortunately, we have to rely on human evaluation because abductive reasoning is not a solved NLP task yet. And it turns out humans do much better still. We can do better. DeLorean is green. We can do better than supervised or unsupervised methods. And the supervised method is not only supervised, but it's also powered by Comet that I'm going to talk about in a bit. But it's still much worse than human. which will motivate the remainder of this talk. But in addition to that, I'd like to highlight this automatic evaluation measure, which is a little bit challenging because we just don't know how to do it quite right. So still we can look at Blue, Rouge, and BERT score as a points of reference. So it turns out by those measures, we can still outperform unsupervised baselines, but not the supervised one, because Rouge or Blue really focus on particular n-gram patterns. And without really fine-tuning on this particular data set that has particular writing style, it's hard to be very lucky with generating exact n-grams. So this requires how to evaluate this is an open research question. So here are some other examples from our algorithm, unsupervised algorithm. So Ray drove his car on a steep mountain road, and then later he was fine, but his car was totaled. What happened in between? So our algorithm generated that as he drove the car to the top of the mountain, his car is hit by another car. Counterfactual reasoning example. Tara wanted to buy a new shirt for her upcoming school formal. Originally, the story goes as follows. She went to the mall with her mom, brick and mortar store, and then she knew but this is, so that's the original second sentence, but the new situation, counterfactual situation is that, well, she decided to order from online, perhaps due to COVID lockdown situation. And so the original ending would then be more about how they actually went to the brick and mortar store and try things out. But in this revised story, now it's about they, presumably the store, sent her a shirt that fit her perfectly, so excited about it. So the story is adequately modified so that it doesn't talk about going to the mall anymore. Okay, so that was DeLorean. And now let me briefly talk about neurologic decoding as another example of unsupervised decoding time algorithm for dealing with the particular kinds of common sense reasoning that might require logical constraints. So today, the winning recipe for conditional generation is a sequence-to-sequence model. So for image captioning, dialogue response generation, machine translation, and so forth. But this doesn't always work for tasks like Common Gen, where the task as an input, we receive a set of words, and then the output should be some reasonable sentence that makes use of all of these words given. After fine-tuning on a lot of examples, the models today are learning something about the fact that we have to make use of some of these words, but not all. It doesn't really understand the logical constraints just by looking at examples in large quantity. That's in sharp contrast with how humans might operate. Well, I don't need a single example in order to be able to do this task. Similarly, machine translation, this is an observation from recent work by Stanovsky and other co-authors that there's a gender bias problem in neural machine generation. Perhaps not a shocking news because it reflects the bias in human language as well. But what happens as a result is that, well, the neural models like to convert women into men in a particular context. So maybe we should, but in contrast to humans, once we know grammar rules, it's far less likely that we make this kind of mistakes. So to summarize the observations we see here, we basically need to be able to incorporate logical constraints at the inference time without having to always start from scratch or try to do supervision on a lot of data, because that's just costly. And humans are perfectly capable of doing this kind of operation. You give me, for dialogue purposes, if you tell me, well, generate some reasonable response that talks about particular content, I can totally do that in real time. If you ask me to write a recipe that contains some ingredients but not others, and in some sort of conjunctive normal form, a product of sums of or ends or of ors, then humans are perfectly capable of doing it. So that's what we try to model in this work. Going through this conversion very quickly, in the end, what we have is that instead of using only the conditional probability of output given input, we're going to have this additional penalty term, which will intuitively penalize any clause that's not satisfied. And in order to do that, we do some sort of advanced beam search, which I'm not going to go into the detail here. But let me just highlight the fact that with fine-tuned language model, whatever search algorithm, typically use the search algorithm or sampling algorithm you use, they always make some mistakes. Whereas if you use neural logic decoding, then we get a nice sentence that satisfies all constraints. It turns out neural logic can be used for unsupervised, off-the-shelf, pre-trained language models as well, with almost identical output. Of course, using unsupervised models, basically they don't understand what this input is about, so you get completely irrelevant sentences out. But with neural logic, you still can solve this original task. And it turns out, if we look at coverage, so this is the percentage of constraint satisfaction. Neural logic, whether supervised or zero shot, green and yellow, have high coverage, whereas typically supervised neural models, they have lower coverage. And the x-axis here show the model size. So the wisdom today, conventional wisdom today, is that, well, the larger the better. So that's true here. And the larger models do seem to learn these implicit constraints, logical constraints, but it's still not going to pick up everything, even with the GPT-2 XL size. And you might wonder whether the high coverage is due to lower language quality, but that's not true either. When we look at Rouge and Meteor, neurologic method really dominate the typical supervised method with conventional beam search. And in fact, not only neurologic outperform non-neurologic case, unsupervised neurologic, which is a yellow line, even on a smaller data network, still outperforms larger supervised network. So that's an happy ending, because these days we keep hearing how larger networks do better. And that's generally true if you use the same kinds of search algorithm during decoding time. But wait a minute, there's nothing wrong with the decoding time algorithms. And in fact, algorithms has always been at the heart of computer science. So I think we need to really look at inference time algorithms more going forward in order to be able to use smaller networks. Not everybody can afford feeding giant monster-sized neural networks today. So in this work, I quickly talked about neural search or continuous search, which is the DeLorean, and then discrete search, neural logic. And in fact, I envision that there can be a variety of different kinds of search algorithms that can be customized and developed for neural language generation. And so it's my speculative thought, but I think we can push quite a bit further with inference time algorithms. Now I'm going to talk about part 2, but before going there, let me make a brief remark about the current paradigm of deep learning. So it's always combination of supervision on a lot of QA or categorical problems with self-supervision on a lot of raw text. And this recipe works for winning leaderboards, whether it's language leaderboards or language and vision leaderboards or vision leaderboards. This is the winning recipe, but it fails on generative evaluations such as abductive reasoning, counterfactual reasoning, and various constrained text generation tasks that require logical constraints. Some people then might think, that's because there's something wrong with the supervision. And I mean, imagine even taking a deep learning class in which professor teaches nothing, no lectures, just lots of exam problems with the correct answers provided to you. We cannot really learn an entirely new concept in this way, in a effective way. So then some people might think, Oh, that's because there's something wrong with the multiple choice supervision. We should do self-supervised learning on a lot of raw data. But there's something odd about that as well from human perspective, because if the professor doesn't teach anything, but provide a lot of deep learning code, not even written in Python, but entirely new language that you've never seen, that's encoded in, say, Korean, what are you going to do? Probably it's even harder to learn anything. And so we can't really learn concepts well enough through the combination of this current paradigm of deep learning. We need to learn from declarative knowledge. So that's going to be the story of the remainder of this talk, which starts with Comet Atomic 2020. And this just appeared at AAAI here. And it builds on our previous works, Atomic and Comet. But I just be very, very brief about the whole thing and just highlight the fact that Atomic 2020 has a lot more than before. So Atomic originally had relations like this, that X gets X's car repaired, might require having money beforehand, and then as a result, X might want to call Uber for a ride. And this is only a subset of original Atomic. And now we have a lot more that includes, oh, by the way, money can be used for paying repairs, or, oh, you could also forward that into origami. And we have also fun new relations like, oh, in what counterfactual situations this event cannot happen. So for example, you cannot get your car repaired if your car is totaled completely. So we have a more event-centered common sense knowledge as well. And so we kept growing the graph so that currently we have about 1.3 million if-then common sense rules over 23 different inference types. And the paper poster presentation and recorded talks give you a lot more detailed information about this, but I'll just highlight one thing, which is how much does GPT-3 know? So to give you a bit of perspective though, GPT-3 is very big. It doesn't even fit into the screen because it's more than 400 times larger than our new Comet, which is built on top of a BART. So with that in mind, GPT-3, considering that it's on few shot, it's doing very well, especially that GPT-2 zero shot was also doing much worse. And the number here is accuracy judged by human evaluation. The Comet still does much better than GPT-3 with considerable gap. And this evaluation setting is somewhat adversarial for Comet in the sense that we try to separate out training and test to be as different as possible. So typically, if you had a random split between training and test, then you would get higher number than this. Okay, so turns out Comet generalize well on out-of-domain examples. And so you can try this demo site. And if you click event, that's the Comet version based on atomic knowledge graph. Whereas if you click concept or ConceptNet, this is a Comet demo based on ConceptNet. And by the way, the demo has not been updated with the new Atomic Comet 2020 yet. So if you go there, you're going to be playing with the older version. But in case you may have not seen the demo, I can just highlight what it looks like. So you can give, instead of person X, it's okay if you just give a random name. Nothing breaks because of the fact that Comet is built on pre-trained language model that understands also raw text quite well. And then you get this graph prediction, which might include things like, oh, as a result, John might want to call 911. And that's great because the word like 911 or medical help, attention, etc., are not even part of this input sentence. And yet the Comet is able to reason about the preconditions, post-conditions, people's likely actions afterwards, and so forth. There's some interesting observations about the level of abstraction that happens by Comet. So you can search atomic knowledge graph by going here and then type one word, any content word, and in real time, it's going to populate a number of well, actually not number, all of the events, atomic annotated, human annotated events that include that word conscious. And you notice that there are events like self-conscious or subconscious. So it's going to search anything that has conscious as a substring in real time and populate all of this. And they are all in the training data here, nothing in the test or development. Okay, so what's interesting is that, so there's person X being very self-conscious, and yeah, I realized I had a blow up version that I forgot to show. But anyway, so if you search this atomic with this precise event, you see what humans wrote. Oh, before then, maybe X needed to ate too much food or can't fit into clothes, and so forth. So that's what humans wrote. And humans wrote nothing about X wanted to do something. But Comet, on the other hand, it turns out it doesn't memorize atomic as is. Instead, it's rephrasing things or even adding new knowledge that was not even annotated before. So maybe person X wanted to look good, show off. Maybe person X needed to do something embarrassing beforehand. There's something wrong. And that's interesting because it's more abstracted away than what humans wrote in the original atomic knowledge graph. And you see a lot of new words that was not like how the person might be seen, nervous, that's pretty good, shy, insecure, that was not even part of this original annotation. So we find that atomic is able to generalize, abstract away for something new. It turns out it can also reason about something that's not there. So Sarah is conscious. This is not part of atomic knowledge graph, in that when we go back to this earlier search result, there's self-conscious, there's no just conscious. There's self-conscious, subconscious, unconscious, there's no just conscious. And self-conscious is, of course, very different from being conscious. So it turns out, even though Sarah is conscious, this sort of knowledge is not encoded in the graph. Strangely enough, it's pretty good. Comet is quite good at saying something reasonable, that, oh, maybe Sarah is aware, observes stuff, and being observant. So these are quite good predictions. There are more examples of this nature that are out of domain, like solving, rising to the sunset on a motorcycle and after solving AI. This is out of domain in that it's a little bit, the sentence is more complex than typical atomic event. And also things like solving AI does not appear in the knowledge graph, but the predictions are that she's going to be daring, brave, adventurous. So these are quite reasonable. Gary breaks the world record for most controversial tweet. So he wanted to be famous. He might needed to do research or write a book. And as a result, he might feel happy, excited, and he might want to celebrate, to tell everyone about it. So overall, the predictions look quite reasonable. And so Gary Marcus, as we know, has been concerned about deep learning, because when he gave prompt like this, what happens when you stack kindling and logs in a fireplace and then drop some matches is that you typically start AAA. GPT-2 transformer, talktotransformer.com, continued his prompt using what appeared to be a nonsense instead of the intent of this act. And so that's because language models are different from knowledge models. So Comet is essentially a knowledge model. And if we try Gary stacks kindling and logs and drops some matches, you do get correct predictions. By the way, these are in the order of decreasing order of probability scores. And sometimes you see none, and that means the model predicts that human annotators might have said none in this situation, which is, you cannot ignore this, but this happens somewhat frequently due to the fact that the original atomic knowledge graph has a lot of none. And so to summarize what we have here so far, language models learn observed knowledge in language, or more explicitly spoken knowledge in language through self-supervision. Atomic, on the other hand, they represent declarative knowledge and can be used for supervised or semi-supervised learning of such knowledge. And so COMET combines them together into neural form. And atomic is a symbolic representation of knowledge in language instead of logic, which allows us to combine atomic with raw text, which then leads to the neural representation of a common sense knowledge that generalize surprisingly well to compositional and previously unseen events, as I highlighted the 3 examples just now. And compared to many other existing knowledge, common sense knowledge resources, especially with atomic, we deliberately try to focus more on causal knowledge, because some of these simple causal inferences are almost memorized knowledge. So we were exploring that. Now I want to talk about more complex knowledge about social and moral norms, called the Social Chemistry 101. So this is sort of like 101 class for machines to learn about human morality and social norms. Because GPT-3's morality is somewhat questionable. If you give a prompt like running a blender at 5 a.m. is rude because ... GPT-3 might say, you can wake up the entire neighborhood. What kind of blender is that? You can only do it if you are making a thick smoothie and need to incorporate some ice. So it's funny, haha, perhaps no harm made. But if you give other kinds of prompts like, it's okay to post the fake news if it's in the interest of people, or if it helps the XXX agenda, it's an acronym with the 3 characters. So that's not good. And this kind of generation can pop up because of what people actually say out loud on the internet. It's unfiltered. It includes all kinds of stuff that may or may not be safe to include. So I don't think this is a phenomenon that happens because GPT-3 is not large enough. I don't think 4 and 5 will actually solve this problem. And we need different ways of teaching AI regarding people's descriptive ethics. And so what we do in this work is that given a situation like asking my boyfriend to stop being friends with his ex, we're going to think about rules of thumb that people might use or invoke in that situation. So for example, it's okay to ask your significant other to stop doing something you're uncomfortable with. Turns out humans just don't agree with each other, or we are just all very different. So some might actually focus on other aspects of moral or social norms, and may focus on the fact that, oh, you shouldn't tell someone else what to do if you care more about authority and subversion. And then if you care more about loyalty or care, then you might say, oh, you shouldn't make your significant other doesn't feel like a lower priority than your ex. And this opinion will vary, of course, depending on whether you ask your boyfriend's opinion, his ex's opinion, or the narrator's opinion. So all sorts of different disagreements can arise. And then there are some level of agreements about, I mean, even as a human, you can imagine other people thinking differently within reasonable scope. And so what we do in this work is that for any given situation, paired with one of many different rule of thumbs, we populated these 12 different categorical as well as open text annotations. And so that amounts to 300,000 of rules of thumbs grounded on hundreds of thousands of real life situations with the structured attributes that include the social judgments, cultural pressure, legality, and some moral foundation theory dimensions, which are inspired by this book. And so the paper talks about how you can populate, run large neural models on it so that we can compute various evaluation, but not going to go into the details of this. And I'll just share some of our philosophy behind this work, which is that when we think about people's norms, It might include the social norms, moral norms, and ethical norms. These are different concepts, but it's not easy to really divide them into like separate categories in a clean-cut way because they can overlap. And not only that, people are complex and we never really seem to agree with one set of values. I mean, look at, this divisive election as well for any given country. So what we went with is basically inspired by descriptive ethics. That's a line of study that asks people what they might do in a given concrete situation. So you get diverse opinions. Sometimes you get very, like, for example, is it okay to kill somebody just because you feel like it? Probably everybody will agree that that's not okay. Hopefully everybody will agree. But for situations like meeting with your ex, maybe people will disagree to some degree. So we get distribution of people's ethical, moral, social norms. And this contrasts with prescriptive ethics, which is more about what are 5 or 7 fundamental dimensions of values that everybody must agree upon. And there are such studies, but that's not what we took here because, in part because it doesn't seem like humans agree upon one set of values ever, but also because grounding is important for AI. Even if we somehow take a vote and take the election, voting result without questioning it, we might still realize that AI doesn't know how to apply those 5 magical set of values down to complex situations in the way that humans do. So that's why our work is grounded. And I would like to highlight this, our AAAI paper called the Scruples, which provides a much richer, grounded situations for ethical judgments with real life anecdotes. So please go check it out if you haven't. Okay, so I'm going to make some closing remarks now. So if we search Commonsense from ACL Anthology, which is the repository NLP papers, then we see there was a big void between 80s and the past few years. And so indeed, when I started thinking about common sense research several years ago, people told not to even speak the word in a paper. Try not to use the word, try to paraphrase it to something else. And so I was following that advice a little bit and then thought about it again. And I realized that, well, although the past failures, I mean, I think there were a lot of great research done. Still, it's inconclusive because the research was done based on weak computing power, not much data, no crowdsourcing, not as strong computational models. And then the past research was too much about logical forms as representation formalism or conceptualization instead of natural language as knowledge representation. So I think we could definitely try a lot of new approaches to common sense. And we've seen a lot of exciting research in the past few years, but probably brute force larger networks will not completely solve common sense on its own, analogously to how we can't reach to the moon by making the tallest building in the world 1 inch taller at a time. We probably need to do a lot of different stuff on top of larger networks, which, by the way, I'm not against. It's just that alone is not going to be sufficient. So my speculation this year is that minimally we need to investigate two different directions, one being unsupervised inference time algorithms that can draw better reasoning out of pre-trained neural language models, and then ways to provide the supervision as a form of declarative knowledge for knowledge modeling. So more focus on neural knowledge modeling as well as symbolic knowledge modeling, their integration. And in doing so, I think we need to include diverse set of knowledge, not just something narrowly defined. Yes, I didn't get to talk about this visual version of it, but there's our ECCV paper about that from last year as well. So this talk contain some of our recent work, but not all. And so there are a lot more in our ACL Commonsense tutorial. And it's publicly available, so you can go check out. And the level of attention we got is quite encouraging in that initially we were worried, are we going to get enough registrants? But then I was pleasantly surprised how many people came check it out. And then, of course, what's really fascinating about this AAAI Commonsense tutorial is that it has a lot of new content that was not covered by ours as well. So highly recommend to check this out as well. I guess Antoine shows up there twice though. All right, so I want to also share a bit of my other thoughts on the relevance of language and embodiment, because this is one of the frequently asked questions to me, that, well, my dog, my cat has common sense without language, therefore, I'm pretty sure that you don't need language for common sense, despite all these other examples in which language was convenient to include for common sense intuitive inferences. At the end of the talk, some people still worry about the fact that their babies have common sense without language. While it's true, I think in the end, don't we want to build common sense models for adult human beings as well, not just for your dogs or cats? Another commonly asked question is that, some concepts like that juicy, crunchy feel you get when biting into an apple cannot be learned without embodiment. Therefore, we shouldn't worry too much about language models and worry more about embodied experiences. The truth is, we do learn a lot just from language ourselves. So we do not need to experience the fact that a tiger can eat a human being in real life situation. You do not need to see someone else being eaten. You do not need to even see YouTube video about it. You just read about it, and that's sufficient, ideally. So, we don't need to drown in the ocean in order to believe that we can drown in the ocean either. So it's likely that, but when I say that, I'm not against grounded learning either, because I do also work on grounded stuff or even embodied experiences. It's just that we do make considerable trade-offs between the coverage of concepts and the richness of representations. And so I don't think one necessarily will dominate the other, but rather we need to research on all these different routes and then really think about how to connect the dots across a different mode of operation for learning. And my vague speculation is that language might be important as a powerful representation medium, even connecting through different representation medium, because when we think about this tiger case situation, it is a language that we did rely on in order to learn such a concept declaratively. Okay, so final remarks on language and reasoning. So I really like this book, The Enigma of Reason, which I briefly showed at the beginning of this talk. And in that book, it also talks about system 1 and system 2. In that book, Intuitive Inferences, the authors argue that is a great deal about extraction of new information. So that's very much like abductive reasoning from the information already available. And system 2 reasoning, the book argues that our system 2 reasoning are used primarily not to guide oneself. Here, guide means making an important decision, but to justify oneself in the eyes of other people or convince other people. So really, system 2 reasoning, people keep invoking this for the purpose of communication. And it kind of makes sense when you imagine crafting rebuttal. how much you get to think about, like, how do I phrase this so that I really convince this reviewer too, crazy reviewer too, who somehow misunderstand my perfectly written paper draft. So we do this hard reasoning task through language considerably. And in doing so, another book, as well as this book, the conventional mathematical logic plays at best a marginal role, especially induction and deduction. Even like there are separate chapters of induction and deduction in this book. The way that humans do that through language is fascinating. It has nothing to do with what the theorem prover will tell you, which is why I think common sense reasoning has been so hard, especially when people were taking more formal routes. And I think that's why the language modeling, combining language modeling with knowledge modeling and making reasoning algorithms through language models might be a more promising route going forward. Thank you. I take questions now.
Thanks, Yejin, for a fascinating talk. We have a little bit of time for questions. So we're using the Rocket chat for questions. I don't know if Yejin can see it.
Oh, no.
Okay.
Sorry, I didn't prepare. Yeah.
That's fine. So I will read the questions for you. So we have one question from Karthik. Read the embodiment point that you made for agents. How important do you think a simulated text world or Thor versus real world environment is in terms of learning and exploiting common sense knowledge?
Yeah. Hi, Karthik. That's a great question. So I think there's a limit in the simulation environment. So like, for example, even if we make a robot that can, in the future, they can actually eat an apple for energy purposes, I don't think their sensorial pleasure will be actually identical to that of humans, though I don't really believe this will actually happen in the future. But I mean, the simulation environment, of course, in which AI can experience what it is like for humans to bite an apple. This is just like some engineer writing some reward function. That's not any more different compared to the language description of a human experience being not real. And so, though it seems the current challenge with the simulation environment, though, is that in terms of the concepts, it's really limited in that there's no apple. I mean, you're not going to bite into an apple, let alone you're not going to really cook very much or grow plants and tiger comes along and maybe attack farmers. And there's nothing really quite like that happening in a rich setting. So primarily due to the lack of realism and considerably narrow scope of representation in the simulation environment, I worry how it will scale up in order to match the scope of common sense understanding that humans have about the real world. But having said that, there's something uniquely really important in the simulation environment, which is interactions. And in the current setup with the pre-trained language model, we learn from static data without having the chance of interacting with it. So I think embodied simulation environment can be used in particular to explore how to learn through interactions through multiple modalities. But yeah, that's my current personal thoughts.
Okay, so I think if people are not in the Rocket chat and they want to ask a question, please raise your hand in the Zoom and then I'll call on you. In the meantime, I do have a question for Yejin. So, what is fascinating to me is that, the declarative knowledge in your work looks very different from ontologies that folks have been, working on for like, 20, 30 years. I mean, so is it time that we kind of throw away those ontologies and, replace them with, these language-based ontologies where the nodes are text and the relations are well defined, but the nodes are in a sense not ontology nodes in the way that folks are used to.
Yeah, that's a really great question. And even for the social chemistry design, I didn't share the nightmare we had designing this particular set of annotation that we did. There's something strange about ontology in that it seems that we do have hierarchical concepts for sure about social judgments, culture, pressure, different legality, whether something is legal or not. And when I say these things in this manner, these do come across as, yes, obviously different concepts. But when we face a particular concrete situation and then try to somehow categorize that into bins, all sorts of strange situations happen. It's almost like there's a lot of slippery slopes. And then it's really difficult to come up with, it seems, ontology that's really there's no counterexample. So that's some like open, and it's a open philosophical question for me, like what to do about it. And there's a little bit of ontology like thing going on here as well, in the sense that, well, in some sense, we have this high level division, but to me, they always seemed a little bit blurry. And so maybe what happened also with this original atomic as well as atomic 2020 is that we have very loose sense of ontology, like 23 different common sense inference types, but they're not as formal as conventional ontologies. And I honestly don't know what to think of it, other than the fact that at least this year I'm thinking that maybe it's okay if the ontology is not very clean cut, because when you, at the end of the day, when you train neural models on top, they don't care either. So maybe in some sense that's how humans are as well. Like we understand ontology as vague points of reference, but in real life situations we never seem to really heavily rely on it either. So
Okay, thanks. So I think we have time for one question. Well, we'll have Henry ask a question. He raised his hand.
Hello, can you hear me?
yep.
Yeah. So yeah, I'm thinking about the, I mean, excellent talk, really excellent talk. I'm thinking about the ethical database, and one thing that I observe is just, when you have data that comes from people, as opposed to data that comes from instruments or something like that, people tend to have points of view. And the problem is a lot of machine learning techniques, they're kind of like putting things into a blender. You just hit puree and you get some kind of average of the thing. And with moral judgments or ethical systems and stuff, you run the danger of taking one thing from one perspective and another thing from another perspective and then combining them because you don't know that they're not consistent with each other. So I just wonder if, thinking about points of view might be helpful when you're working on these moral or ethical questions, because people tend to have coherent perspectives that differ from each other.
Absolutely. And I appreciate that you point that out. And in fact, indeed, currently everything feels like a neural soup. Everything becomes blended into uninterpretable stuff. But that's a great research direction going forward, like how we incorporate more precise, crisp values or rules, and then the machine being able to actually tell us, well, the reason why I made this judgment is because you told me that somebody said that XYZ is true and whatnot. So, but I will just leave it as a exciting future research problem to consider further.
Okay, thank you.
Thanks, Jen. So I think we're out of time, and so I want to close the session just by reading the comment on the chat. Very, very, very good talk.
Thank you so much.
And I wholeheartedly agree with that. Thank you, Yejin.
Okay, then. So I think it's time then for the starting with the first paper session of the day, focus on collecting and representing common sense knowledge. Since this is the first paper session, just another quick reminder for the presenters and the audience. Long paper presentations have 15 minutes plus 5 minutes of discussion, and short paper presentation 7 and 3. So I would then recommend to start right away with the first paper towards an atlas of cultural common sense for machine reasoning. And so please, if the presenter is ready, can share the screen and the presentation. Thank you. Anurag is the presenter. Yeah.
Hi, can you hear me or see my screen?
Yes, we can see you on the screen, and also we see your slides.
All right, so hi everyone. That was a great talk, Dr. Choi, and kind of, I guess, makes my job harder or easier the way you want to look at it following that talk. All right, so the work we're presenting here is towards an atlas of cultural common sense for machine reasoning. I'm Anurag Acharya, and we did this work together with my PhD advisor, Mark Finlayson, and Karthik Talamadupula from IBM Research. And I'm here down at Miami in FIU. So I guess this part is made easy by Dr. Choi's talk, that I don't really have to convince you there's been a major advancements in common sense knowledge, right? So like we just heard, Atomic has been great in its field. It has over 900,000 descriptions of inferential knowledge. Similarly, ConceptNet has the semantic net structure, which makes it even easier, and it has over 1.5 million common sense knowledge bits. And of course, Comet automatically learn the common sense knowledge, as we just saw in Dr. Choi's talk. And I borrowed this diagram from Comet paper, and as you can see the structure, I was going to go a little bit into it, but we just heard about it, right? So I think we can all agree that there's been a major advancement in this field. Now then, why do I want to learn, or why do I want to work on this cultural element, right? So let me try to convince you with a few examples. So one of the good applications for common sense knowledge is question answering systems, right? That's one of the uses that we use it for. So here's a question that we could pose. We go to a restaurant and we order water. What do we get, right? So do we get a cup of water with some ice on it? Do you get a hot cup of water, or do you get sparkling water? Now, depending on the people who are on the talk, all of you immediately have one correct answer, right? Here's another question. You've been invited to a wedding. How long will it last, right? Does it last several days? Does it last a few hours? Do I need to book my vacation days? What do I need to do, right? So the answer to both of these questions is it depends, right? So the answer for me, in case of the wedding, if my friend invites me to a wedding back home, I'll probably have to look for vacation days. But if my friend here in the lab, somewhere in the US, invites me, I'll probably just skip lunch and just go ahead, right? So really what we see the difference here is that all this great work, really great that they are in the work they've done, is there's a missing component, and that would be the culture component, right? So, and we see this in real life, right? For humans, culture shapes our cognition, our perspective of looking at things, and the language that we speak, right? So like Dr. Choi said earlier, maybe people are just different, and we are. So why not try to encode that information into our systems, right? So then I think it is vital for us to embed this cultural information into AI systems, right? But of course, there's a key challenge, right? How do we actually collect this cultural information? How can we collect cultural knowledge across different cultural groups? Right? Now, this is an important question. So obviously, what we need common topics and that are comparable like for like across various cultures. Now, this turns out to be actually a really difficult task, because as we all know from our own experiences, the experiences and the things within culture are very specific, right? So we are very nuanced, but at the same time, we need to find something that is comparable across different cultures. So there's kind of like a irony there that we need to find something across, right? So for example, let's say we want to collect cultural information and we ask, hey, how do you celebrate Hanukkah in your culture? Now, it's a pretty good example of what specific culture observe, but that question does not make sense for me because, you know, most people back home don't observe Hanukkah. Or we could talk about, hey, what kind of things do you like to do before your favorite sporting event happens? Now, that is very generic. Of course, it will suit for every single culture across, you know, the human civilization, I guess, but that's very specific, so very generic. So we can't really get an honest answer out of that. And some people might have experienced that yesterday, right, during the Super Bowl. So what we propose is we'll use rituals as the analog to compare various cultures, right? So the one advantage that we have for rituals are that they're well studied and well known, which means there's a rich theoretical grounding, and there's been a lot of research from anthropologists and sociologists, so we know there's a good theoretical background under it, right? Now, of course, I realize that what we need to do is rituals are not equal to culture, right? We're talking about injecting culture, but we know that rituals are not all of culture, right? But there seems to be a strong concomitance between rituals and cultures. Like the example I gave earlier with the water, of course, that won't be covered by just rituals, right? So with the ultimate goal of injecting cultural knowledge into common sense systems, what we'll then present in this paper is not that we've completed this whole task, hey, we've solved this problem, but rather we'll demonstrate a technique that we can inject cultural knowledge into our systems, and we'll use rituals to do it. And hopefully, since this technique works, then we can go further, and in the field, we can use other analogs to inject further more of cultural information, right? All right. So then the next question is, which rituals do we pick? Because like I said, there's a rich body of work there. So just briefly defining culture as literature defines it, they're defined as culturally defined set of behavior. That was by Leach all the way back in the 60s. And apparently, turns out people actually ritualize all sorts of activities to varying degrees. So then it's not about whether or not someone ritualizes certain event, but rather how much, right? And there's all sorts of different rituals, and we go a little bit more detail in the paper, but for our purposes, we'll talk about two types of rituals: rites of passage, that's things like birth and death and, you know, birthdays and things like that, and then calendrical rites, things like New Year's and things like that, right? So of course, there's also political, you know, sports and all of those kinds of stuff, but for our sake, we won't talk about that. So what did we select? So we selected 6 main cultures for this pilot work. So the first one is wedding, right? Again, common across cultures. Funeral. Coming of age ceremonies shown here as bar mitzvah, but we can sort of imagine coming of age as quinceañera or bratabandha or something like that in every culture, some form of the other. Birth, New Year celebrations, and then birthday. So we can sort of all agree that these are specific enough in different rituals, but also good enough to compare across cultures. All right. So the next task then is, how do we select, which groups do we select? Because remember, all of these being able to pose what questions that we answer is really important, right? So what groups did we select? So for the beginning, for this work, we've decided to focus on the United States and India. And of course, again, cultural groups are not necessarily the same as national groups, but for simplicity, we picked these 2 countries. And the first reason is sort of obvious as to why we did this is, of course, they both speak English, a lot of them, most people. So that's really useful for us since we're doing this task in English. And we have access to them since we did this on Amazon Mechanical Turk, and there was a significant presence of Americans and Indians at this venue. And of course, it allows rich cultural contrast, because you can imagine there's a contrast between the prevalent culture in the US versus India. And then not just that, they're within themselves incredibly diverse populations. So we can sort of hope to see a lot of diversity within these cultures, not just against each other, right? So what is the methodology that we actually use, right? Again, we did the hard task of saying, what do we need to use? How do we do it? So what did we actually do? So what we did was the participants were given one of the rituals, one of the 6 as a prompt, right? But it was preceded by some self-identification questions because we wanted the participants to self-identify. And these questions were on their ethnicity, race, their native language, their religion. And we also asked all these things for their primary caregivers, like parents or grandparents, whoever raised them. Because again, the literature suggested that this has a big impact on how people perform rituals. So we asked about their caregivers as well. We actually started by doing a tiny pilot at FIU premises themselves, so just to see if our technique worked. And we actually started small with 3 rituals only: the wedding, funeral, and coming of age. And we saw that everything worked fine. And then we proceeded to the main phase, that is the on Amazon Mechanical Turk. And we used all of the rituals. And we have a small group of 77 participants after correcting for bad fit answers. So again, this kind of shows that this is more to demonstrate a pilot rather than, we've not really solved the whole problem, but we're kind of in the way of it. Right. So what really was in the questionnaire, right? So we came up with some event-specific questions, right? So that we need to ask. So those were things like, where does this thing typically happen? And when does this happen? How long does it go? How many people are traditionally in it? And then among the people, we wanted to know which people are the focus of the events, right? Like who are the important people? And then we wanted to know all this kind of stuff, right? So we came up with this questionnaire. And then what we also wanted were some specific details about these people, right? So to find the specific details, to go further in detail, we took some of the questions from Atomic and we tried to build on top of it, right? So what we did was we took some of the questions that Atomic used, and then we added things into the questionnaire, like, does this person typically use something during the event, right? And what kind of things do they use? Because remember, with rituals, that's also important. So we kind of added stuff on top of the Atomic work. And it's divided into 3 categories, like I said, before, during, and after, one more than what Atomic has. And we considered the same 4 types of questions that, again, since Atomic is the standard, with our intent and reaction, the needs and wants, the effects, and then the attributes, right? So these are the questions that we posed. So let me share the results that we got, right? So let's start with the demographic results of the participants. All right, so this is the data for the US participants, the y-axis being the number of participants. So as you can see, there's a clear indication that the religious view changed as people grew up. So when they were growing up, there seemed to be less non-religious people in the US. That grew significantly, as you can see from this data. Whereas let's compare that to India, where the religion views didn't seem to have changed. In fact, there's one person that turned Hindu, even though they were not Hindu growing up. And you can see that the majority religion is very clearly obvious from these numbers, right? So that's the difference. So, and here, I guess more interestingly is one of the results that we have. We asked people, how long are the rituals? So this is how long were the different rituals in each country. And you can clearly see for funerals, the length for India is absolutely completely different than the US, where the American participants said it lasts a few hours, right? 1.5 on median. Whereas the Indians said it lasted 312 hours, which means 13 days, right? So several days. So that is a big difference, right? Like the kind I talked earlier, similarly with the wedding. Another difference we see is how many people participate in some specific ritual. And as you can see in the wedding, it's really different again. Is the Indian participants said 500 people participate on average, whereas in the US they said about 70. And you can sort of see that trend in all the other rituals as well. So that's a big difference here, right? So moving on, there's more results to share. There's an anecdotal result where, let's say we have a question like, before a wedding, what does the bride like to do, right? So in the US, people said they like to plan the wedding, right? And for India, people said they like to know the groom's family again. Now this would be, I can't imagine any American bride saying, I want to get to know the groom's family, except for rare cases, because the presumption is, of course, that you already know that by the time you're getting married, right? So the common sense, you would think if someone is from the US, is that you already know the family. But of course, with a lot of arranged marriages still happening, the common sense is not the same across cultures. Similarly, with the funeral, if you ask where does a funeral take place, people in the US would probably say in a church or a funeral home, whereas in India, people would say, at cremation grounds, funeral. Again, this is just quote unquote common sense that anyone would know in that place. It's just completely different for different people, right? And these data are user generated, by the way. So let's look at the word cloud, just basically the major things that the people talked about in the US and India. I know there's a lot of words, so I'll highlight a few things that we need to focus on. So for example, as you can see, the word family is pretty pronounced in the Indian word cloud, whereas the frequency is much lower in the US. Like, you can't even see it unless you try to, right? So similarly, we can see other things like party, honeymoon. So these are the words that seem to have higher frequency in the US cloud, whereas religious, rituals, cultural, those things seem to be the focus in the Indian group, right? So you can see a clear difference. So then what do we do from this information is we want to have a cultural common sense graph, something akin to this, for our data. So the blue here is common for both cultures, and orange is for Indian and green is for the US. You can see the differences that I just mentioned earlier, right? So this is a sample graph. So we're currently in the process of creating it for our entire data set, but this is the kind of thing that we want to have and hopefully use it for other existing systems. So then let me end with this listing some of the contributions is, so we propose the novel approach of cultural common sense. Hopefully you're at least slightly convinced that yes, we need to go forward with this. And then what we did was we created an approach to collect cultural common sense. And with our pilot experiment, we're showing that, all right, the approach works for at least one way. And then we have initiated the cultural common sense graph. Like I said, this is a work in progress. So we're currently expanding by collecting data from Filipino participants. So that's gonna hopefully further diversify our work. We're working on creating like the complete common sense graph, hopefully that can be used. And we'll augment that data to existing data set and we'll add that cultural data to it. And then finally, what the hope is that we'll use these augmented data set to improve the existing systems. So that's it. Thank you for listening, and I'll be happy to take questions.
Thank you very much, Anurag, for the presentation. So I don't see any question in the chat, but I have a question for you. So I think in this last slide you mentioned that you have just initiated the construction of a cultural common sense graph. So of course, these tell us what type of expressivity you were planning for, of course, representing at the machine level this type of cultural knowledge. Although it seems to be very complex, it seems to have various, I would say, aspects that may not be completely captured by the expressivity of a knowledge graph. So have you considered alternative knowledge graphs, knowledge representation techniques for this type of research?
Yes, that was actually one of the things that we talked about is because, like you said, the graph, especially two-dimensional things, might not be sufficient. We are considering maybe higher dimensional things and how we can represent them. But I think what we're taking cultural common sense as the starting point, very much the starting point and not, our final aim. So like you said, we are considering other multidimensional things. We haven't quite began really diving deep into it, but that is definitely something in our to-do list. Yes.
Okay, thank you.
Can I ask a question?
Sure thing. Yeah.
Yes, it's really a follow-on from your question as far as the knowledge representation. In the past, a lot of the common sense representations have fallen along the lines of various first order or second order logic type representations. Are you are you going to use as a basis more things in the area of model theory as far as the mathematics behind actually making these representations? And I bring that up because in the, some of the other knowledge representation, the more current things in machine learning, the optimization theory, a lot of the real analysis type things, a lot of statistical mathematics are being used. But it just seems like when we're doing these knowledge graphs that we are going to find ourselves using more symbolic logic type representations. Is that where this is going?
Thank you for the question. At this moment, we haven't, that is not our current direction. I mean, I can't really rule out, maybe we'll eventually get there, but as of now, that's not our priority. So what we want to do is like the great work like Atomic that's done really amazing, and Comet and all those kind of stuff. So in addition to the graph knowledge representation itself, we also want to try to augment the data set. So things that are, systems say, different across people. We want to focus that maybe systems will not be so, for the lack of a better terminology, West-centered, right? So maybe things will be more culturally diverse. So that's where our focus is right now, but maybe in the future, we'll focus on that.
Okay, great, thank you.
Thanks, Anurag. So we have a question also on Rocket Chat, but due to time constraints, you'll have to take that offline. So thank you again, and I think we should move to the next presentation of a short paper. So 7 minutes plus 3 of discussion by Zisheng Liang and Deborah McGuinness, Common Sense Knowledge Mining from Term Definitions.
Hello, everyone. So can you hear me?
We can hear you.
Okay,
and
yeah, so how can I share my screen? So you need to, okay. Okay.
You should be able to share the screen.
Okay.
Yeah, we see that. Thank you.
Okay, so so hi, so I'm Zhicheng Liang. So I'm a PhD student from the Department of Computer Science at Rensselaer Polytechnic Institute. So today I'm going to present our work, Common Sense Knowledge Mining from Term Definitions. So this is a joint work with my PhD advisor, Professor Deborah McGuinness. So yeah. So the CSKG, short for Common Sense Knowledge Graph, is kind of is very useful for many downstream applications, but unfortunately it is incomplete respect to the breadth and diversity of common sense knowledge. So so we think that it would be very desirable to increase the coverage of the CSKG automatically instead of as a complementary effort of crowdsourcing in the literature. So we want to infer knowledge triples from text. Natural way to do this in the literature is to adopt an extract and score approach. So so suppose that we have got some candidate triples extracted from somewhere. So the research question is it possible to automatically distinguish the high quality triples from others? So the focus of our work is to investigate the performance of existing machine learning models for scoring those new triples extracted from tests. Specifically, we use novelty and validity as the evaluation matrix. So so regarding the source of the regarding the type of tests that we are going to extract common sense triples from, we in this work we use dictionary term definitions because we think that the term definitions provides very precise definitions of the properties of terms in our daily life, and it is shown that in the literature that concepts have some properties that can imply common sense. So the approach we take in our work is to first generate some candidate triples by using the frequent part of speech tag sequence patterns of concepts. And then the next step is to examine some existing machine learning models for triple scoring. So there are two types of model we look into. So two supervised model, which we train them on the CKPC data, and the last one is unsupervised model, which is we just run it on the candidate triples and without any training. So let's look at one examples of the dictionary term definitions of bartender. So from the definition, we were able to extract several triples, potential triples on the right. So especially the last one, bartender capable of preparing or serving drinks can be extracted using the part of speech tag patterns shown on the right. And then so in this work, we focus on 12 concept map relation types as the extraction targets. So in the table, we can see that we can actually extract a huge number of candidate triples from the term definitions. So after extract the candidate triples, we so we use the aforementioned 3 different models to predict the possibility scores. So we first look at the score distributions from these 3 models. We observe high variability in the score distribution, which means these 3 models does not have a very in evidence consensus towards the possibility of the candidate triples. So for evaluating the quality of the of our approach, so we use novelty and validity as the evaluation matrix. So for novelty, it is measured by the percentage of generated triples that are unseen in the training set. We also look at the compute the novelty rate against the full subset of concept nets. Instead of doing exact match when comparing 2 triples, we also do some normalization, pre-processing steps, like removing the stop words and treating the phrases as a back of words after lemmatization and stemming. So we also look at some other automatic proxy for novelty. We tried word embedding based similarity, but it seems not working very well in our case. So for validity, we sampled 50 triples out of the highest score triples out of for each relation, and then evaluate their possibility manually. So the criteria of this the triples for selecting the high score triple is that we search for the first 2 we chose the triples higher than 0.9, and for PMI we select the top 1,000 triples. So for the results, we can see that the models can actually extract some valid and novel triples, but the performance vary on different relations. And we also have there is an interesting finding is that it matches our observation that the term definitions contains some more common sense knowledge for a few relations, like allocation capable of and has property, etc. So one weakness we observe in our manual evaluation is that the models have kind of weaknesses when scoring triples, because they are all the triples are all from the high score triples, but the validity for those triples are all less than 50%. So some takeaways, as we saw in the previous slide, we see a very wide variability in the started scoring methods. But actually, we humans can do a good job, have a great consensus toward those possibility of those triples. So that's why we suggest when we use this when we use these models in practice, we need to look at the weaknesses of and strengths of those models. So specifically, when we want to choose a proper model to use, we need to it might be relation specific. So and we also need to determine when the mine valid and novel contents is worth adding. For example, we see valid triples camper allocation tends from the definition of camper, but concept that already have a very similar one, and then so it's kind of difficult to make a decision. But we suggest that we can actually look at the performance game of some downstream application like question answering, if we added the new knowledge into the KG. So for summary, we also release our code and data on GitHub. So if you are interested in our implementation and want to look into the more of the details, please read our paper and look at the GitHub repo. Thank you.
All right, thank you very much, Jason. So I don't think we have time for questions, unfortunately. So any type of question on this paper, please use the Rocket chat. So thanks again. Let's move on to the last paper for this session. A paper on AWARE, ontology for situational awareness of autonomous vehicle in manufacturing. And please, the presenter may get ready. And the paper is by Bolus El-Azamar, Sidin Chali, and Michael Felber.
Yes, hello everyone. I'm not able to share screen because I guess the previous participant needs to stop sharing.
Sure. Jason, please, can you stop?
Oh, okay. Okay.
Okay.
Thank you very much.
Okay, can you see my screen now?
Yes, thank you.
Okay, awesome. All right, so welcome to our presentation entitled AWARE, an ontology for situational awareness of autonomous vehicles in manufacturing. This work has been done with Serene Shelley and Michael Ferber, and it is supported by BMW Group, Logistics Robotics Division, and Karlsruhe Institute of Technology. So the work in this paper falls in the scope of logistics automation within manufacturing plants. So the robot you see on the slide is BMW Group's Smart Transport Robot, or shortly referred to as STR. This robot is designed to transport dollies or roll containers through logistics halls in a car manufacturing plant. So an STR can typically lift, transport, and set down a load weighing up to 1 ton. However, the problem is that autonomous robots operating within a fleet in a complex manufacturing environment, such as what we have in production plants, actually lack the agility and ability to smoothly perform their missions without getting into cumbersome situations. So in the following slide, we're going to show some of these bottleneck situations in a later slide. To solve this problem, we must first enable robots to have kind of common sense and understanding of their environment. And that's what we refer to as situational awareness. In literature, the term situational awareness is defined as the perception of relevant elements in the environment, the comprehension of their significance, and the projection of their future status. So according to Friedman and Adams, increasing common sense levels is a viable approach to achieving high levels of robotic situational awareness. Thus, in this context, achieving situational awareness in robotics goes beyond ensuring basic functionalities such as navigation or manipulation or task planning towards being able to make decisions on the most favorable behavior or towards a more optimal course of action. So here is a short video to give you a better understanding of how real-world situation actually looks like. So as you see, the manufacturing environment where the robots are deployed are complex environments, because you see both humans, machines, autonomous, non-autonomous vehicles, and moving objects, non-moving objects, static objects. So, and the complexity is also increased by the difficulty of establishing traffic rules book, like we see on the streets, or traffic lights, for example, to regulate traffic within a manufacturing plant. So to be more concrete about the purpose of this work, we show here some impediments which we observed during case study conducted on productive autonomous robots deployed in manufacturing plants in Germany. So although the robots are equipped with the required hardware and software to operate safely without human supervision, their behavior still demonstrates a lack of smoothness due to shortness in cognition abilities. So some of the operational drawback here, on the left figure, you see that overtaking an obstacle on a two-way aisle might lead to a bottleneck with oncoming traffic. So in that case, a more suited behavior is to avoid overtaking long obstacles. In the middle, we show a convoy driving situation. A desired behavior for the rear robot is to mimic the behavioral pattern of the front robot without attempting to overtake, since the front robot is assumed to have anticipated insight and thus a more reliable judgment on the situation. On the right, you see that the field of view of the autonomous robot is deficient because of proximity. So the load carried by the forklift is not necessarily in the robot's field of perception. The autonomous robot is required to perceive the loaded forklift while approaching, and given that the robot knows that it's loaded itself, the robot is expected to reason and deduce potential collision of loads, and thus the robot must increase separation distance to the forklift. So overall, our main contributions of this paper are the following. One, we propose the AWARE ontology, which is available online, for modeling situational awareness. Our ontology combines the representation of the environment, the robot perceptions, and the decisions the robot is allowed to make. Two, based on an evaluation, we show the coverage and applicability of the AWARE ontology to automobile manufacturing environment to ground robots' proprioceptive and exteroceptive perceptions, as well as priors on the environment for the purpose of situational awareness. So although situational awareness is a prominent concept within human factors community, it is rarely used in robotics. So we have a paper from Dan, Fox, and Gross, which present an application agnostic definition of the terminology situational awareness and the process involved in acquiring situational awareness. So according to the paper, an agent is situation aware given a goal and the situation if it can build a complete representation before the situation evolves. Kama and Jane presented the domain-specific ontology for modeling shop floors with autonomous and automated vehicles. However, their ontology only focuses on the communication aspect in a simulation scenario and does not cover robots' perception. Also, other research related to robotics cognition, such as Diab et al., adopted knowledge models focused on task planning, which does not require a foundational modeling of agents' awareness. Besides that, the operational environment represented in the knowledge model is often not relevant to manufacturing plant. Also, several ontologies have been proposed modeling awareness-related aspects, such as sensor information, but without really considering the awareness as a main aspect of the ontology. Such ontologies, which are outlined here, are adopted in our paper as upper level for our ontology. So SUMO, which is a suggested upper merge ontology, is adopted as an upper layer for the knowledge schema. And SSN, which is a semantic sensor network ontology, is adopted to represent sensors and observations and link them to the observed entities. So the observation class in our ontology is a fundamental class in our knowledge base. Given that n-ary statements about multiple entities are needed to represent prevailing knowledge of the situation, we used verification to enable richer definition of properties. At specific timestamp, multiple data streams emerging from the exteroceptive and interoceptive sensors of the robot are respectively analyzed and transformed into high-level observations. Then for all given observations which are presumed to capture the prevailing situation of the robot surrounding, a decision can be inferred. Here we show a snapshot also of the ontology on the artifact branch. So all dynamic assets in the manufacturing plant are incorporated within the class Sumo object. And among the objects, there are the artifacts to represent objects that are products of a making, including agents present in the plant that are not humans, also including sensors as well as plant itself. So Sumo artifact is ramified into subclasses like vehicle, like storage unit, like transportation unit. Vehicle class would cover forklift or autonomous vehicles such as AGVs. And the transportation unit would cover all the transportation unit which are either pulled by another vehicle, such as a trailer is pulled by a tugger train, or lifted by another vehicle, such as a dolly is lifted by a forklift. And here also in our knowledge schema, we show the Sumo region concept, which is reused for the limited topographic area. Sumo region is partitioned into geographic and infrastructure region. So geographic area is particularly relevant since general policies and safety rule might differ from one country to another. And infrastructure region combines kind of different operation area, which are listed under operational area, and all the different zones, such as speed limit zones, no replanning zone, or restricted areas, which are under constraint zones. Also, all the sensor information are inherited from the SOSA sensor class, which incorporates wide range of the sensors the robot use. Proprioceptive sensor is used for proprioceptive sensing, which is measuring values internal to the system, such as battery system or location or battery health state or charge level, while exteroceptive sensors refer to exteroceptive sensing, such as acquiring information from the robot's environment, such as camera or LiDAR, which measures distance to objects surrounding the robot. SSN property combines information attributes related to perception capability of the robot. So according to SSN, a property is defined as a quality of an entity which is particular aspect of an entity and that is intrinsic to and cannot exist without that entity. So this includes visual features such as a bounding box, which represent a bounding box of an object detected by computer vision object detection algorithms. So to evaluate the aware ontology, we refer to a set of competency questions which we collected. So a human expert analyzes whether the deployed concepts, relations, and axioms are able to answer all competency questions. Here in this table, you see a selection of these competency questions. So we collected a competency question by analyzing the behavior of the productive autonomous robots in manufacturing plants in Germany. And we did some on-site observation and expert feedback to make sure we cover everything which the robot does. So based on the vocabulary we defined by the ontology, so the desired behavior rules discussed earlier were implemented in logic programming language. So as a result here, for example, you see in the situation that we discussed earlier where the robot encounters a long obstacle. So instead of overtaking, the robot here is stopping because it's understanding that it's a long obstacle on a two-way aisle and it cannot overtake in that situation. Here, another example of a convoy driving situation where the front robot encounters an obstacle and stops. So the rear robot recognizes the obstacle ahead as another robot and trusts the judgment of the robot ahead, and then it mimics its behavior instead of trying to overtake that robot. Here also the third situation we discussed as well, where the robot perceives the forklift approaching and increases separation distance to the forklift to avoid any potential collision of flows. So our future work orientation are actually twofold. First, we will adopt some late fusion components to enable sensor fusion at the knowledge representation level. Therefore, for example, single objects which are detected by the LiDAR as a transitway obstacle and by the camera as an object of focus will have the respective observation entries linked together in the knowledge base. And second, we also will focus on modeling projected future observation based on observations recorded in a given time window to be able to give some further look into the future in a short time span for the robot to be able to expect what's going to be the situation in the next upcoming timestamp. Yeah, thank you for listening, and I'm ready for your questions if you have any. Thank you.
Thank you very much, Bulos, also, for staying within the 15 minutes of your talk. So yeah, let me actually check on the chat, the Rocket chat, if we have any question. Not here. Anybody in the Zoom call that wants to ask a question?
Alessandro, I can ask a question.
Sure, let's go ahead.
So have you thought about novel situations where something completely unexpected happens and somehow then it's when you should apply common sense? I know the power going out on one of the robots or something that's not planned.
I see.
Or
no, actually, that's not really in the context of this work because of one reason, because we have a constraint of having, a robot which is deployed as part of a process. So it needs to be deterministic to a large extent. We cannot really leave a lot for situation decisions on the spot, so it needs to be defined as like running on the street. So the cars would need to stick to rules of driveway and right of way and so on. We did not really go into the direction of unseen situations.
Okay. Thanks, Pedro. Maybe since we have another minute, so I was just curious. I think your examples are based, grounded very much on the visual aspects of the scene. I was wondering whether you were planning to include other modalities and what actually that would entail for the overall architecture.
I see. Yeah, that's actually very interesting. So now we focus mostly on the visual aspect, which include the LiDAR and the camera views. Other modalities would be having different policies depending on internal sensors as well of the robot. So such as behaving differently if you're low on battery, or if you're not connected to the internet, or you're not connected to the cloud platform. That's one aspect. Another aspect would be to cover also go in the direction of communication, robot to robot communication, where the insight might be enriched by other robots' point of view. But it's still kind of, yes, visual to a large extent when it comes to the surrounding environment. I totally agree. Yeah.
Okay, thank you, Willis. So I think, we are exactly on time. So we now have a break, and we'll gather again for the second paper session at 10:55 Pacific time, so in around 20 minutes. So thanks again to all the speakers and the audience, and see you in a bit.
We'll be talking about our work on lexically constrained text generation with the help of Commonsense knowledge graphs. This work has been done in collaboration with CMU as well as Bosch Research. So the basic problem that we are trying to address over here is that when we are talking about tasks such as concept to text generation in a lexically constrained setting, how commonsensical in nature are the sentences that have been generated. So when we say about concept to text generation, what we're essentially trying to say is that given a set of concepts like common noun or verbs that we use in our day-to-day life, the sentences that are generated, are they syntactically and semantically sound in nature? And at the same time, are they including all the concepts that were given to us originally? So let's take an example. Let's say we have four concepts: dog, frisbee, catch, and throw. An ideal statement would be something like a dog leaps to catch a thrown frisbee. But a lot of language models are not able to generate such a perfect sentence. For example, UniLM generates something like two dogs are throwing frisbees at each other, and BART generates something like a dog throws a frisbee and a dog catches it. Now, these sentences, if we look at them, UniLM is basically missing one of the concepts that was given to us, catch, whereas both of these sentences are lacking a commonsensical meaning. So in this particular work, we have tried to address both these problems, where not only are we trying to ensure that the sentences generated, they have a common sense nature to them as per human understanding, whereas we're also trying that all the concepts that were given to us, we are able to include all of them in the sentence generated. So this problem can be thought of as having three major challenges. The first part is that we want to extract the common sense knowledge information between the concepts that have been given to us. Basically, we iterate through different kinds of knowledge graphs and get the common sense information that we need. Once we have this common sense information, we would like mechanisms that can help us inject this knowledge into the language model so that we're able to enhance the language model's understanding of common sense. And finally, constraint decoding, where we are trying to ensure that all the lexical constraints that are specified in the task are included in the sentence generated. As part of this experiment, we will be working with the CommonGen dataset. So now let's look at each of these three modules in more detail. The first part, knowledge extraction, is where we are trying to better understand the relationship between any two concepts that is given to us. The knowledge graph that we've used here is ConceptNet. And the reason we find it to be a very suitable knowledge graph for this problem is because it gives us relations in form of triples. So ConceptNet stores relations as a graph, and what we are having over and what we are able to extract out of it is in form of knowledge triples. So let's say we have two concepts, audience and show. Then ConceptNet would give us a knowledge triple like audience at location show, which essentially tells us that audience and show are the two concepts related by the relationship type at location. There are three different methodologies that we propose here for extracting common sense information. Let's look at them. So the first one is multi-hop extraction. Now, taking an example of concept set such as cut, kitchen, knife, and watermelon, if these are our four concepts, then some of these concepts are very closely related to each other. For example, if I take cut and knife, they are very closely related by saying knife is capable of cutting. But something like watermelon and knife are not very closely related and might need some intermediate concepts to establish a relationship between them. So we might need to say something like watermelon is a fruit at location plate related to knife. And we have to say this because watermelon and knife are not so directly related to each other. So essentially what we are doing over here is we are trying to find those intermediate concepts that help us connect any two unrelated concepts with each other. These can be one hop, two hop, three hop, and hence the name a multi-hop extraction. But one of the downsides of this approach is that we might be extracting too much information. We might be extracting too many relations, a very lengthy chain of relations. So we work with something called as knowledge selection, which is our second approach. Here we are trying to cut down the number of relations that we have extracted and be more intelligent about what kind of relations are we selecting. So such curtailing can be done based on length and frequency. But the two things that we will be talking about today are random subset selection and prior random subset selection. Basically, in random subset selection, we assign a random probability to all the common sense relations that we have extracted, and all the relations that are above a particular threshold are selected for further processing. Whereas in case of a prior random subset selection, not only do we assign a random probability to all the relations, but we also assign them a prior probability based on their relationship type. This helps us in ensuring that more frequent relationship types are appearing more frequently in the subset that we are selecting. In either of the two cases, we ensure that at least one relation with respect to each concept is selected so that we don't have a concept for which we have not selected any relationship, so that we don't have any concept for which there is no corresponding common sense relation that we have extracted. So this is what we do in knowledge selection. A third approach of query expansion is a bit different. Here, let's take an example of the concept set, drill, field, run, and team. Now, there will be many common sense relations that we will be extracting with respect to these four concepts. We try to identify which are the intermediate concepts which are common across these different concepts that we have extracted. So for example, baseball is a concept that would have been ideally an intermediate concept between these different concepts. And if it appears in at least half of the concepts, if it is associated with at least half of the concepts that have been given to us, then we can feel that yes, baseball is an important concept, intermediate concept with respect to these four concepts that have been given to us. And we call these intermediate concepts that we're extracting as expansion concepts. So in short, what we are trying to do over here is take a given set of concepts, find what are the important intermediate concepts that connect these given concepts and call them expansion concepts. So these are the different methods that we propose for extracting the common sense information from a knowledge graph such as ConceptNet. The next part is how do we inject this information that we have extracted into the language model, because we have observed that language models are kind of very are very basically learning the corpus which they have been trained on, and we want to inject external common sense knowledge into it. So the language model that we experiment over here is UniLM, which is essentially a multi-layered bidirectional transformer. And although it gives a great performance on common gen dataset, but still it is far from a human level of common sense understanding. So the first baseline method that we propose over here is knowledge concatenation. And what essentially we are proposing over here is that whatever external common sense relations that we're extracting, or the expansion concepts that we just talked about, whatever we are extracting, we just concatenate them to the original set of concepts that we were sending. So let's say if we had four concepts, run, team, field, and drill, and we had some expanded concepts like baseball, player, tie, and so on, we would be sending a new list which would be comprising of both the original concepts as well as the expansion concepts. But a more interesting approach that we want to focus on is the attention-based injection, where we are trying to learn the attention between the concept set that has been given as well as the concept relations that we're extracting. So let's say we have this concept relation that we've extracted, football related to sport. What we do here is we first tokenize them and convert them into a phrase like football related to sport. And then we train an encoder to learn a representation for the BERT embeddings of these common sense relations. At the same time, the UniLM model will give us the hidden representation of the original set of concepts that we are feeding to it. Once we have these hidden representation of the original concepts as well as the concept relations, we can calculate attention between them, and this can then be fed to the later layers of the UniLM model. We will be discussing more about how these two methods and their performance compares in later slides. The third part of this entire module, which is the constraint decoding, is a part where we are trying to enforce the different kinds of lexical constraints on the sentences that we have generated. So the common gen dataset provides us with two major kinds of constraints. One is the including all the concepts that have been given to us, and secondly, ensuring that all the POS tags match correctly. So here, usually in the process of decoding, we would be considering only the top beam with the highest probability as the output sentence. Instead of doing that, we consider the top n beams, which in our case are the top 4 beams, and we calculate a coverage score for them. Coverage score is essentially calculating what percentage of concepts are covered in the final sentence generated, and at the same time, how many of these concepts have a correct POS tag attached with them as specified in the given dataset. So the sentence with the highest coverage score is obviously selected. And in case there are two sentences which have same coverage score, then the sentence with the higher probability as given by beam search is selected. Now let's talk about the experimentations that we have done. As I have focused, there are three major parts of this entire problem statement: the knowledge extraction, knowledge injection, and constraint decoding. And this entire experimentation is built around doing different kinds of ablation studies by plugging and playing with the different approaches we have available for each of the module and seeing which of these combination works best. We evaluate our results quantitatively on different metrics such as blue, rouge, etc. And we also do a qualitative analysis in later slides. So the one thing that we find is that common sense injection definitely leads to increase in the different evaluation metrics that we have. The increase is very slight and very small, but we definitely see an increase in all the different kinds of metrics that we are evaluating on. Attention plus prior subset selection is a model that gives us the best results in terms of blue score. And if we also add the best and beam scoring for the constraint decoding part, then although our blue score dips a bit, but it definitely sees an improvement in other scores. In later slides, we will see that the best and beam scoring is very important when it comes to enforcing the lexical constraints. At the same time, we also observe that selecting a subset of relations instead of selecting all the relations is definitely a better way, and it's definitely giving better results. We can attribute this to the fact that including a subset reduces the amount of noise that we are sending to our models. And the baseline thing that we want to focus here on is that although the results don't see a huge improvement in terms of blue score or Roche scores, but in the qualitative analysis, we observe that the common sense information has in fact improved a lot. The blue scores here don't really improve a lot because we are just comparing the target sentence that with the sentence that we have generated, which might or might not be similar. But at the same time, the common sense nature of the sentence has improved significantly. Talking about the query expansion results, we find that these method as well as the concatenation methods do not perform so well. And the blue score is around 25, which is much lower than the blue score of 28 that we saw for the multi-hop methods, or the blue score of 27, which we observe for baseline models. At the same time, we can say that this is primarily due to the noise that is being added because of the too many expansion concepts being added. And finally, the lexical constraints. Here we can, as we were talking before, the best and beam scoring helps us reduce the number of missing concepts from around 42% to 28% and 27%, which is a great improvement. The mismatching POS also drops in all the different methods that we are proposing, but the drop is not very significant, and therefore it's definitely a scope of future work. Now let's take some examples of qualitative analysis. And here we can see that in case of attention injection, we were able to observe that both the commonsensical nature as well as the concept coverage improved. It is not yet at the human level, but still we were able to observe improvements in both, improving the commonsensical nature as well as the number of concepts that we were covering. Similarly, when we compare prior subset versus random subset selection, we observe that prior subset is definitely better. It has better common sense. And at the same time, it is also reducing the number of concepts that were being repetitive. And finally, talking about constraint decoding, here we can observe that adding constraint decoding, adding the best and beam scoring method helps us in improving the coverage significantly, as we saw in the quantitative results. And this does not have any major impact on the commonsensical nature of the sentences that we generated, but there were few exceptions which might need some future work. So all in all, in this particular work, we are not trying to beat some kind of a blue score, but what we are trying to do is try to understand how we can devise methods that can help us enrich the language models with the common sense knowledge and help us in improving the amount of concepts that we are covering in the sentence that we have generated. As next step, we would like to work with all of the three different approaches that we have proposed. We would like to work with more knowledge graphs. We would like to experiment with different kinds of language models, different injection methodologies, and also different ways in which we can perform constraint decoding in a more in a better way. So that's the work that we have done for this particular task, and I'm happy to take any questions. Thank you.
Thanks very much. I don't see any questions in either the chat or, oh, I see two people typing. Can you go back to the next steps while they're typing?
Yep.
Let's see. So which language model is next? You said experiment with other language models. And why are you choosing whichever one you're choosing?
Yeah, so we are choosing with a BART model because this is, so basically some other, like there have been some more work on this particular data set that we have observed, and BART is one of the language models which has performed great as a baseline. So we want to see how our models, how our approaches of extracting knowledge and injecting knowledge work with respect to BART. So that looks like a very promising area because the baseline results are good. So it might be good to see how our methods further enhance it.
Okay, I still see people.
Does it answer your question?
Oh, go ahead. Yep. Philippe, do you want to just ask your question or should I ask it?
I can ask it. So I was just wondering, I see that one of the future works is to apply these to other knowledge graphs. And I was just wondering if the authors can speculate on how easy would this be? And, are there any expected limitations of the method, any expected pitfalls and that sort of thing?
Yeah. So I think one important thing for our method is that we try to we expect the knowledge graph to give us some kind of a relation between the different concepts that we have. That's one thing that we want our knowledge graphs to give us. And secondly, we are also heavily reliant on the intermediate concepts that we are extracting. So these are the two things that are important to us. So the different kinds of knowledge graphs that we might be experimenting with, the way data is structured in them, what is the structure of data that we are getting, what is the noise that is in the data set, are they giving us information about tokens that can be potential tokens in the final sentence generated. Those would be some of the key things for us to work on. We are thinking of different ways in which we can use different knowledge graphs. One is, we use knowledge graphs, we extract information from them as it is, we tokenize them and calculate attention on top of it. That's one way. And second thing is we use these different knowledge graphs to construct a concept net based or a concept net type of relation between tokens. So for example, we might have a huge corpus of sentences in the form of common sense reasoning. So we can extract them, and from that we can try to create a graph-like structure on our own. That's one way. And second way is, we just send it as it is to calculate attention on top of it and see how the sentences are being generated. So to also answer your question in one more way, like the pitfall that we think here might be that if we are not able to extract these intermediate tokens, that might be a pitfall.
Okay, I actually have another question if nobody else has. I was wondering, so in the past when we tried to use, for example, ConceptNet or another source that has a lot of lexical nodes to extract paths, we were always seeing a lot of noise coming from ambiguity of nodes, right? So for example, run can mean a lot of things, can be as a verb, as different nouns and so on. And in our experience, this was often throwing us at paths that we didn't want to end up with. So how are you guys dealing with this right now? And is this a problem? How big is it, and so on?
And you get a 1-minute answer. Sorry.
Okay, sure. So definitely, if so the thing is, one good thing over here is that the different concepts that have been given to us, they're usually not very distinct or very highly unrelated from each other, right? So for example, if let's say I have a concept like plant, which can mean something like planting a tree, or which can mean like a factory plant, right? So if the other concept is chlorophyll, right? So the plant factory and the chlorophyll, these concepts will have a huge chain between them, which will automatically get rejected because we are trying to not use concepts which have too many intermediate concepts between them. At the same time, the POS tag is also an important factor which helps us, because plant can be a verb, it can be a noun. So usually, if they do not belong to same part of speech, it's easier for us to reject concepts which are belonging to some other part of speech. But if they belong to same part of speech, then yes, it is another pitfall and the model might get confused.
Okay, great. Thanks very much. That was a good talk. And if you could stop sharing your screen, and the next paper will be deriving behavioral tests from common sense knowledge graphs. And I'm not sure who's speaking, but we can see your slides.
Hi. Hi, can you hear me?
Yes, just fine. Thanks.
Okay, great. So I start. Okay, I'm Yasaman Razaqi, and I'm presenting the work Driving Behavioral Tests from Common Sense Knowledge Graph. This is a work with Robert Logan and my advisor, Samir Singh. So I'm starting by emphasizing on the fact that accuracy and benchmarks is not enough for testing our models. And here To further illustrate, I use an example from the ACL checklist paper that gives us a toolbox to create lots of simple behavioral tests. And here we see a Google sentiment analysis models has a high failure rates on a bunch of simple examples like I didn't love the flight, or I can't say I recommend the food. And having this test gives us a good intuition of where our models usually fails to further look at them. And with having this in mind, our goal is to create some behavioral test cases to examine common sense models. And the goal for these test cases is to be simple and easy to scale up. To create common sense tests, we need a source of common sense knowledge, and common sense knowledge graphs gives us a huge resource of structured common sense knowledge, which we want to use to create our test cases. Before going further, I want to introduce the NLI tasks, which I use as an example for the rest of this talk. In the natural language inference task, we are given a pair of sentences as premise and hypothesis. And the goal of the model is to predict the relation between these two as entailment, contradiction, and neutral. And here, for example, when we have the premise of there is a soccer game with multiple male playing, when we have the hypothesis of some men are playing soccer, the label is entailment. And when we have nobody is playing soccer, the label is contradiction. So we want to create some tests like this with the taste of common sense. And how do we do that? We are given a set of triplets from common sense knowledge graphs. We want to somehow transform them to a set of pairs of premise and hypothesis sentences with the sense of common sense and giving them to our NLI model and see, okay, what is the failure rate of this NLI model and these tests. For creating these test cases, we are introducing a pipeline here, which uses the information in common sense knowledge graphs. And I introduce the phases of this pipeline here. So first, we are given a set of triples from our knowledge graphs. And unfortunately, all of these triplets in our common sense knowledge graphs are not that much useful for us because we have an example like a person desires a headache from concept nets, or person X reads 6 books. As a result, person X wants to never read again from Atomic. These examples may be meaningful in some contexts as common sense, but since we want to create some high quality behavioral tests, these are not useful for us. So in the first phase here, we go through them and manually filter the ones that are not that much useful for us. And after filtering manually in some kind of triplets, we have a set of like useful knowledge as triplets for us. And we use some test specific templates for creating our test cases. And given these templates, we can transform these triplets from our knowledge graphs to create a generalized set of tests and to test our models here. And here, since all the information that we have from the common sense knowledge graphs are inherently varied, the assumption here is that the model should predict entailment if it uses its common sense knowledge while doing the inference. So now, given this pipeline that is now complete, we can create a bunch of tests, and we created a number of test cases from 7 relations from concept nets and 5 relations from Atomic for the NLI task. And as I said, the assumption here is that all the labels should be entailment as the golden label here. When we tested Roberto and Bart fine-tuned on the MNLI dataset, which is an NLI task, we saw that, okay, the failure rates on our tests are really quite high. And when we looked further, we see that these models mostly predict neutral as a relation between these 2 sentences that we created, which gives us, okay, they failed to use the common sense knowledge they have while doing inference. And having this, we further force the model to predict between the entailment and contradiction labels, and the failure rates here are much lower, but still we see some high failure rates on some specific relations like desire and needs which is interesting to go and look further on this. And maybe it's because the NLI dataset, models on NLI dataset do not need to know these kinds of knowledge while doing inference. We also create some test cases for the common sense question answering task based on pickup, which gives you a goal and two solutions, and the model should pick one of the solutions between them. We use a same set of relations for creating our data sets, and we tested a Roberta and BERT fine-tuned on the PICA task. And here we see that the failure rates are much lower. This was somehow expected because the PICA task is itself common sense, and the models should have higher knowledge of common sense while doing these tasks. And in conclusion, so we introduced a pipeline to create simple behavioral tests from the information in common sense knowledge graphs. This work, of course, has limitations, which we can further generalize them with more natural ways of test and automated ways, because we also had the manual filtering up. So we need to be able to have ways to further scale up the test cases. Thanks for listening to me, and I appreciate your feedback.
Thanks very much. We have 2 minutes for questions, and I'm not seeing, oh no, I see somebody typing, but as that person types, what kind of test cases are you going to focus on for doing your scale up?
So by scale up, I meant like more automated ways, somehow trying to not doing the manual filtering would be a good way, but this would be a trade-off, because if I don't do the manual filtering, then maybe the behavioral will not be that much high quality. So I should consider this trade-off between these two, maybe using more relations and more tasks. But of course, more automated ways would give us opportunity to scale up.
Great, thanks. I still see one person typing, and we've got, oh, there. Interesting to say ConceptNet, not useful for testing concepts. Will this be a general statement?
Oh, no, I said, of course, these are just some examples we found during, so we had to do manual filtering, but these are like, in some contexts, these common sense concepts would be meaningful. But it's noisy. There are like many other works that show that these knowledge graphs are noisy.
Well, let me say what I mean is that all these kind of general purpose concept nets, those kind of knowledge graphs cannot be very useful for your the kind of testing, the kind of concepts we want to push, So is that the general purpose, those kind of knowledge graph useful? That's what I mean, the general statement.
Sorry, I didn't get what you said, but I didn't.
What I'm saying is that, if we can use those kind of general purpose, those knowledge graphs to do some lot of reasonings, right? Common sense reasonings. And the reasoning means, we say, okay, this statement probably is problematic, right? So if we have to filter those things, for the special tests, that means it's difficult to put them for general use. That's something I feel important to know, if that's the case.
Sure. So there are not the number of them that are with this which I call useless here, because it's really important for my own test to have a high quality, is not that much. And of course, these knowledge graphs are really useful for other tasks. But I wanted to mention that there are some noise here, and to use them in tasks like mine, that I have to be very careful about the quality of test cases, we have to be careful about that noise.
Great, thanks very much. There's also another question in the Rocket chat, but we have to move on to the next talk. So maybe you want to answer that question of how long it took to do manual filtering.
Okay, sure.
But great talk. And in the meantime, our next and last talk in this session is graph to coherent text. Sounds like the Holy Grail. Passage generation from knowledge graphs by exploiting edge representation in sentential context.
So can you hear me?
Yes, we can hear you, but we don't see slides yet.
One second, one second. One second.
Oh, maybe we're viewing your other monitor because I'm seeing what looks like a background.
Oh, one second. One second. Ready?
Yep, that's good. Okay, we see it.
So, yeah. So you all can hear me, right? So, I'm going to present here. I'm Litton. I am from Institute for Infocom Research, Singapore. So I am going to present here our work on graph to coherent text, passage generation from knowledge graphs by exploiting edge representation in sentential context. So I will give a context of a particular use case in which such a system can be used, leveraged. Is graph retrieval task where when information is organized in large knowledge graphs, there can be scenarios where search queries targeted particular subgraphs which need to be presented to the layman user in a comprehensible manner in a natural language. So in such scenarios, the knowledge graph to text generation works can be useful. So, so this is a typical scenario of knowledge graph to text generation. The kind of work which this like our method is handling. So the text generation model takes a title text and input knowledge graph as input, and then generate a passage which essentially describe the information contains, essentially represent the information contained in the knowledge graph in a natural language, and the passage should be the passage generation should be guided by a title text. So before we go into our method, we should like I will give you some examples of coherent text and why coherence is important. So first one is a coherent text, example of a coherent text, and second one is an example of an incoherent text. In the first one, there is a topical continuity between sentences in the passage, and there is a novel content introduced in each sentence by the author. That means each sentence, while writing each sentence, the author have a trade-off between content for informative, novel content for informativeness, and content for topical continuity, thus establishing coherence. So in an incoherent text, each sentence deals with the distinct topics, and there won't be any sense relation between neighboring sentences. So which makes the text more, less comprehensible for a layman user, layman reader. So text coherence. So this is a formal definition of text coherence. So coherence is a term of text linguistics used to refer sense relation between single units. That means sentences or propositions of a text. Due to these relations, the text appears to be logically and semantically coherent. So there are other works in the linguistics which studied of topical continuity, the need for topical continuity to establish global coherence while generating text. So our method is how to explicitly model content ordering and decoding sentence by sentence to better model the order of the content, and explicitly learning an optimum trade-off between topical continuity for coherence and novel content selection for informatives during sentence generation. So through our method, we are trying to mimic the human author's way of selecting content for each sentence, in which he have a trade-off between topical continuity and informativeness while writing each sentence. So this is an abstract view of our system, which takes an input graph, and while generating content for it generates the sentence output text in a sentence by sentence manner. While selecting content for each sentence, the system refers the previously generated content and the for topical continuity and the content from the input graph for novel content in each sentence. So for our input representations, like, so in a knowledge graph, an edge represents the most is a basic unit which contains a human cognizable information. So by edge we mean the nodes connected by a relation. Nodes contain named entities or concept connected by a relation. So essentially a graph can be represented as a set of such edges, because the entire knowledge graph can be reconstructed from such a set where named entities concepts are connected by relations. So each edge is represented using a triplet, like with the named entities, relation label, named representation for dense representation for named entities and dense representation for relation label. And we compute context vectors for because to represent the context of each edge in the graph, so we compute context vectors for each edge attending over other graph edges. So overview of our method, we generate content in a sentence by sentence order, compute edge representations at each time step t of sentence generation using a gated mechanism for content generation. That means for each during each sentence generation, we update the input graph representation for input graph, so that it contains the content for topical continuity and informativeness. So for this we employ 3 gates, a gated mechanism consisting of 3 gates, a coherent gates, which selects the content for topical continuity from edge representations at time step t-1, and content selection gates, which selects the novel and content for novelty from original edge representations. That means the input graph, the original input graph representation, which didn't went through an updation through the while generating sentences. So the human author will have a trade-off between while writing each sentence based on the context of the sentences, based on the context of a sentence to be written. He will have a trade-off between coherence, content for topical continuity and informativeness. So which will be to mimic his trade-off mechanism, we employ a control gate which weights the content the content selected by 2 gates, the 2 other gates. So here is a here we depicts the picture of our neural architecture. So for each time step t of content order, there is a content ordering RNN. So for each time step t of content ordering RNN, the content gate selects the content from the original graph representation. This is the original graph representation represented as a set of edges. And this is the graph representation for time step t, computed for time step t-1. So gates take graph edges from which the content to be selected, and the hidden state of content ordering RNN, and context vectors computed for each edge, and select content from coherence gate selects the content from graph representation computed for previous time step, while content gate selects the content from original graphs representation, and control gate, which takes the hidden state of content ordering RNN, finds a trade-off between content, novel content and content for coherence. And so the graph representation for time step T is a mixture of both. And hidden state of content ordering RNN is computed at time step T by taking the mean of all edge representations as input. So from each hidden states of content ordering RNN represent the sentence representations. Each one of the hidden state represent a corresponding sentence in the output text. So from each hidden state, we use a sentence decoder RNN, which decode this material, which realize the sentence from the hidden state by attending over the edge representations computed for time step T. So this is, we use a template generation and slot filling kind of approach for materializing this output sentences, which we'll talk about in next slides. So text generation, we execute the text generation in 2 steps. Generate sentence templates, rank entities at the nodes to fill the entity slots. So here is an example of a sequence of sentence templates generated by our method. So each sentence have a entity slot, and we rank the input entities at the graph nodes to fill the slots. So this is the sentence template decoder I have explained earlier. So which initiates with the content ordering RNN hidden state and attends over the time step T for content edge representations at time step T for. So here is an entity ranker. So which takes entity representations at the entity representations content ordering RNN hidden because the hidden state of content ordering RNN decides the sentence in which the entity to be mentioned, while sentence decoder RNN hidden state identifies the slots in which entity to be mentioned. So it takes entity representations, content ordering RNN hidden state and decoder to rank entities. So the recently released dataset, auto-created dataset by Commonsense, which followed the default, and we follow the default data split for training and evaluation. So in their dataset, there is around 40K paper titles and abstracts from semantic scholar corpus, and so they use SCI information extraction, which is a state-of-art information extraction tool for scientific domain, to construct the knowledge graph, extract the relations and construct the knowledge graph. So in text generation, in objective metrics, we have an incremental results when compared to other peer systems which used a direct single sequence decoder. We got some incremental result, but relatively it's a low blue score for all systems because it's the dataset used is an auto-created dataset, and a lot of information in the abstracts cannot be, because while creating knowledge graphs, a lot of information can be lost, and a lot of information in the abstracts in the training data cannot be reproduced from the input graph. So for these reasons, like it's a relatively low blue score for all systems, but still we have a incremental advantage over other systems. So here is a example of a generated text from an input knowledge graph, where the system learned to learn to generate the content for topical continuity and informativeness without much redundant content in sentences, in output sentences. So, but our primary motive was not to report the results on objective metrics. So how the system learned to generate content in order, and it can achieve text coherence, global coherence of output text generated. So for this, we conducted qualitative evaluation using human evaluators, and the all human that we provided the output text generated by each of the methods in a random order to avoid any kind of bias. So human evaluators were asked to choose the best performing system based on the attribute under consideration. So we evaluated for coherence, informativeness, and grammaticality. So for coherence, we have a clear advantage for over others, while in others we have an incremental advantage. So in in going forward, we wish to use this kind of approach. Like we wish to formulate better models for coherence in sentence by sentence neural text generation. So this can be such an approach can leverage other external resources for identifying coherence or computing coherence while decoding output passage. Thank you. If you have any questions. Hello?
Thanks very much. We actually only have like a half a minute, so I don't see a question, but maybe if it's a long answer, you can answer my question of how you think your evaluation results might have changed if you used a different task rather than that CON-LL from 2007.
Can you repeat the question? Hello?
Hello, did you not hear the question?
Yeah, I didn't.
Okay, but we've got like 30 seconds. I was just wondering, to use a particular task from 2007, if you used a different task to do the evaluation, how do you think your results might have changed?
Because I cannot give a specific answer on that, but still, because a lot of our we reported our results on a single data set, and there should be more controlled experiments to evaluate the efficacy of the method. So yeah.
Okay. Thanks for the talk. We should move on to our next panel, and Philippe will be the moderator for that.
All right. Thank you, Deborah. And, thanks everyone for exciting paper presentations. It is a great pleasure of mine to kick off the panel of today's workshop. So we have a panel on the topic of "Are language models enough?" Which is a provocative title, and I hope that it will inspire a lot of interesting discussions. We have 4 really great speakers. And I will introduce each one in turn. Let me just spend a minute or two to introduce the setup of the panel. So we will spend 20 minutes in the beginning to give each of the participants, each of the panelists, a space to give an opening statement of around 4 minutes. So that would be in the first 20 minutes. Afterwards, we'll have the remaining of the panel will be questions that will come either from us or from the audience. So we ask the people that are in the audience in this call to to put their questions in Rocket Chat, and I will monitor, and I will use some of those questions. I'm sure that we will not be able to use all of the questions because 1 hour is too little to have to discuss all of them. But still, I think that we're gonna have some really interesting discussion. So without further ado, let me kick off the program of the panel by introducing the first speaker. So that is David Ferrucci, who is currently a founder and a CEO of and a chief scientist of Elemental Cognition, a really exciting company that is trying to build what they call natural learning, or a very ambitious pursuit of building intelligent systems. And many people know Dave from his impressive work on IBM Watson. So without further ado, I'll just give the floor to David. If you have slides, feel free to share your screen, or if you prefer not to, that's okay as well.
See. Okay. Can you guys hear me? Great. Thanks so
Yes.
much. No, I appreciate that. And yeah, I think this is a provocative topic, so I'm going to try to be provocative. So, I mean, look, my 4-minute statement, like knowing how language models work, let's do like this thought experiment, right? If your student answered questions like a great language model might, then would you award them a PhD, a master's, a BS? Would you let them graduate high school? I mean, maybe it sounds silly at first, but I think it's a serious thought experiment. I feel like the answer is not an obvious no. Okay, maybe the PhD is especially egregious, but the question is provocative in that, like, how many students actually pass more or less that way as it is? I think the approach, with language models, when you think about what they're really doing, can deliver real value in the legitimate synthesis and transmission of knowledge. I mean, like, these devices are like, constructive search systems in a sense. They use the same content, but construct structurally consistent responses that, while not explicitly represented, are likely to, at least upon interpretation, make some sense. So why? Because, as we know, the implicit knowledge models in people's heads that cause the language to occur in the first place can be represented through the patterns you see, in the language. And I think that sort of like fancy mimicry is a useful function and certainly requires some form of intelligence for humans to even do. In fact, it may serve you well in most corporate middle management positions. Okay, I'm kidding. It's a joke, but forgive me for my inductive bias. I think where it gets interesting is when you expect systems to explain why they said what they said. So you find yourself in this situation where the answer sounds right, but before you can take responsibility for the decision, you want to see the work. You want to be convinced that, in fact, the answer is grounded in the causal model that is consistent with your assumptions about how things work. So before you decide, before you buy or sell, whatever the case may be, you want to see that answer, but you want to see that it's in fact based on a logically defensible causal model. I think this happens all the time in real life with humans who also parrot their answers. So humans can and do function as really excellent language models. How do we tell the difference? And does it even matter? And under what conditions do we care? So some of us will probe, we'll dig in, and we in effect say things like, show me your work. Why does that follow? What are your assumptions? What is your evidence for the confidences in your assumptions? How do you make that leap, or how do you make that inference? And the answer, if the honest answer is always, well, that seems to be what other people might say. I generated an answer based on a statistical synthesis of all the chatter. I mean, that's interesting for what it is, but no, I don't think it's enough. So my answer is that it's not enough. Hasn't been for me, regardless of machine intelligence, in fact. I expect more from an AI and frankly, more from people. If I sense like super parroting or language modeling versus understanding going on with a human expert who I expect to trust, I'm out literally like that fast, because in the end, I have to own the decision. I'm looking for someone else to help me make a better and more informed decision. I think language models for sure should and are seeding the next generation of search systems, and with great value, but not enough to meet the expectations I have of AI to become a collaborative and intelligent thought partner that understands and reasons with us to afford better decision-making. So I think architectures that will work, and the one that we're still working on, elemental cognition, uses language models as just one component of a more holistic architecture that puts every sentence in the form, ultimately the formal representation, which we can provide, for which we can provide rational explanations.
Awesome. Thank you, Dave, for a nice and provocative opening statement. Let's go to the next panelist. So I'm happy to introduce Shifu Cheng. So Shifu is a computer scientist that has worked on a number of different, on a quite a wide variety of topics spanning information retrieval, computer vision, machine learning, signal processing. I know him I'm impressed by one of his work on that combines scene graphs and reasons over them. So you know, I'm looking forward to hear Shifu's statement.
Thank you so much, Philip. Can you hear me?
Yes.
Okay, great. So I have my slide share. I'm not sure you can see it. I'm going to make a point to answer the question that a language model is not enough, and we need a knowledge base, external knowledge base, to help us to make reasoning, particularly for multimedia reasoning. And the case I'm making is for common sense knowledge base. So this is just one example. Some of you probably have seen this example before. When you watch a movie from beginning to the end, you don't need to see every scene in between. So very often I walk in the park, I see a group of people in the park near my home. They are riding this skateboard, and very exciting. And I don't have to see from beginning to end to figure out what's happening, right? Beginning, you see a boy is playing with a skateboard and trying to reach the rail. And then very quickly you see he's on the floor. And I probably can fill the gap by saying, okay, he's trying to practice or show off or maybe impress other people, but it's a very challenging task, and the rail is slippery, and maybe he was too fast and he lost the balance, and that's most likely an explanation. So I, as a human observer, I automatically retrieve the possible common sense knowledge from the repository of knowledge base I have accumulated. And the other task we are working on, and Philip and maybe Pedro are also familiar with, is called VCR, Visual Common Sense Reasoning. This was launched by AI2 and by UW. The task is when you show the picture to the model or to human observer, you can ask the question about who, what, where, when, why. In this case, you can say, what is the bottle used for, right? So what is the purpose of the bottle? In my group, as Philip mentioned, work on computer vision. We can figure out what the object in there, what is the relationship between the object. But to answer this question, is simply to have to exhort to additional knowledge graph that we have accumulated in our mind or in the so-called human future AI system. And this is inspired by Kekne Dang in USC ISI. And so given the information we can extract from question, from language, from images, can we retrieve relevant knowledge elements from the knowledge base? In this case, we look at the concept net. And trying to see if there is a plausible path that can connect the dots. Right? So the question is about what is the purpose of the bottle? And you find a table in faucet. You say, okay, faucet and the bottle. And likely that's a sink, they see a sink. And they say, oh, that's likely to be a soap and they use for cleaning the hand. Likewise, we have a recent paper in ECCV trying to use the knowledge base external one to help us to parse the image understanding. So we can do a decent job in object detection, riding a bicycle event detection. But figure out actually these two people holding a hand while riding a bike. It's hard for computer vision. But if you consult with the knowledge base, it's a people hand close to each other, and then very likely they hold a hand. And this kind of a knowledge base can help us to correct the mistake. For example, if you apply one of the top computer vision work, the tail, it's the kite in the picture, might be misrecognized as a tail. But if you apply the external knowledge base like ConceptNet, you say, okay, usually kids play with a kite, holding the kite in their hand. Then you can correct the mistake. Likewise, another one here, without seeing the whole body of the car, you only see a piece of the windshield, and it's buried by all this other debris and other occlusion object here. We can figure out the windshield is on the car. So I'm trying to make a point that language model is great, and a lot of progress in computer vision and language is great, but we do need a common sense knowledge base for a lot of the tasks. We need a diverse set of a knowledge base, physical, spatial, temporal, causal behavior, and their recent work using crowdsourcing like visual comment in AI2 again, and that's a very good direction. How do we automatically discover them and represent them? And so later on, we can use for reasoning, for grounding, for complementing with a language model between different modality. So there's some early work in CMU for never-ending learning from a language side, and then on the image side called NEO, never-ending image learner, is trying to go that direction. I think that's very exciting. And recently, there's some DARPA program, like Commonsense program, or Kairos looking at event schema, understand the common sense relationship between different events. And that's a very exciting direction for me. So my answer is not a large model is not enough. We need much more, particularly in the common sense knowledge base.
Thank you very much, Shifu. All right, so let me introduce Lukasz Kaiser. Lukasz is our third panelist. He's a research scientist at Google Brain, and he's also working at CNRS. Lukasz is probably well known from his work on the transformer paper. He's a co-author of TensorFlow. And recently he has been working on efficient transformers in the Reformer project. So Lukasz, the floor is yours.
Thank you, Philippe. It's a great pleasure to be on this panel, and I'm very happy that there is such a wonderful and provocative topic. Maybe it shouldn't be very provocative because I mean, even a few years ago, right, language models were this kind of not very well-known thing that people in NLP did, and not many people outside cared very much. And of course, if you think of language models as such, right, as the mathematical definition modeling the next word in the sentence, so giving you probabilities of sentences as they come, in the narrow sense, they cannot be enough for much other than auto-completing on your keyboard, because what's the statistically most probable next word that I will say, and as David already said, this is not that useful. Nobody wants to say the most probable words, right? This would never be interesting. But in recent years, language models have grown to encompass like all of these sequence-to-sequence model things, right? When we can do translations, where you give them a lot of context, and then you tune them to output language, not the most probable language of the internet, but you take in training all of the knowledge of the internet as kind of the knowledge base or the context, as Shifu said, and then you fine-tune them on some specific data set which tells the language model actually what you want to produce. So you can fine-tune them to produce reasoning, right? You can fine-tune them to use this context to answer questions. You can fine-tune them for many things. And I think in this extended sense, the language model may cover a lot more than what we thought before. So let me be more specific. I think when you tell the language model to reason, and the language model is pre-trained like the recent large language models on all of the internet, and probably mixed with some programming data and whatever people find, they mix in books, nowadays more and more of multimodal data. So the language model's weights start comprising what Shifu was saying, this common sense knowledge base, except it's encoded in the weights. And then you tell it to reason, and it's not reasoning like David said, there's no formal language behind it, but it can reason just in English. It can give you reasons, why do you say this? It will tell you. And on top of this, you train it possibly with a loss that really verifies in some way, and that may involve some symbolic reasoner. You train it with a loss that verifies that what it's reasoning is actually a reasoning. Like recently, language models have been used for maths. There is the GPT-F for formal reasoning and maths, where that's exactly what's happening. You have a formal reasoner, but used not as a generator, but only to verify that the model is doing sensible things. So when you train language models like that, they become more than just these, predict the next word things. And in that setting, it's very hard to see why they would not be enough to be superbly useful. So they can really learn, like they can beautifully encompass knowledge bases, right? When they're trained on all of internet, they do as good a job on common sense reasoning as anything that AI has seen before, I would claim. And when you do fine tune them for reasoning and do give them this reinforcement, like maybe a language model should be able to write a query to Google or write a program, run it on a shell script, see the output, and then do this again. So when you start interacting with the environment with language model, you use ideas from reinforcement learning. I do think that's the point where they become enough, maybe not for full understanding of language. I think that may be a little bit too big of a statement, but at least for being useful on their own, for like solving tasks like maybe correcting bugs in our programs or answering queries from databases. So that's what I wanted to say, and I'm looking forward to the panel. And thank you for organizing it.
Great, thank you, Lukasz, for going in depth on the capabilities of language models and some like setting our expectations actually rather a bit more precisely. Okay, so let me introduce Tony Veal, who is an associate professor of computer science at the University College in Dublin. So I have to say that Tony Veal is definitely the scientist who has whose slides I think are the prettiest that I've ever seen. So I had first time the chance to see his presentation in Amsterdam several years ago, and I was really impressed. Of course, besides that, he has really some brilliant work on computational creativity and frame reasoning and frame manipulation. So Tony, the floor is yours.
Thank you, Philip. I'll just share my screen. Do a quick. Sorry. Okay, so as Philip said, I'm interested in creativity, specifically creative language, and the kind of language that really challenges common sense. And jokes in particular, though very creative metaphors, really try to break common sense in very interesting ways. And a very quick way to think about what they do is they create a deliberate friction and a race condition between system 1 and system 2. System 1 jumps to conclusions. System 2, which is much slower, but deeper and more analytical, comes in, mops up, and explains the apparent anomaly created or observed by system 1. Let me give you an example in terms of language models. I was using Google a few months ago. Very briefly, between the 2 lockdowns in Dublin, I was able to run out with my wife and see Tenet, this big tentpole movie, which, spoiler alert, is about time travel, in particular about characters who can reverse entropy to move back through time. So I was writing to a colleague to arrange a meeting, and I knew he wanted to see this movie as well. So I said, by the way, we went to see Tenet last night. this is a real head wrecker of a movie. Our brains are still bent out of shape, but we plan to see it again last week, so we'll understand it eventually. But this is what passes for humor in my group. This is my weak attempt at a joke. Now, Google, or the Smart Compose feature of Google, dutifully underlined last in blue to say there's something really wrong with your use of language here, or I suspect there's something really wrong with your use of language here. And if you click on that, it suggests next as the most likely word choice here. You should say, plan to see it again next week. Of course, in the context of a time travel movie, which I knew the recipient knew about too, last makes perfect sense. It's an example of irony. Irony, this really tendentious concept. And to be true, I actually meant last and next. I meant last in the pretense world of me being in this movie. And I meant next in the real world context of, I hope to see it again next week if the lockdown hasn't returned by then. Now, this is an example of where the statistical mechanism has detected an anomaly, but doesn't know what to make of the anomaly. It doesn't understand it as a creative use of language, and it doesn't have enough confidence to recognize it as an error. So it very moderately and unobtrusively marks it in blue, as if to say, this is on you, buddy. You figure out what's going on here. Let me give you another example of a better joke this time. So here, first off, let me give you the normative situation and the language model perspective on it. I say this is normative. The basis for this is still a bit outre. My wife caught me wearing her clothes, so I packed my things and left. Okay, so here's a classic staple of movies and sitcoms. The husband is caught doing something untoward. The wife gets upset and kicks him out, so he packs his things and goes to a hotel. You've seen it 100 times in some media or another. It's not a particularly funny situation, but if I replace my, which is a very high probability after so I packed in a language model context, we can get a joke. My wife caught me wearing her clothes, so I packed her things and left. Okay, so her now, still very low probability within the context of the language model, makes perfect sense in this humorous context of transvestitism, I guess. So one language model is enough to register surprise. It cannot give us an interpretation. The language model encodes a great amount of implicit common sense knowledge, which is why it's able to assign reasonable probabilities to word events, but it cannot jump out of itself and explain the surprise. If it could explain the surprise, it wouldn't be surprised. And for humor, for irony, for creative metaphor, we need surprise and the absence of surprise. We need surprise and explanation. We in fact need two language models, or we need two models at the very least. Maybe they can both be language models. I suspect that more like system 1 and 2, we'll have a language model and a symbolic model. Or maybe we'll have two language models and a symbolic model. One model to recognize the anomaly, one model to recognize that the anomaly is actually meaningful and not a mistake. Both of those models can be language models. And a third model to actually understand the anomaly, or if you like, to get the joke. The language model doesn't get the joke. Two language models can recognize the joke. It takes an extra model to get an understanding of the joke. And this is all borne out, of course, by EEG studies of event-related potentials, where we see that if you were to scan someone's electrical brain activity while they're reading a joke like that, or the normative alternative, you have this N400 spike, which signifies a tremendous amount of extra processing going on when you see the joke version. But we don't have an understanding here that this is an anomaly or it's a meaningful surprise. And we need another model. We need parallax. We need to be able to compare the outputs of models. One contains implicit common sense and the other contains explicit uncommon sense. And I think humor will be the ultimate challenge for language models. I think they will play a significant part in solving the humor problem, but they will not be a complete solution. Okay, that's my 2 cents worth. Thanks for listening.
Right. Thanks, thanks, Tony. So, right. So by now we have, we made a round of everyone presenting their views. So I would like to follow up with a question that I think is stemming from your opening statements, which is what sort of, so it seems like language models are not sufficient on their own, right? So perhaps we need 2 language models, or we need higher level structures. So can you comment on, so what would be the higher level structures that we should complement these language models with? And in relation to that, in which scenarios would we like to do this, right? So should we think about cases where, let's say, like, letting a language model deal with your bank statements, like, let's say, high risk cases, or should we think about specialized reasoning, for example, temporal reasoning, and so on? So yeah, so to recap, my question would be, what else do we need essentially? What higher level, higher order representations of knowledge do we need? And perhaps in which use cases is this most urgent and pressing to go for? Okay, I don't know, Dave, would you like to go first? Maybe we can retain the order.
Yeah, sure. Look, I mean, I think that in use cases that I deal with all the time, it is, it's about decision making. It's about providing explanations that are ultimately rational and people can take responsibility for. So there is a, we think of it, or we call it sort of a prior model, a prior structured model that represents how a domain works. And let's, assume that got there somehow, but that's a separate conversation. And so the idea is that, well, ultimately I want to be able to reason over that. And I wanted to provide structured explanations, justifications for whatever computation I'm doing over that formal model. Because the way we look at it, the fact that the model is formal has value, not unlike it's valuable when a human lays out their thinking as precisely as they can with regard to different standard inference mechanisms, so that you can all agree that you aligned on a common way of making inferences and so forth. So there's a fundamental value that, again, independent of machine intelligence, we humans partake in that. So with those advantages, we now take the language and we map into that structured representation and benefit from that. And when you're doing common sense stuff and you think about, well, you want to make predictions even in common sense scenarios, what do we take for granted there? Like, what are the structures we start building? We build maps, we build timelines, we have some knowledge of naive physics, of agency, of belief, meronomy. I mean, fundamental social concepts that we start trying to map that language into, so we can make those inferences. And to the point that was made earlier, the power that the generative language models have can extract information, especially with the fine tuning, because you could say, I'm looking for information in this form, in this structure. Is there anything implicit out there? And then before you make a decision on it, you interpret it. So you try to map it into that formal, structure. So you use the language model for what it's good for, and then you take that interpretive step, and then you get the structured you get out, from the structured representations what they're. Each domain there might be specialization of that, but that's where I think you get the benefit and you get that complementarity out of it. Now we can talk about how you build those structured models, but and how do you get efficiency there? But anyway, I think for doing the sorts of things that we're trying to do, those are the complementary structures you want.
Right. Okay. Thank you, David. Yeah. So in this slide there is also a comment on Rocket Chat that says, I want to challenge what Lucas said about the big LMs can be as good as dealing with database querying as anything else. Would you want your bank to be using a language model for your personal money and account, for your large companies, financial reporting, and etc. So I think I just want to read this out before, Lukasz, you basically go ahead.
Or should I go ahead? Or
yeah, either way. Okay, you can go ahead maybe. And yeah.
Sure. So I would love my bank to finally use a language model. I've just spent like 3 hours trying to wire money to some account, and there was a 0 missing at the front or something like this, trying to find the bank name somewhere. Which I typed in, but I missed 1 0 in some identifier. So I would love for this bank to have a language model to finally just do this for me. The language models make no mistakes copying digits when they're trained properly. They make 0 mistakes. They generalize. You need a proper architecture. It's not any transformer that you'll train that will be good. But they generalize to higher lengths nowadays. Like, these are results from recent years. You won't get it immediately with the standard transformer, but when you tune the architectures of language models, they're basically so good at simple math tasks like adding, copying digits, that you can trust them as well as you trust your computer. I mean, maybe at like very high lengths of digits, they will start making some mistakes probably, but you can get neural networks to be almost perfect, and I would totally trust them with my bank. As I say, it's not easy to train these models, and it's like out of distribution generalization and arithmetics have been weak points for the transformer, but this is because the transformer architecture was never designed to, like, I wouldn't say that the transformer architecture is the last word in language models. You should make better language models. You should make them generalize better. And you need to make them larger because, of course, a small model cannot have the context that's needed to recognize humor, to recognize common knowledge. But a large model can, same as I do. Right? Why do I recognize humor? Because I've seen similar statements. So a language model can, and like when you have the ability to fine-tune really large models, which unluckily very few people have, and that's why I work on efficient language models, because the size you need for them and the amount of hardware is simply not available to in many places. But I do believe that we can make them efficient. I do believe that sparse models in particular can be hundreds of times more efficient. And in some sense, when you do sparse neural networks, they start resembling symbolic methods in a sense. So it's like all of these things. When I say language model, I don't necessarily mean a deep neural network, right? It's a model that can have many components, and maybe it should take examples from a k-nearest neighbors with a knowledge bank rather than trying to pack everything in weights, right? So there is a lot in architecture and work, but in the end, it's a language model in the sense it gives you the probability of the next word. And I believe that, yes, well-done language models can do my bank account and actually would make my life easier if they did. But yes, how to train them, how to build them is a big question.
Okay, thank you, Lukasz. So Shifu or Tony, would you like to go ahead?
Sure. I think I have a bias. I'm working on media, looking at perception. So I love to see a language model connect to our perception world closely. Handling the bank account, maybe you don't need a robot or maybe a physical action, but having a robot or maybe an assistant at home taking care of your house or helping take care of your grandma or your grandpa, that kind of interaction is very important for us to make decisions not only in linguistically or semantically, but also physically. So I think if I have the luxury to choose which component to add, I will advocate for grounding. So learning the language model with grounding. grounding to physical perception, grounding to action control, grounding to navigation in the physical space. And that helps you not only to explain why you make a certain recognition or decision making, but also to plan what to do next. And that's, I think, is a wonderful area that I have not seen being addressed. And we look at a lot of common sense, maybe a knowledge base. And today they are curated by linguists or maybe by a language expert. But to discover what can be represented in this knowledge base or common sense repository, and coming back to help us to guide the future agent, physical robot interact with human, I think that could be another side benefit for us, not only a digital language model, could be a physical knowledge base can help us to control a robot.
Okay, thanks, Shifu. So yeah, so Tony, I was slightly surprised earlier that one of the solutions that you proposed were basically having two language models. I was thinking, what about your other work on, let's say, frames and metaphors? So is there space for those representations, and how would those be? Would they figure out the jokes that you tried to make in your email, for example?
I suspect that the way things are evolving, it's going to be language models all the way down. But the models will have different perspectives and will be arranged in complementary fashions to compensate for the weaknesses in each other, and in cases of humor, to maximize the weaknesses in each other. In old school AI, the systems were prone to two kinds of effect. The ELIZA effect, when a system is less smart than it appears to be, because we're quite generous as humans when we read a natural language output of a machine. And the tailspin effect, where a machine appears to be less complicated than it is because it exposes its errors in what it outputs. And I have a friend in computational creativity who built a recipe generation system, and they uploaded the recipes onto foodnetwork.com automatically to get feedback from people without telling them that they were machine generated. And the output was full of tailspin errors. The recipes would say things like, add 0.26795 cups of chopped onion to the stew. People would immediately go, what? That's too precise. Or it would say things like, add a dash of green beans. People think, green beans don't come in dashes. A language model can easily overcome those problems because they will use the phraseology and the terminology of the recipes on which they're learned from. But the interesting thing about that particular experiment was that the people on foodnetwork.com didn't say, oh my God, these are computer generated, we've been fooled. They immediately downvoted the recipes because they thought they were generated by a human who was mocking the typical foodnetwork.com participant and their finicky approach to quantities and so forth. So there's humor of an unexpected kind and there's humor of an expected kind. And figuring out which is which is really a matter of authentication and trust, which also relates to the banking issue. It's one thing to get a language model to figure out which bank you really want to write your money to, and to trust that it won't send it to a Colombian drug dealer instead of to the IRS. But you want to be able to validate the system's actions based on a language model with something that isn't a language model, I think. For purposes of creative computation, where people expect the output to be weird and wonderful, we don't need validation. But for things that are part of our regular financial or medical lives, we would need some kind of non-language model regulation of the output or authentication to give the system a level of trust.
Right. So relating, so I think one point that keeps coming up is, matters like, trust, or, do we need to look into more than text? And this relates to the next question that I would like to pose, which is, how do we know that basically, how do we know whether the language models are enough, right? So basically the question of evaluation that should tell us something about trust. there was also a lot of discussion yesterday at the neurosymbolic panel on aspects, for example, of validation of language, of architectures, of neurosymbolic or whatever, or any architectures that we build. So basically the question would be, what is the right way to evaluate here? Like, I feel like many of the, for example, common sense evaluation benchmarks that we work with are text only, right? And I think Shifu, for example, hinted at this aspect of that maybe we need to do more, maybe we need to look at grounding. And also in the audience, Howie Young talked about, simulation. So do we need to have our algorithms or agents be do something that's a bit more dynamic, right? So either be in an environment of that sort, be sort of embodied, or I don't know, do we also need to look into more strict forms of validation? I don't know. So what would be your thoughts? And whoever wants can go first.
I can tell you that, when we started thinking about this, we got very interested in what you were saying, this notion of testing, systems. It's expensive, unfortunately, but testing systems more interactively and in context, looking at having systems create representations. So when we even interpret simple narratives, we have the system build timelines and build maps, build causal graphs and state transitions and things like that. So, and it's interesting because when even when you look at students doing reading comprehension, and if you look at people doing cliff notes, they summarize stuff. It's like, tell me what all the characters are, tell me what the events are, draw me a map of what happened, draw me a timeline of what happened, and ultimately, are these things interactive in nature? Is the system demonstrating that it has access to essentially the models that cause the language to occur? And anyway, that is a harder way to evaluate these things, but may give us more confidence that they're developing the understanding we expect them to have. They could make predictions similar to the way that in ways that would give us confidence. I mean, I have to say though, in the end, like, we convince each other all the time that we know what we're talking about just by creating more and more language strings. So I don't know that ultimately that's necessary, but in the end, you have to know whether or not you're convincing people that you have good answers and the answers are well justified. And that ultimately, just like we do, they always go back to the human-human interaction as a basis for this. Is, have you convinced me of an answer? Have you convinced me that you're a trustworthy expert to a point where you've given me enough information that I'm willing to take responsibility for the decision? And that's sort of ultimately the bar. And in human-to-human interactions, that's realized through that interactive, dialogue in many ways.
So if I can follow up, I really like what David said about interactivity. I think a lot of language models today are evaluated in a one-shot fashion. So you do a QA and you say, do you get this correct or wrong? But if you start to dig deeper or dive in, you say, can I ask follow-up question? If I make a mistake, if I rectify my question or may clarify, does the system respond with the correct understanding? So I think that interactive dialogue or collaboration between human and agent or robot and human, or in a sequence of interaction with a common goal, and then the machine or language model can behave in a coherent way. So you don't just change your answer rapidly when you rephrase the same question. That's what we're seeing in some of the benchmark today. It's not stable. So I think that kind of cohesion and interactivity and dialogue or physical collaboration is key. And I have not seen that one yet.
It seems like we're veering dangerously close to the Turing test when you put too much emphasis on dialogue and interactivity and the idea of catching the system out.
I mean, that's a good thing, right?
Well,
I mean, it's a good. What I mean by that is, it's sort of a good. It's showing us that we're challenged, right? We're getting there, right? I mean, we're getting to a point that it's not so easy, to distinguish, and it forces us to start asking this question: what do we want out of AI? How do so it's making it interesting. I mean, that's how I'm taking that. It's making it interesting.
I would say that I 100% agree here that interactivity as just having some environment, may it be a robot that runs in the world, or may it be dialogue with other people. Environments can take many forms, but having this interaction where there is an external reward, be it by other people, users, be it by a robot that just, I think making language models interactive is, to me, the single most important thing in as the next step for language models. And how exactly, right? Should they be grounded in a physical world? Should they be in a simulation? Should we focus on dialogue? With dialogue, it's a little bit hard, as we say, to judge what is good, what is bad. There's not easily an automated judgment, but interactivity is, to me, the key. And I think we're not as far as we sometimes think, because before the Turing test, for a robot, the first judgment will be, does it drive into a wall and crash? And if we start interacting with language models, we're at least a little bit on this stage still. Like maybe they'll do 3 turns correctly, but then they kind of drive into a wall and crash in language. They're not as good, and probably because we're not training them to, right? And so one thing people are trying now is to generate small programs, right? You write a text and the model is supposed to generate a program that computes the answer. There is a MathQA data set for, like trivial questions like, from town A to town B, it takes 2 hours. From B to C, it takes 3. How long does it take from A to C if you go through B? Or things like that. Just add 2 numbers and let's get somewhere there. But if you generate the operations token by token, half of the time you get something that doesn't compile at all. That's what I mean by driving into the wall. And on the other hand, it's not surprising because the data sets are tiny, the models are not trained on them. So I feel like this is the research area where we haven't really figured out yet how to do language models inside an environment, how to do interactive language models. We know very well how to train them on supervised data. We can train them on all of internet, great, but they can't really interact because interactions are somehow different, right? They are grounded, they have context, have all of the interesting features that we seem to be lacking. But how do we train? And there is this whole area of reinforcement learning that says they know the answers, but it's very rarely used with language models. And when you try, it's really hard to make it work, I feel. Or maybe, maybe there are some people who know how to make it work. I just don't yet. But I want to say that, yes, interactive language models may actually be great. But yes, we are not very far in them yet.
So Tony, I don't want to put you on the spot here, but I was just wondering because it seems like it seemed like you were implying that there is a downside to this interactivity in evaluation. So is that the case? Like, is there a potential downside of going out in the wild and just openly evaluating language models or any architectures that we build? Is there a situation or aspect of intelligence that we perhaps don't want to do, that we don't want to evaluate in that way immediately?
No, I agree that interactivity in a meaningful context that isn't artificial, some kind of American Idol X Factor style nonsense is very meaningful. I just hate the Turing test. It's been bastardized in popular culture to the extent that I don't think it's properly understood anymore. It's abused horribly.
That's a different problem. I agree with.
Yes, people in the media are always asking, "Can we do a Turing test for this? Can we get the computer to generate paintings and compare them to human paintings and see which ones fool the audience?" And it's a terrible race to the bottom. Simultaneously, it's a race to the surface, which I guess this panel is about. In many respects, language models are a race to the surface to control the surfaces of language while doing an end run around the understanding mechanisms that sit at the bottom of human language. And a fascination with Turing test style environments just encourages people to race faster to the surface and to do this end run around the bits that we think are missing and that we're discussing here. But longitudinal studies or complex studies where people interact with a language model technology over time, the equivalent of a relationship versus a one-night stand with a model, to see, is this really doing what I think it's doing, or is it an ELIZA effect? You play with the model long enough so that it exposes its tailspin effects eventually, if it is as shallow as you think it is, or it exposes the morality of the decisions it's making. Is it saying stupid things 1 out of 10 times? Or if I use it long enough, is it something that I'd be happy to use in my banking application? I think those are very valid testing situations.
Right. So, so one niche that this is probably the last question, given that we only have 1 hour for the panel. But I feel like one niche that is connecting all of the panelists is, you know, some interest in generalization. So I know that, for example, you know, for example, I know Lukáš has this work on generalizing to long tail entities or events. And then Shifu has work on, you know, how do you understand reference in images? And, you know, there is the work on jokes, which I assume require a tremendous, you know, some sort of very strong way to generalize and sort of relate context, relate concepts in cases that you haven't, you know, connected them before. And, you know, I know that also some of the examples that Dave was showing on their Commonsense work require this very open-ended generalization and reasoning, which I guess is also triggered by, you know, the work in Watson, where, you know, it was this just generalization is just really a very big challenge, I believe, of AI. And, you know, certainly we can see language models generalize in some sort of way, right? Whatever prompt we give them, they are able to give us something back. So that's already something. But generalization in a matter of, you know, drawing analogies between situations, so somehow understanding the world at a deeper level, I don't think that we are there. So my question would be, you know, how do we improve this aspect?
Maybe someone else should go first this time.
I can give it a shot. So generalization definitely is a very important issue, and we all dream that we can have a lot of training data from internet or so-called self-supervised learning between video and caption or image, and then we can magically learn the mapping between different concepts, even between different modality. But when you try to test on a new domain or new task, there are two issues, right? Whether is the performance still hold. The second is if you have a new vocabulary or a new concept, how do you handle it? How do you know you're missing something? And we had a program in DARPA called GAILA. It's trying to recognize object or event with very few sample. We demonstrate very good, robust performance, but at the end, we cannot expand. So I think my answer is coming back to the final structure. Are we learning something that there's a structure there we can understand, we can explain, and we can use the structure to generalize to the new concept, a new phenomenon we have not seen. For example, coming back to my field on object recognition in computer vision, I can properly recognize tens of thousands of object classes. But when I go to a new field, medical, or maybe COVID-19, or maybe climate science, those are new kind of objects I have never seen before. So how do I handle that? And so is there a way in the previous training or large language model, I can abstract them into a distinct abstract of either its attributes or structure or some kind of a description of a relationship between object or real world, so that I can quickly apply to understand the new domain. So that structure abstraction from language model, I think will be very useful for generalization, and which I think is still open challenge right now.
I think when you generate with language, as opposed to answering questions, say, in a constrained fashion, you're dealing with very rich semiotic possibilities. And we want our machines to generalize, but the human audience already does a tremendous amount of overgeneralization in some cases. Myself and a student had a paper recently where one of the reviewers said, please replace the example video you provided. We had a video of 2 robots performing a computer-generated story. And one robot was taking the role of Donald, and the other robot was taking the role of Hillary. And they have a whirlwind romance. And the narrator, which was an Alexa device, says, Hillary fell in love with Donald because he was rich and powerful. This was an example of the symbolic storyteller coming up with the idea that Hillary should fall in love with Donald, and then retrospectively looking in the knowledge base to find reasons why someone would love this person called Donald. And it found 2 properties, rich and powerful. And the reviewer said, this is terribly sexist. We don't want you linking this video in the paper. Either remove it completely or provide a link to a different video that isn't sexist. Now, we're talking about a fictional character falling in love with another fictional character, but this was taken as somehow indicative of the entire culture and of the entire world of the storytelling system. In another story, a female character, the story generated a situation where a female character cooked a meal for a male character. And when we were showing this example, someone in the audience said, that's sexist, having the woman do the cooking. Now, under normal circumstances, in a long interaction with a dialogue system, you could figure out if a system had biases like that. But people are so willing to infer generalities in a one-shot fashion that when we make our systems generalize, we have to be equally aware of the human audience's willingness to generalize at the same time and to somehow deal with the perception of offense where none is intended and none was explicitly generated.
So I may take a shot. I absolutely agree. I mean, I think it's apparent what Tony says, that humans do overgeneralize immensely. I've been spending this pandemic time with my 1-year-old daughter, and the capability of generalization that she has is unmatched clearly by any machine model we can produce. And yes, the overgeneralization can cause problems, but it is also the magic of learning from very little data to do amazing things, right? That babies can do at very early age and humans later as well. And we have certainly not understood or even replicated these abilities in full, but what it seems to show, at least the language model research that we've done in the recent years, which is, it's just a few years. So in research time, it's not that much, but it looks like larger models generalize better, and it looks like the architectures matter. Like, for example, attention architectures do generalize from fewer data than RNNs in some sense. And probably there will be better architectures that we'll find maybe by analyzing the brain as well, that may generalize even better. The shocking thing to me was that larger models, which are hugely over-parameterized for the data, actually generalize better. And this is what people study recently. And it seems to hold. It doesn't seem like just a fluke. We don't really, I think, understand yet what's regularizing it. But I do believe that we're making these first tiny steps in actually understanding what may be happening. And yes, as a side product, we may one day create models that will overgeneralize as badly as we humans do, but maybe that's actually a success in terms of research.
Yeah, I mean, my reaction to that was, I think, just stepping back and when I look at the power of machine learning and even what we're witnessing using language models in practice, and I don't think the field has ever been this good at generalizing. I mean, in some sense, that's one of the most powerful inferences. Of course, you could under or overgeneralize, but it's never been this good in many ways. I think the questions that were raised, the challenges that were raised are right. Maybe in summary is, what are you generalizing to? And how does that ultimately get decided is sort of an interesting problem that you have. I think that, when we approach that, we essentially say, what's your starting point? What is your prior model? I think in the case of the trial, the prior model, is you don't have a lot of information, so it's extremely sparse, very general, and you end up overgeneralizing. So, what are you preconditioning for when you target that generalization? I think is an interesting aspect of it, but I think it's very promising where we are today.
Awesome. Yeah, so we are actually running overtime at this point. So I would like to thank everyone for participating. I like to say that I really liked Luka's stand. So you stand, you were able to stand on the side of language models are more or less enough, so or at least they can do a lot. We just have to look into how to have better ways to train them, or maybe we should look at language models not as the language models that we have today, but rather as a more of a family or more of an idea of approaches. So I appreciate your stance there. I liked Shifu's insights from this multimodal perspective, from the perspective that we have to look at language models and at intelligence not only from the perspective of having the language model by itself, but we should actually look this in some more simulated environment. And I feel like here also I feel like here is also where Dave was stating that we have to look into how children learn, how children do this, what are the priors that we go for, and in general just what are our goals of the tasks that we're looking at. And I like Dave's optimism, saying that even though we have still probably a long way to go, we are making really good progress, and we should take the different ingredients that we have. So maybe good language models, but also combine them in much richer infrastructure and have that. And I know that Dave is working on a bunch of projects along this way right now. And finally, I really appreciated Tony's challenging of some commonly accepted notions. So when I asked about generalization, I kind of made an assumption that this is a desired property, and I really like your basic challenging of these notions of that I kind of had as starting points. And similarly, I really appreciate your input from your work on metaphors and applying this language model in sort of day-to-day situations, and where do they go wrong. So those are just some of the takeaways that I have from today's discussion. I hope I didn't misrepresent anyone. And again, I thank you all for participating in the panel. We will wrap up here with this part 2 of the workshop. We will resume in 14 minutes with the keynote by Josh Tannenbaum. And after that, we have set paper session number 3 with 3 more papers that we'll talk about.
Thank you, Philip.
Thank you.
Thank you.
Thanks very much.
Thank you.
Thank you all. Bye.
Thanks.
So welcome back. We're up to our next invited speaker, and it's a great pleasure for me to introduce our next speaker. Our next speaker is Josh Tenenbaum, and he's a professor of cognitive science and computation in the Department of Brain and Cognitive Sciences at MIT. And he's also a member of CSAIL, the Computer Science and AI Lab at MIT. And he's inherently a multidisciplinary researcher working in the intersection of computational models and behavioral experiments with the goal of improving understanding of human learning, reasoning, and perception. He's been recognized with more awards than I could possibly go over, but a few prestigious fellowships from the MacArthur Foundation, from the Society for Experimental Psychologists, and the Cognitive Science Society. And he's going to talk to us about reverse engineering the core of human common sense. So with that, I'll yield to Josh.
Okay, hi, can you guys hear me okay?
Yes, we can hear you.
Okay.
And are you going to share a screen?
Yes, I'm going to do that here. Second.
And lots of good books in the background.
Yeah. Let me make sure I do this right. Okay. Oops, a second here.
Okay, we can see the screen, and you might want to go into present mode.
Yeah, I'm just going to put this into this mode here. So now, okay, you guys can just see my slides normally now, right?
Perfect. Yep.
Great. Okay. So thanks a lot for inviting me to this workshop, and especially coming after the last panel, because there's it's a great setup for the issues I'm going to be talking about and the issues that really, along with a lot of you, I've been thinking about for quite a long time. So let's start off with the question of what is common sense. The classic definition, certainly the one I learned when I was getting into the field, is something like this. It's heavily bound up with language, as most of the people here have been working on. It's not the only thing you could mean by common sense, but certainly one thing you could mean is it's all the background knowledge you need to understand and use everyday natural language in all the everyday ways human beings do, whether it's reading the newspaper or reading Wikipedia or whatever it is. Okay. If that's what you mean by common sense, then the question is, then how are you going to get it? And the challenge is that most of this knowledge is, though it's bound up with language, it's just not something that anybody ever talks about. The whole point is that it's what you need to understand in order to talk, so you don't even need to say it. And how are we going to learn this? Well, there's been different approaches, of course, but one that is in the background of, or in the foreground really, of this workshop and the discussion is looking at some approach to statistical learning of the implicit structure of how language is used. And as models for statistical language models have gotten larger and larger scale, this has seemed increasingly promising, that even though the models aren't in any way particularly built to have common sense, just by learning the implicit distributional structure of how language is used, effectively that definition of common sense will pop out or emerge. And then the question we're all asking ourselves is this all we need? Do we just need to keep scaling this up? I'm not going to make a strong argument that that isn't going to work ultimately. I honestly don't think it is. Instead, I'm going to talk about an alternative answer that I think is at least as promising. It's harder in some ways, but much easier in other ways. And it's the approach that we and other people here, including like Dave Ferrucci, I think we're broadly in agreement of how to, what we should be doing. And we might just differ only in small ways on how we might do it. Maybe not even that much. So this is to look to the way humans actually come to common sense. And that means looking at how humans come to language. So let's try to learn not the implicit distributional structure of how language is used, but the conceptual structure underlying human language and how we learn it. And then in so doing, learn common sense the way humans do. Now it's harder because you have to know something about how humans do. But in addition to the great strides that engineering has made in the last few years and the last few decades, the basic science of human cognitive development has also made great strides. And the work that we've been doing on the computational modeling of cognition side is heavily influenced, informed by, and in interaction with the science of infant cognition and early childhood learning. And I think one way to sum up the insights here, which if you want to read more about this in an AI context, I would refer you to the BBS article by Brendan Lake, Tomer Ullman, Sam Gershman, and myself on this idea, is that building on insights of many researchers, we're especially influenced by our colleague Elizabeth Spelke, as are many others in AI these days, but Renee Bayer-Jean, many others, Gergely Chibra, many others who have studied cognition in very young babies. So babies younger than 1 year who basically don't know any language, certainly aren't producing language, and barely know a few words. But what they've uncovered is that from about as early as you can look in studies that maybe start from 2 and 3 month olds, human thought is already structured around a basic understanding of physical objects and substances, intentional agents, and their interactions. And you could think of these as intuitive theories of physics, of objects and their dynamics, some kind of intuitive analogs of forces and masses, and intuitive psychology, where agents have behavior that's caused by their desires, their beliefs, their plans. This is a notion of common sense, what we call the common sense core, that I think is at the heart of what I think is this at least as promising route. Okay, because we know from our science that some version of this is there as early as you can look, and probably built in genetically as the result of just the ways our brains and our bodies are built. It's shared in many ways with other species, but it's really enriched and extended massively in humans, both as the basis of probably distinctive human capacities that lead to language, and then even more so in really interesting feedback and bootstrapping loops. Once we have language, once language comes into the picture, these are the things we talk about. And thus, when we talk to each other, we learn more and more about the physics of objects and the mental states of other people. And then we learn more and more about concepts that let us learn about things that go even beyond these core domains. Okay, so that's in a sense our best thesis, I think, on where we start. But if you really want to look at this human developmental route to common sense, right, you have to say, okay, well, first, how are we going to reverse engineer that? And then how do we go beyond that? So a lot of what I'm going to focus on here and what our group has been focusing on is how do we capture in the form of some kind of models of the intuitive physics that you might see like in this 1.5-year-old playing with blocks or stacking up cups, right? So we're trying to say, what is the model of the physical world, of the world state that underlies the images that he's seeing and the dynamics of the objects that, the state transition dynamics, the physics, if you like, that he can use to predict what's going to fall over, what's going to happen when he picks things up. It's not the same, being able to predict is not the same as planning, and that's a separate hard problem. But as a first step, being able to know what might happen and if you don't do anything, and what might happen if you do this or that, that's, we think, the basis of our ability to grasp the physical world, literally to grasp things, and then to make plans. Or intuitive psychology, like this from the famous studies from Felix Wernicke and Michael Tomasello here. Ask yourself what's going on inside the head of another 1.5-year-old, the kid in the back who's watching the scene, who sees somebody doing something that they've never seen before, and in some sense literally is able to read his mind to figure out something about what he's doing and why and how to help. And you can see that by what happens when the adult stands to the side after, just watch it again and think through online what's, put yourself in the perspective, if you like, of that child. You see this guy banging the books into the cabinet and you want to know, well, what is he doing and why? And then now he stops, and being a naturally helpful sort, what do you do? Well, if you figured out he seems to be wanting to have some goal that has to do with getting inside that cabinet, you open it up, and then you see the shelf, you step back, you look at what he's holding, what he's doing. You can see from the way, oops, I'm going to turn off these very cute but slightly distracting videos. You can see from the way, like at this key point, watch how he steps back, makes eye contact, and then looks down to the hands. And that's, an outward correlate of what we think is going on inside the head of intention understanding, and then even forming some potential joint plan. If I've helped you out appropriately, are you going to do what I expect? So we're building models of the sort that I'm sketching out here, which are basically sophisticated kinds of probabilistic generative models of the physical world and of agents' behavior that we think underlie these core common sense abilities. But that's just the first stage, and it's mostly what I'm going to talk about here, but I just want it to be clear that if you look at the full swath of human cognitive development, these are the main kinds of achievements maybe of the first year or so. But then after that, let's say between 1.5 and 3, the main achievement is using that knowledge to learn language. That's the most important thing that, say, any 2- and 3-year-old is learning. And then once you have language and the basic, enough syntax and semantics and pragmatic understanding of how language is used, then you can use language to learn everything else, whether it's by reading or talking to people, and thereby access the full sweep of human knowledge that builds culturally across generations. So this, I think, is the route to the, human intelligence in very broad strokes, and the human-like route to building machine common sense. But that's, to us, again, it's going to start with the starting point. Now, you could be asking, and again, this is what many of people in I think this community have been exploring, and in some of my own research with AI colleagues, it's not that I don't think this is irrelevant, but you could be asking, why not, why not take the large-scale statistical approach and just scale it up beyond language to all these things, perception, physics, agents. If that has been promising in language, and we also know how promising statistical models in computer vision have been done recently, maybe that's what we need. Do we really need to understand what children are doing, or can we just build like multimodal large-scale models? So in the BBS article, this was 2017, which is like ancient history and modern AI terms. We talked about how attempts to do image captioning, while they can be quite successful within the domain of data sets that they're trained on, when you unleash them in the wild, if you like. So here's a state-of-the-art image caption system from just a couple of years ago, deployed on sort of interesting photographs. What they describe is not unrelated to what you see, but really misses the point. And we think, again, that's because these systems that just as many of us believe the statistical structure of language doesn't just give you the concepts, the statistical structure of how you relate one complex information source, language, to another, images, the challenge in some sense is even harder there to expect generalizable conceptual structure. But there have been exciting recent developments, and on the minds of many of us, of course, there's GPT-3, 2.3, there's the latest from OpenAI, that I'm sure everybody here has seen, DALL-E, for example, which is, as far as I know, only described in a very informative blog post so far. So I don't really, none of us know all the details or have had a lot of data, but it's very intriguing how much progress has been made in terms of compositional image generation from text, like avocado chairs or sketches of cats and so on. At the same time, as I'm sure like many of you, have done, I've studied just what you can get from the sort of the templates that you can interact with on the OpenAI blog for DALL-E. And it's really interesting to see, like, what are some of the things that the system does very well, like these examples here, and other things that, it does much more poorly, to the point of really seeming like, well, is that, are you really understanding language and scenes in the kinds of common sense terms that we see those young babies already starting to do? So to take one notable example, here are a couple of sets of scenes that DALL-E generates when you give it this prompt, more or less. So one prompt is, and these are two different scenes and two prompts. One is a stack of 3 cubes. A blue cube is on top, sitting on a green cube is in the middle, sitting on a red cube. The red cube is on the bottom. And that's a particular stylized way that I guess they wanted to just describe what we might just describe more simply as, 3 cubes, a blue cube on a green cube, and then on a green cube on top of a red cube or something. So consider that language versus the one on the bottom there, in which we've just swapped the role of red and blue. And what you can see on top are scenes that were generated from these two prompts. And the question for you is, which is which? Now, again, the most striking thing here might be, wow, these are pretty photorealistic images of red, green, and blue cubes. And there's no doubt that that's really impressive. But it's pretty hard to see either of these capturing, the actual structure of blue on green on red or red on green on blue. At least to me, it doesn't immediately pop out which is which, because whichever scenes you look at, sometimes there's 3 cubes, sometimes there's 4, sometimes there's 5 or 17. And, sometimes there's a clear set of 3 things like a blue on a red on a green, but other times there's a red on a green or a green on a red on blue. There's no real consistency here. And I don't know if anybody has a clear sense which is which. We could do, if this was interactive, I'd have you raise your hands and vote, but I think it's pretty clear that it's not that easy to tell. I think the correct answer is that, which is it even, I forget. I think the one on the left is the red cube on top, and the one on the right is the blue cube on top. And there's a slight preponderance of more red cubes on the left on top. But in no case is it actually fitting the scene description perfectly. Now, this is a kind of compositionality, multiple objects in spatial relationships with each other, that, you know, is the sort of thing that people in formal semantics have studied for a long time. This is like Bloch's world. This is supposed to be the easy kind of compositionality compared to like avocado chairs and drawings of cats and a baby daikon radish in a tutu walking a dog. So again, we scratch our head and puzzle at this and want to understand. And I'm not saying I understand. I'm not sure whether anybody understands what these models really can do and what their limits are. But again, the fact that some kinds of compositional language-driven image generation work so well and others work so puzzlingly poorly suggests at least fundamental gaps between what these models are trying to do, what kind of structure they're built to capture, and the structure of how humans understand scenes and talk about them, and the basic common sense representations that link those things up. So I just want to put that out there as some motivation to pursue an alternative approach, in addition to seeing where this really just large scale engineering route is going to take us. Okay, so the thesis is, if we want to talk about scenes or anything in the world, really, we'll start with scenes. We first need to be able to understand scenes as people do, and then ground language in that. That is, see grounded language not as just statistical links between word streams and pixels or motor commands, but as links between language and the conceptual representations that underlie our perception and our action in the world. I'll just give one other example, you know, again, because it's one of my favorite recent examples to talk about the challenge of generalization, and especially in light of the last panel, where there's a lot of really interesting questions like, do people generalize too much? Are remarkable features of or capacities for generalization? What are our models doing? Where are they going? And I'll give you one of my favorite challenges in common sense scene understanding, what I think of as a fundamental challenge in generalization that reflects the way human scene understanding can generalize to new environments, not just new objects, but new environments that are in some important ways vastly different from our training environments, with essentially no retraining or fine tuning, which means we as humans just see the structure in these scenes out of the box. Okay. And to illustrate, I want to consider basketball. Okay, so I'm not a basketball expert. I think it's fun. I played it a few times, and I'm sure in this room there's a range of basketball abilities and familiarities, some of which far exceed mine. Okay, but I think all of us can look at a scene like this, which is a typical basketball game, viewed from a typical viewpoint that you might have if you've sat at courtside and never played in the game. And you know what's going on because you know something about basketball. There's players, there's a ball, there's a goal. One person's trying to get the ball in the goal, another person's trying to block it. There's some other people interested in the activity and so on. Okay, the person's jumping up in the air. All right. But whatever you've learned about basketball from experiences like this, it generalizes to very different views on the scene and very different scenes even. So consider this as a shot of a basketball game, a professional NBA game, from a camera that's right next to the rim on the backboard. This is a viewpoint that none of us have ever actually been in. And you know, maybe you've seen this in an NBA camera, but the first time you see this, you have no trouble generalizing whatever you got from the first scene to this one, right? Even though it's a totally different viewpoint, you still recognize that basically the same thing is going on: the basket, the ball, the players, person trying to get it in, another person trying to block them, and so on. This kind of generalization is not something that just strictly learning-based computer vision systems do automatically or really at all, but it suggests having the right kinds of scene representations that are not just emergent from statistical structure. Okay, but the problem of generalization is much more severe than this. Consider video games like this. This is a sort of NBA sports video game, not the most contemporary one, not the best graphics, sort of, you know, okay graphics by today's standards. Has some things that are sort of unrealistic, like that circle of white arrows, which reflects the player control. Not, you know, that's just there for the video game. But you see this, and you don't have any problem seeing exactly the same thing, even though the pixels are different. You know, this is exactly the sort of thing that conventional computer vision would have trouble with. And that white circle, you know, could have all sorts of adversarial effects. You know, instead of being a person, this could now suddenly become a giraffe or something like that because of that white circle. Or maybe it's a skateboard or a giraffe on a skateboard. But let's keep going. Let's consider even, you know, less realistic scenes, like, for example, this one here, in which you have a player making a slam dunk. The graphics are even worse, lower quality. We can still see what's going on. And it's also unrealistic, right? This guy is jumping up far higher than any basketball player or any mortal human could ever jump up to do that slam dunk. So, but we still recognize what's going on. And we can recognize, even though it's this very unrealistic kind of jump, we still recognize it as a jump and an unrealistic one. We understand what's unrealistic about the height that the height that he's attaining. Okay, or consider, for example, this is a Minecraft scene of basketball, and even though the graphics again are terrible in some sense, they're these blocky, Lego type graphics, we still have no trouble, whatever we know about basketball, generalizing the people, the basket, the ball, the teams, and so on. Or consider this old school Atari game. This is a one-on-one Dr. J versus Larry Bird game. So it's one-on-one, it's a little bit different. Again, the graphics are even more terrible, yet we have no problem seeing the same thing. And even more, and this is my last image here, the actual original classic Atari, the 2600, the one that deep reinforcement learning has made such progress on. This is the original Atari 2600 basketball game. It's hard to imagine worse graphics than this by today's standards, and yet it's really not any different as far as common sense scene understanding. If you have had any familiarity with basketball at all, or even probably if you've just seen one game in the first setting, the first setting on the left, the most realistic standard setting, it would generalize just as well here. You'd see the baskets, the ball, the people, the competition, and so on. Okay. So what's going on? What is the structure of how humans represent the world, the places, the objects, the agents, the physics, the goals, the plans that spans this entire range, right? And that can start from this kind of experience and this experience only and handle this kind of generalization. We don't know the answer, all right? But to me, this is just another way into the same challenge and the same topic of common sense, okay? I think if we can solve this problem, that's going to be the first stage of solving the problem of how we really get common sense through language the human way. And that starts with reverse engineering these kind of concepts here. So how do we capture intuitive physics or intuitive psychology in engineering terms? Well, the first step is to have modeling languages which are up to the task, which means they have to be able to capture the representational structure of objects and agents and the causal structure of their interactions and the computational structure, because especially once we have agents in the picture and we're trying to understand other people's minds and plans, we're understanding systems which are themselves computing. So to do this, we've been very interested in a class of models, really AI programming, modeling, inference, and programming languages known as probabilistic programs or probabilistic programming languages. And for those of you who aren't familiar with probabilistic programs, you can think of them as a toolkit that integrates some of the best ideas of multiple generations of AI and cognitive science research. In the same way that the word neural network has come to mean something which is mostly detached from the original notion of the idea, which was taking a motif of a neuron in cortex and then scaling up the network motifs of how that thing works. And now it's come to stand in for something like end-to-end differentiable programming. Probabilistic programs started, depending on how you count, maybe 2 decades ago, more seriously, maybe in their modern form, 10, 15 years ago, but started as the idea of taking motifs from probabilistic inference in graphical models and scaling them up in various engineering ways. And what they've become at this point is what we might call modern probabilistic programming. And I'm listing here on the right a number of probabilistic programming languages, including the ones in bold, all fit what I'm calling the modern category, which is that they're all actually built on top of modern deep learning languages like TensorFlow and PyTorch. So in some sense, they start with what you can do with neural networks, but then they build powerful tools for symbolic representation, so symbolic languages for model building, and that means representing and reasoning with abstract knowledge. So models which are not just structured architecturally like a fixed network structure, but which have programming language capacities to them, data structures and algorithms. And then probabilistic inference, that's where the probabilistic part comes in. So the models that we're building think of them as generative models, especially most of these programming languages have either through a functional or a declarative nature, have a fundamentally causal semantics to them, okay? Which means they describe the processes in the world, like how objects interact or how agents plan and then interact with objects. So in the spirit of causally structured generative models like Bayesian networks, we're building We think of the mental models in our heads as these kinds of causal generative models about what's going on in the world. But then by wrapping those inside these probabilistic programming languages, we can do inference from sparse patterns of uncertain data, working backwards from the observed effects of the underlying causes in the world to infer what's really out there, and to have models that have the right kind of representational structure. This is where the symbolic part's in, to really capture a world of objects and agents and their interactions and their thoughts. And using neural networks for what they're good for, which in this view is not really fundamentally causal reasoning or abstract knowledge representation, but pattern recognition, function approximation, which is going to be very useful for doing fast inference with these models, extending them to cases where we don't really have a causal understanding, but still need to have predictive expectations, and so on. I think it's that full toolkit of ideas that is now enabled by these modern probabilistic programming languages that can really help us deliver on this reverse engineering common sense vision. If you want a pretty easy introduction to these kinds of models, check out the probmods.org webbook, which is an interactive webbook that was mostly written by Noah Goodman, a colleague and collaborator of mine. I and a number of others contributed also. And it has a lot of cool interactive code boxes, so you can really, if you want to learn about probabilistic programs, you can explore them interactively as well as pedagogically. I would also refer you to the last of the languages on this list called Gen, which was developed by Marco Cusimano-Towner and Vikash Mansinga at MIT in the probabilistic computing group that Mansinga runs, which is, of all the current modern PPLs, the one that's closest to the sort of set of modeling and inference capacities that we're trying to use in the work that we're doing here. And we increasingly do a lot of collaborative work with Vikash and Marco and others to try to take the ideas I'm talking about here and scale them up in various engineering ways. Another key idea, in a sense, the kind of probabilistic programs that we're interested in working with here is inspired by game engine programs. We call this the game engine in the head because we want to distinguish it from other important ways that people are using game engine technology in learning-based AI at this point. So what do we mean by the game engine in the head? This is the idea that the kinds of programs that are in modern game engines for very fast ways of simulating approximately graphics, the way light bounces off the surfaces of objects to render images, or physics engines, the way objects might bounce or collide or slide when they're just moving on their own, or when somebody picks them up or throws them or drops them, the way water might splash when you drop something heavy into it, so that models the interactions of the particles of water as well as the solid object. These, I should also mention game AI, which are basically very simple kinds of perception and planning algorithms that can be used to model the non-player characters in video games. The idea here is that these sorts of tools, which let a game designer create a new game and a rich, immersive, interactive experience relatively easily without having to program all that stuff from scratch, because it's like a basic built-in stuff about how objects interact with substances in the world and how agents might work and so on, that these might be some kind of first rough approximation to what is built in the common sense core, the kinds of things that infant researchers have uncovered and suggested are there very early in babies. So to put this, just to illustrate this a little bit more concretely, the idea isn't the way game engines are used, for example, in a lot of reinforcement learning systems where you train like an RL AI in a game engine environment, and then you're going to deploy it into the real world and you have a sim to real transfer problem. The game engine is the training grounds. Here, the game engine is what is the model of the model in the head, or the model of what the kid has in their head of the world. So that when this boy here looks at this stack of wooden blocks and the bird on there and says, well, I wonder what might happen if I roll the ball towards it, and then can imagine what is possibly likely to happen, namely hitting the blocks, they'll fall over in some ways, and then the thing on top will fall over. I'm sorry. That's the idea, right? It's a rich, compositionally structured mental simulation engine. So what we've done in work now going on for about 10 years with a number of colleagues is, for example, tried to use this set of tools to model intuitive physics, what we call the intuitive physics engine, which starts with a game-style physics engine. And the particular details aren't important, and the way we've implemented it are almost surely wrong in most of their specifics. right? We're not claiming that the details of today's game physics engines correspond precisely to the way the mind works, although there are some intriguing parallels, as Tomer Ullman has written about in this Trends in Cognitive Science paper that's called Mind Games. If you check out, it's one of the references on here. But to a first approximation, some of the kinds of representations and sort of physics engine hacks seem to have something to do with the way humans can intuitively, mentally simulate complex physical interactions. And then we wrap those dynamics models inside a probabilistic programming framework for inference and learning. And that enables us to model a wide range of intuitive physics judgments in, for example, classic kinds of blocks world scenes, where you might have a very traditional kind of question, like here's a stack of blocks like the ones shown on the left, and how likely is it that this stack of blocks is unstable or will fall over? So we can do an experiment where we might show people 50 or 60 different block towers varying in their subjective instability and have people rate on a scale of 1 to 7, or maybe just make a 2 alternative force choice judgment. But we can get some graded measure of their confidence that this tower of blocks is very stable or very unstable or somewhere in between. And the judgment there is what's shown on the vertical or y-axis of that inset plot, the scatter plot there, this one. Each point is a different stimulus. Along the x-axis is prediction of one of these probabilistic approximate physics engine models. So we basically approximately reconstruct the 3D scene using a kind of inverse rendering or inverse graphics computer vision algorithm. Okay? That gives you only an approximate location of the blocks in 3D. And then we run physics forward a few time steps. And again, it might only be an approximate physics. The forces might not be exactly right. But that's enough to get a rough idea of whether the blocks are going to move or fall and how many of them will fall. And then we just do that a few times, and that gives you a very rough, call it Monte Carlo, but just a very rough stochastic sample-based estimate of the amount of instability in the scene. That's what's plotted on the x-axis, and these two are very highly correlated. This is a pattern that we've seen across many judgments, not just the question of will the stack of blocks fall, but which way will they fall if they fall, or what will happen if, for example, the gray stuff is much heavier than the green, or for example, you might see a scene where you don't know which color is heavier, but the scene like these ones here is surprisingly stable. These towers look like they should be falling over, but you might be able to kind of work backwards and infer, well, if it's not moving, then I bet one of them might be much heavier than the other. That would explain why it's not moving. Okay. I'll just illustrate this with one other judgment, which some of you might have seen me talk about this before. So in that case, you've seen this. But if you haven't seen me talk about intuitive physics before, this should be a completely novel task. And I want to do this because it's really important to contrast very familiar judgments like, will the stack of blocks fall, or which thing is heavier, with a judgment that, until you've seen it, you've never had any relevant immediate training data. So it's another example of kind of out of the box, zero shot generalization. It's not that you haven't had relevant experience, okay? It's just that it's a very far form of generalization that seems to be required here. So here's the much more novel task, which is this one. What will happen if the table is bumped hard enough to knock some of the blocks onto the floor? Is it more likely to be red blocks or yellow blocks? So I've specified the task with an image and with a sentence in language. And somehow your understanding of language and physics should allow you to answer this. So I think we'd all agree in this case, it's more likely to be red blocks than yellow blocks. And maybe you'd say that because you see more red blocks than yellow blocks, but that's not enough. So consider other cases like this. If the table's bumped hard enough to knock some of the blocks onto the floor, is it more likely to be red blocks on the floor or yellow blocks? So here, there's more red blocks, but I think we'd all agree more likely to be yellow blocks, okay? How about here? Probably red here, probably yellow. Yellow, maybe red, yellow. Okay, this is a more fun demo to do interactively. Hopefully some of you were trying this yourself as I was going along. And you're more confident in some cases than others, but the key point is I just gave you about 10 scenes, and we could have kept on going for the entire rest of the talk. But the point is that in a very generative way, you can make these judgments, you can make them very quickly. And we think you're doing this using not some kind of simple symbolic reasoning like counting up things, but by doing something like a mental simulation in a very approximate and probabilistic way. So to illustrate, here's a reconstruction of one of these scenes in our game engine and a small bump that knocks the yellow ones over. Here's the same scene, but with a much harder bump. Okay, we can replay these and notice, again, they're different in all sorts of details. But that doesn't matter. At the grain of intuitive physics, the same thing happens. It also doesn't matter whether you run this simulation all the way to the end, right? After just a few time steps, like you can see here, that's enough to know what's going to happen, to know it's going to be mostly yellow at the grain of intuitive physics. So the suggestion is that running such a simulation, and it could also, by the way, be a very low precision simulation. You don't have to simulate the precise dynamics, and you don't even have to simulate all the blocks, but just perhaps an imperfect, imprecise, approximate simulation, just a few time steps with maybe one or a few different initial conditions is enough to estimate roughly what's going to happen in these cases. And that's exactly what we've done in this modeling result here, where again, on the y-axis are people's average judgments about this query, and on the x-axis are the average of a few simulations in this sort of a model. And again, you can see a pretty good correlation. It's not quite, but it's almost as good as the correlation that we had when we were modeling the question of you know, how likely is the block tower to fall over, or how stable is it? A much more familiar one. So I put these next to each other to say, look, humans can make these and innumerable other judgments just, you know, in blocks world, let alone outside of blocks world. And somehow we need a model which is able to capture that. Or if we want a model of common sense physics, it should be able to capture both the very familiar ones and the very unfamiliar ones. And in this case, the model is doing so without any learning at all. This model is completely built. It's built with the ingredients that I've talked about, a game style physics simulator and certain kinds of probabilistic inference capacities. Now, I'm not saying that you didn't do any learning to get to this point. Surely you did. But what I'm saying is it's not some kind of generic statistical learning. It's something more like model building. And we'll come back to that at the end of the talk. I don't have time to go into the details, but you know, we and colleagues have used the same kind of models to actually model infant quantitative expectations in intuitive physics settings. So infants can be shown scenes like these, where some objects of different shapes, colors are bouncing around inside a container. After a certain period of occlusion, one of the objects appears, and it might be more or less surprising depending on the dynamics of the scene, how many objects there are of different kinds, where they were at the point of occlusion. You can vary these different physical factors and quantitatively predict. Now on the y-axis, the infant measure of surprise, and along the x-axis is a probability. It's sort of inverse probability correlates with looking time. And it's the most classic way that infant intuitive physics has been assayed is violation of expectation. You look longer when something violates your probabilistic model, but here we were able to actually build a quantitative model based on one of these probabilistic physics models. I'll point to just one other intuitive physics phenomena that Toby Gerstenberg did when he was a postdoc in our lab. I should say here, I didn't mention the key people who did this study were Erno Teglos and Luca Bonatti. They were the experimentalists, and Ed Vool and I worked with them on the models. And I also didn't mention, I'm very sorry, the work before on the block modeling, that was primarily done by Pete Battaglia and Jess Hamrick, who are now both working on related things at DeepMind, where they're pursuing really interesting hybrids of neural and kind of symbolic probabilistic approaches there. So it's really interesting to see where they've gone with some of these same ideas. Now, Toby is a recent assistant professor at Stanford, but when he was in our lab a couple of years ago and continuing in some collaborative work, he studied effectively causal inference in a dynamic intuitive physics perception setting. And I point to this because I think it's so important. I mean, as many of us know here, that the semantics of verbs and many other interesting ways we express common sense knowledge and language depend on our ability to represent counterfactuals. Now, what Toby did was to try to realize these, study them perceptually. So he gave people these dynamic scenes, like think of this is like an overhead scene of a billiard table or an ice hockey table. And you see two objects moving and some interesting causal structure where in this case, there's like a hole or a goal, and the questions that you might be asked is, you know, did B go in the hole, or how did it go in the hole, or did A cause B to go in the hole? And in some cases, you can ask people to just make a descriptive judgment of the task, like did B go right through the middle, or did it miss completely, or did it just barely go in? And then you can also have them make a causal judgment. So did A cause B to go in the hole, or was A responsible for B going into the hole? And then, so Toby had people answer these questions, either prediction basically, or kind of causal explanation. At the same time, he used an eye tracker, and you're visualizing the results of just one trial from the eye tracker to see what people were doing with their eyes while they were looking at the scene in preparation for answering the question. And you can see a dramatic difference that in the case of just a descriptive query, people were looking at the scene and they don't always look at the objects. Here, watch the scene on the left, but they look at the objects, and then after the key causal event, they look predictively, where is it going, right? So they extrapolate where B is going. But crucially, in the causal case, they do these counterfactual simulations before A hits B, as well as after. Watch this again. Now watch here on the right. Before A hits B, look how the person is extrapolating where B was going. Now, the reason why that's important is because you only can say that A caused B to go in if B was already not going in, right? This is the but-for condition of causation, right? In a situation where B wasn't going to go in, and then A makes contact with it, and then it does go in, then you can say that A was responsible. And people intuitively understand that. We don't tell them to do this, but this is just what they spontaneously look at in order to assess the counterfactual situation. It's not clear, right? This is a borderline case. Is B going to make it? I don't know. I'm going to have to make a few predictions in order to see. And what we find is really dramatic differences in looking as a function of in the causal condition. You see these counterfactual looks. I won't go into the details on this because I want to make sure to leave a little bit of time for learning that isn't just about physics. I mean, again, as people here who study causal language or common sense in causal language, we know the different ways we might talk about these events. These are just a few possible descriptions. Each of these has, in some sense, embedded in it the kind of some interesting kind of counterfactual structure, which Toby and also his lab members in this recent CogSci 2020 paper, which I wasn't involved in, but it's really beautiful work, really tying this into language, has shown that you can capture these kinds of counterfactuals with basically probabilistic counterfactual simulations and use that to quantitatively model people's judgments in a whole bunch of different cases. I don't expect you to really understand what I'm saying. Think of this as an advertisement for Toby's cool work and the richness of what he can do by varying all these really subtle differences of the situations, including what did happen and what might happen. And he can capture people's judgments quite quantitatively with the kind of models that we're talking about. He's also extended this to kinds of causation where nothing's moving, but the counterfactual is whether something could move. So we might ask, did removing this block cause the tower to fall? Or is this block keeping the others from falling? Is this one supporting or preventing them from falling? So when you think about all these ways to use this kind of language, this is, we think, the common sense conceptual structure that supports that use of language. Again, it's not something that I really want to go into in much detail, but just I think because it is really the most interesting part of the common sense core and absolutely central for language is to go beyond the physics part to call it the intuitive psychology part. Here, the models that we're building are models of, or the models of what's inside people's heads are models of how intentional agents plan their actions, suitable for observing actions and then working backwards to understand what were the goals, the desires, the beliefs of the person in the scene so that you can understand and interact with them appropriately. Okay. So again, this picture on the right here, this is not a model of people's minds. It's a model of people's minds. Okay. And the idea is to have a causal model of how beliefs and desires, these folk psychological concepts, give rise to actions in the physical world through some kind of intuitive planning algorithm, such that then you can observe, say, the world state, the agent state in the world, and the actions the agent takes, and then infer backwards in a probabilistic sense to the beliefs and desires that are at work here. Okay. The most basic principle of how these models work is something that is summed up nicely in this Other Trends in Cognitive Science article by Julian Kahara Edinger and colleagues. It's called the naive utility calculus. And it's just the idea that, again, the basic ideas of expected utility theory that have underlied the way that we think about rational agents and building agents in AI, notions of cost and reward and maximizing expected utility, at least approximately as best we can in some kind of maybe boundedly optimal way, that these ideas we think are actually quite intuitive, that they are, as scientists and engineers have drawn them out, they are trying to elucidate what are effectively structures that are already in our heads, that there are intuitive notions of rewards for certain states, which we think of as goals, costs for action, and that we intuitively understand other agents as trying to maximize their rewards minus costs effectively. And in a number of studies, we've shown how to take these sort of efficiency-based planning models, basically things that we can build these on POMDPs, or partially observable Markov decision process planners, or we could build them on more sort of probabilistic version of classical planners like PDDL planners, and some recent work from Shen in our group. But regardless of how the planning system works, the idea is that an agent is trying to take efficient actions on balance to achieve their goals, and then you can work backwards, understanding that principle of efficiency to figure out what goal, as well as what set of beliefs, maybe true or false, would best explain what they did. So in this is one example of this kind of model in action from Chris Baker and Julian and colleagues, what we call the food truck studies, where you see an agent in this simple overhead map again, come out of their office. Let's say this is a hungry grad student who comes out of her office, and this is the office building here. On this part of campus, there are several parking spaces where food trucks come, back when people used to do that sort of thing. And here, the two parking spaces in this scenario are these two yellow squares. There are 3 different trucks which come to campus on different days: the Korean truck, the Lebanese truck, and the Mexican truck. And on different days, they're in different places, or you might see different parts of campus where there are different geometries, okay? On this particular day, in this part of campus, the Korean truck is here, and the Lebanese truck is over here, but our student can't see that. She can only see what's on this side of the wall. And now we observe her taking a certain sequences of actions. This is what we observe. She goes past the Korean truck, around the corner, where she can now see the other side. And at that point, she turns around and comes back to the Korean truck. So the question is, what is her favorite food? Korean, Lebanese, or Mexican? And if you think about it for a second, your first response might be Korean. If people mentioned system 1 and system 2 a bunch earlier today, your system 1 response might be Korean. But if you think about it for just a moment, most people decide it's Mexican, which is interesting, right? Because Mexican isn't even in the scene. But only that could really explain what she did, because otherwise it would be a kind of inefficient thing to do. All right. Not only that, you can infer that not only did she think, or did she prefer Mexican, but she must have had some belief that Mexican was possibly or even probably there. So people judge in this experiment both what she likes best, as well as what she thought was behind the wall. And her initial belief most likely was that Mexican was, more likely than not to be there. Otherwise, why go out of your way like that, right? So people make those judgments, and I think you can too. And our model captures that by doing this kind of inverse planning with, it's a POMDP, so with partial observability. We know the agent doesn't know what's on the other side, and they have to gather information, and that's part of the model. I'll just ask you one other question here, which is, what emotional experience do you think this person had when they got to their side and turned around? Probably you'd say something like disappointment, right? How do you judge from this little grid world that somebody is disappointed? Well, we could describe it in various ways, like saying, well, when people kind of go towards something that they think is there that they want, and then they see it's not there, they're disappointed, they went out of their way. But if we want a fully general model of emotional experience, such as disappointment or satisfaction, frustration, and so on. We think that, and it's in some other work that we've been working on with Rebecca Sachs and some of her students, we think you can build that kind of model of what emotion concepts are on top of the same things, okay? Something like disappointment being like, a sudden drop in the expected value of the agent, okay? I'm not saying that's what disappointment really is, but actually we can model people's subjective understanding of disappointment in scenarios like that. And these models, again, are quite quantitative. This isn't just one scenario, but we have very good correlations across a wide range of these scenarios, maybe even better than the intuitive physics situations. We can also extend these to more sort of realistic video type contexts. And I won't go into the details of these things, but by building on robotic action simulators, we can capture, and also by making these models multi-agent. So we can look at actions like this, which again, might be rather inefficient actions, but which we might be able to recognize as somebody reaching for something in an unusual way because of an obstacle, and somebody else trying to help them. And we want to know, what makes a scene like this look like helping, or a scene like this look like kind of the opposite, not helping, but something like hindering. So we take the same models, we ground them in a 3D model with physics and graphics for visibility. We recursively nest them in the sense that we say, well, what it is to be helping or hindering is to have a utility function that depends on your expectation of another agent's expected utility. So helping is to take another agent's utility as a positive contribution of your own. Hindering is to have a negative utility. These are the abstract concepts. Think like the golden rule in folk ethics. These are the abstract concepts that underlie what it is to help or to hinder, built on top of what it is to want something, right? Or to try for something, that we think can capture the conceptual structure of both intuitive psychology and more generally the kind of social cognition that we feel and talk about. So just to wrap up this main part of the talk, and then I'll just say a little bit about prospects for learning. If we want to know what do words mean, essentially, right? What are the common sense concepts that language is really about? What does it mean to cause or to help, to support or prevent, to make something happen, to almost do something, to be responsible for something, to launch or to catapult? This is other work that we've been doing where we use these physics models to capture these kind of tool use or object-based multi-object plans. To believe or want something, to be surprised or disappointed, to be helpful or cooperative. Of course, we don't really know what these words mean, but we think that by grounding them on these kinds of representations, it's going to be essential, and it's going to add something that just pure statistical models, whether it's language or language and vision, aren't going to get to on their own. Okay. This is mostly all I have time for. I mean, I'll spend a few minutes just, again, flashing through a few things that are mostly just advertisements for recent work that people in this community, some of you might know about this, others just might want to check this out. It's ways we've tried to use this to come back to the issues that I think this community most cares about. So for example, with some students, we've worked on what now is a quite popular domain of grounded language, visual question answering in richly simulated worlds like the Clever domain, where with a few colleagues like Keishin Yi, Judge Wu, Chuan Gan, and more recently Jiayan Mao, as well as senior authors like Antonio Torralba, Pushmeet Kohli, we've built various kinds of what we call neurosymbolic grounded language models, where we take what are very standard conventional neural computer vision models like mask RCNN type models for object detection, or this was done a couple of years ago. So our neural language model was stacked LSTMs, but you could do the same thing with transformers. But what we're doing is not building an end-to-end system. Rather, we're using the neural models to parse into symbolic conceptual representations of scenes and language meaning of the sort that we've been arguing are there in our core common sense understanding, and then sort of glue these together to answer questions or to do other grounded language tasks. The original work that we did on this from NeurIPS 2018, achieved really strong sample efficiency and generalization, but relied on basically building in all of this conceptual structure. More recently, I mentioned Jiayan Mao. He had, starting with a paper in ICLR 2019 and extending to with many of the same colleagues to a paper that was just accepted to be presented at ICLR 2021, what we call neurosymbolic concept learners, which take the same basic architecture, but in this case are using distributed vector space representations of meanings of the basic concepts, but in distinct visual and language context. So there's sort of like embeddings of red and green or square and round as visual concepts, as well as embeddings of the concepts behind language. And again, I won't go into the details, but I would say check out the neurosymbolic concept learner paper for how you can learn in effectively an end-to-end, only weekly supervised way, what are these visual and linguistic representations. Now, there's still a lot built in here, and I think that's really important. The basic kind of symbolic architecture of scene representation and semantics is built in, but the particular representations of specific concepts can be learned. Okay. It can also generalize in a powerful way, at least within to more complex scenes and sentences, and maybe even a little bit to real world images. And the most recent work that I mentioned, which builds on this cleverer data set from last year's ICLR, which just kind of extends the same idea to a dynamic setting with physical interactions. Here, now we're starting to be able to ground some of the more interesting aspects of language in counterfactual analyses of the physical dynamics. So we might take a question like in this scene here, what would happen if the cyan cylinder was not in the scene? So watch this again and ask, what would happen if the cyan cylinder were not there? We see what does happen, right? First, the red ball hits the cyan one, which hits the metal one, okay? But suppose the cyan cylinder weren't there. Well, we can parse that into a program-like representation. This is the neural symbolic part, that has as in it one of the basic functions of a counterfactual evaluation when you remove something from the scene. So here's now, we can now use our intuitive physics model to evaluate the counterfactual, to reconstruct the scene without the cyan cylinder. And what we see is that the red ball hits the silver metal cylinder. And so that allows us to say, okay, yes, the red rubber sphere would collide with the metal cylinder, basically. Okay, so again, this doesn't, I don't want to say this by any means solves any of the hard problems really in grounded language. It's more of like a proof of principle, or like a baseline that something like this could be built, right? That we can parse language into a conceptual representation that can evaluate a counterfactual on an intuitive physics mental simulation model. And in the most recent ICLR thing, increasingly parts of these concepts now are starting to be learned using that same kind of end-to-end learning approach. Okay, does that solve the problem? No, but I mean, again, I think I want to put this out there to motivate the community to think about this sort of approach. There are, like the other things I hope I've talked about here, we're really just raising more questions than I think we're answering. But questions like, how could you learn more of the actual like logical forms that are built into the system? Or how could you learn more of the physics engines? And here I'll just leave you and leave us with what I think is just the really hard problem of learning that this whole approach is trying to, I think, motivate. If effectively the real learning that we think happens is not, I mean, learning of common sense is whether it's learning the structure of language and the concepts behind language needed to do what I was just showing, or how you extend and grow your intuitive physics engine beyond whatever is built in. It's some kind of learning programs, right? The things that are learned are program structures, probabilistic programs, okay? Which means your learning algorithm is some kind of program learning program, all right? You could call that, if you're a neural net person, you might think of that as like architecture search, but again, to me as a probabilistic programming person, what I mean is you have to learn the structure of the probabilistic programs and really whole probabilistic programming languages which describe domains of common sense thought. And the problem of learning programs or even programming languages is not an easy problem. It's really the hard problem of learning, right? Because there's no, unlike learning in a neural network or some kind of other standard machine learning model, there's no nice error landscape with nice topology, let alone a nice geometry of smoothness that you can just do gradient descent on. The space of programs is a much harder problem to search. So what I think this leaves us on, which to me is like the big outstanding problem of learning that a lot of our work, and I think many others right now are excited about, is how do we think as learning as programming? Okay, that we called this recently in a review paper by Josh Rule and colleagues that the child is hacker, and by that we don't mean bad guys who break into your email and steal your credit card numbers, but the MIT sense of hackers, like creatively, playfully exploring spaces of code or other kinds of structure in the world, and building increasing structures in some kind of curiosity driven way. That's, I think, a way to combine other views of learning that are influential among developmental psychologists, like the child as scientist view or curiosity based exploratory learning, with the idea that fundamentally learning is building programs. And as far as how to actually build algorithms that build programs, well, here what we're trying to do is to draw insight from all the different ways that we as coders build programs, right? So what do we do on a day-to-day basis when we're trying to improve our code? Sometimes we keep the structure of the code fixed and we tune parameters to optimize its performance, right? That's what you're doing when you're doing gradient descent in a neural network. But most of the time you do something that involves changing the code, and then you have all these practices and techniques for making your code better, whether it's debugging, writing new functions, writing new libraries, refactoring, writing whole new languages, compiling, transpiling. Most of these are not algorithmized, though of course compilers, that's exactly what they try to do. But these are all practices that software is built from. So ultimately the goal of this part of the research program is to build algorithms which capture these kinds of processes. Now, again, we're just at the beginning of doing that. We're very far from being able to do that. I'll just point to one paper that was done together. This is the thesis work of Kevin Ellis with a number of collaborators, especially Armando Solar-Lezama, who's one of my programming language colleagues at MIT. And what we do in this paper that's called Dreamcoder is we combine sort of a neurosymbolic Bayesian learning approach with techniques from programming languages for refactoring code automatically to be able to learn in a kind of hierarchical Bayesian way languages for coding. So a system might, in this case, start off with like a set of tasks, which is like, can I build these block towers in Blocks World with interesting structures? Or can I draw these drawings, like these logo drawings? But I'll start with something very minimal, like just a logo programming language where I can put pen up and pen down, I can move forward and I can turn, right? And a little bit of recursion, basically. And can you build, for example, a language of graphics programming from those primitives by being able to basically write new primitives in your language, like new functions that you can reuse by name? And indeed, the system is able to do that. It's able to learn primitives and then combine them into yet new things like radial, take a basic polygon drawing thing, but then repeat it in some radially symmetric way. It's called Dream Coder because it uses a sort of wake-sleep algorithm where it builds the symbolic knowledge that I'm showing you, but it also trains a neural network by basically imagining random dreams from its body of knowledge that then provides training data for a neural network that can guide its search. And this is just an example of where I think the field of machine learning meets programming languages to yield program learning is just starting to be able to go. That ultimately is going to be what we need, or a key thing that we're going to need if we're going to deliver on this whole roadmap, to start with the core knowledge programs that are built in, but then be able to explain something about how we go beyond these, how we build that knowledge out, how we build the structures underlying language on top of that. So this is where I'll just leave you here. What I hope is that many of us will be able to increasingly follow what is the roadmap that developmental psychology has pointed out to AI, taking note both from the richness of how humans seem to start, as well as the learning algorithms, and trying to show something of the techniques that can be used to capture these in engineering terms. If that's something that you're excited to learn more about, I'd love to interact with you, talk more. I know I probably didn't leave much time for discussion, but I hope I've given some things to think about, and love to see where this community can go with this. Thanks.
Really great talk. And sadly, we're close to the end of time. So actually we're over time, but there are two themes in the questions. One is around the model, the a priori model. And is that related to DNA, RNA, et cetera? And how does this work scale for building intuitive physics, psychology, et cetera? But if you could answer quickly.
Sure. Yeah. I mean, when you say DNA and RNA, I mean, yeah, wow. So I think what you're asking is from a biological perspective, right? If we talk about concepts or representations being built in, how could that be? Well, in some sense, it's got to be built into the DNA, as well as like the machinery that reads the DNA. So the whole, structure of transcribing and developmental biology, which I only dimly understand. And I think we as a field or as a species only barely understand how is it that, a cell and a body is a machine that builds itself. So, I don't know. We don't know how, cortex comes out of DNA. We have some idea, but somehow it's going to be, yes, it's going to be structures that are built into cortex, both the circuits and the algorithms in neuroscience that are going to implement these things. And we don't really know how that works, but we have a lot of evidence in terms of what we can see in the behavior of not just humans, but many other animals that can be studied even in the minutes after birth, or even prenatally. By doing, for example, brain imaging while babies are still in the womb, right? That in a sense, the large scale architecture that we're talking about seems in some form, some proto form, to be built in. How that actually works is a challenge to be uncovered. Okay. What was the second question? The question of
how does it scale to build these?
Oh, how does it scale? Yeah.
Intuitive.
Well, yes, I've mostly focused because I mean, the one of the nice things about being both a cognitive scientist and an AI researcher is I can study certain small scale versions of the problem and not worry about how they scale, but study them with experimental precision and rigor using the methods of psychology, right? And to try to build these models for these small scale cases. But yeah, I mean, the short answer is yeah, that everybody wants to. I mean, on the engineering side, scale is critical, especially when we're talking about common sense and language understanding. And of course, that's been one of the main reasons why people have been very excited about neural network methods and so on. I would say the scaling thesis here rests on not just the idea of probabilistic programs, but probabilistic programming languages and these methods for building, basically automatically writing code, including languages. Like I didn't have time to go into it at the end. If you're interested in this Dream Coder work, there's an archive paper on it. And so I'll just type this into the chat. So check out the paper on archive with Kevin Ellis as the first author. But what you'll see there is, I mean, again, this isn't meant to be by any means a complete answer to scaling, but it shows how you can start off with a very simple language of effectively a simple kind of language of probabilistic programs, and then try to build that out iteratively, growing your language. On the pure engineering side, when I mentioned, I'll just put this also into the chat too, the GEN probabilistic programming language from MIT's probabilistic computing group. This is a language that has been built to scale in an engineering sense, in the sense of like you can build really large scale models of the sort I'm talking about and do scalable approximate probabilistic inference in them of the sort that should be suitable for like robotics applications or augmented reality, virtual reality. So, you know, these are in some sense different kinds of scaling theses. There's like, how do we build these things at scale? And then how do we have autonomous learning that can try to grow beyond what we initially write? And, you know, we're just at the beginning of seeing what that would look like. But those are some of the ideas that are out there that we are trying to work with, because, you know, you're exactly right. If that's the question you're asking, this may capture in some limited form or in some small scale form that we can study in the lab how people think, but to be able to turn into AI, you're going to need these kinds of tools.
Great. I'd love to ask more, but we're over time. I'll grab the Rocket chat and the other chat log and send it to you. And if you are here for our wrap up, I'm sure that people would follow up. Thanks very much.
What time is the wrap up? Remind me, Debbie.
The wrap up is at 14:55 Pacific time. Actually, it's probably going to 15 Pacific time.
I'll try to. Okay, cool. I'll try to join. I have to go do something else in my lab for a bit, but I'll try to come back for that. Awesome.
Okay,
thanks.
perfect. Thanks.
Yeah, thank you. Thanks everyone. Thanks, Philip. Thanks.
Thank you.
And with that, I'll yield to the next moderator.
Thanks, Deborah. That's me. So we come to the final paper session, part 3. We have 3 papers, 2 long papers, 1 short paper. So we'll start quickly. If the first presenters, Alessio, can start setting up and sharing the screen. His paper Zero Shot Object Interaction Recognition via affordance graphs. Well, we thank Alessio for his talk, and we
thank you very much.
So yeah, if you can please stop sharing. Yeah. Okay. So the next talk is given by Enrique. So if you can please share your screen. Exploring and analyzing machine common sense benchmarks. So Enrique, please go ahead.
All right, thank you, Pedro. Hello, everyone. My name is Enrique Santos, and I am a research scientist at Rensselaer Polytech Institute. And this work was developed under the DARPA Machine Common Sense program. Okay, so although there is no single agreed definition of common sense, most of them take into account that common sense is the shared human ability of understanding and judging everyday matters. So in machine common sense, we use tasks to benchmark AI implementations by challenging them in diversified aspects. So for example, a task might focus in social interactions, while another task may focus in numerical estimation. And even within the same task, we may find samples evaluating different common sense aspects, for instance, time and space. But one question is, what exactly are these common sense aspects and why they are relevant? Well, there is a lack of consensus of what this metadata should be, right? So currently, this metadata is limited and largely presented in an unstructured format or completely not present. And this metadata is relevant because the lack of it is preventing us as researchers in machine common sense of fully assessing both tasks and AI implementations with respect to their soundness in evaluating common sense. So that's why we believe this assessment can support answering questions from multiple stakeholders, as we see in this slide. So this specific work as a first step is supporting answering some of these questions or insights. And for that, we need, first thing is a common vocabulary for both data and metadata about the elements of this machine common sense ecosystem, and the modeling based on common sense dimensions for that. We want to focus on data that is publicly available, and that includes open benchmarks, open systems, and their training and testings against open question sets. And result of this would be the display in a unified dashboard with browsing capabilities as well. So under the DARPA MCS program, the common sense benchmarks are being categorized in terms of dimensions, and they include question type, topic, and reasoning type. And the table provide an overview of the first year's benchmark choices. And for now, we have been largely focusing in the benchmark related dimensions. We have been experimenting with some of these dimensions related to systems, most interpretability, but it's out of the scope of this talk. Okay, so we have surveyed a number of common sense benchmarks, and they are largely from the first year. And we have started collecting some definitions we could use for creating a common benchmark modeling. So I bet this is not new to many of you in the audience, but I want to expose these constructs to motivate our modeling. So as you can see, the tests are varied. They explore diverse aspects like social interactions or objectives. And based on the findings of this survey, we have modeled these results as an ontology, which we call the machine common sense benchmark ontology. We have extended the schema.org high-level terms to further describe benchmarks structures and their constructs. So for instance, you can see the modeling of questions, observations, hypotheses, solutions, and so forth. In addition to this, we have this part of the ontology that presents a number of terms that can be used to categorize the samples of each benchmark. So far, these categories are largely extracted from the Psychic benchmark because the Psychic had that categorization available as metadata. Okay, so we have used this ontology in an ETL pipeline to annotate multiple benchmarks with the available metadata. So we have a converter in the middle, which takes the data sets as inputs, and we generate an annotated JSON LD file, which gets fed into our MCS benchmark browser tool, which we develop under the scope of this work. So this is a brief preview of the tool. So we have shown here some of the benchmarks we have currently loaded in the system. We can go into one of them. We can see the parts of the benchmarks with some statistic, number of questions, and then you can dive into a specific data set, see the specific samples with the available associated metadata for each of them. So for next steps, we are incorporating open-ended benchmarks, which are benchmarks that are not multiple choice. We are also researching common sense principle or theories, including time, space, causality, and more, to support the refinement and deeper representation of common sense aspects. And the takeaways from this work is that benchmark metadata is crucial to allow the precise description of tests, but there is a lack of consensus of what this metadata should be, right? And we have seen from this workshop and the panels and the talks that this is a controversial topic, but are our efforts in machine common sense really encoding common sense, or are they just heavily based on linguistics, statistics that are correlated with a subset of the common sense aspects? How can we answer this question, right? So this work just scratches this bigger question. And we believe that surfacing this discussion of test metadata is a step towards this. So I finished this talk here with our vision, and that's it. Questions?
Thanks, Enrique. So we have time for a few questions. So I'll ask a question. So are you envisioning some way that, for instance, people who develop benchmarks could sort of easily submit, the benchmark so that it could be kind of incorporated into your library?
Yeah, one idea that we had before was to provide some sort of annotation tools to help in this process, together with an standardized formalization of the metadata. I'm not really sure if we are going to pursue this direction at this moment, but this was an idea that we had during the course of this work, yes.
Okay. We have time for one more question if somebody wants to ask one. Otherwise, we go to the last paper.
Just to add on to that, we would love to see people submitting benchmarks with some metadata about what the benchmark is good for and maybe what it's not good for, so people could figure out when to use it and how to use it. And we think part of the solution might be the community figuring out what kind of metadata is useful.
Okay, thanks, Deborah. Okay, so we move to the last talk of the workshop. It's going to be given by Kwabena Nauma. So can you share your screen? The title of the paper is A Context Mechanism for an Inference-Based Question Answering System. We can see your slides, but we cannot hear you.
Sorry, I think I was muted. I hope you can hear me now.
Yes.
Okay. All right, thanks. So in this talk, I would describe work on incorporating context into an inference-based question answering system. And this joint work with Alan Bundy at the School of Informatics and Yan Tao in Huawei. All right, so the motivation for our work is mostly focused on question answering and how we answer questions using data from the web. The challenge is that this is a very noisy and uncertain environment, and the critical bit that we see missing is the fact that most of the question answering benchmarks sort of evaluate only questions, answers are not necessarily based on individual user context. So it doesn't matter really where the user is at the time or any other information. You can basically answer these questions simply by looking at the questions and the data without any additional information. Now in the real world, question answering sort of is much more complicated than that, and the context of the user and the situation within which they find themselves are quite vital to getting correct answers. So a very simple example would be a question such as, what's the population of London? Now, if you have 3 different users in 3 different contexts, simply looking at time and location here, each of these contexts will result in a different answer. So in context A, the population of London would be, with respect to England, more likely, and for the year 2020. Whereas in context B, you would probably not be looking at the population of London at all, but the population of London in Ontario, which is the more likely answer that context B would require. And in context C is a completely different time, although we are looking at the population of London and England. So these three different contexts would result in very different answers. A hypothesis is that incorporating context in the reasoning process, involves or improves the quality of the answers that we tend to a user through sort of personalization of the answers. And a hybrid sort of reasoning process ensures that the assumptions that are made by the system, by adopting these different contexts, are transparent to the user. And our primary contribution here is the fact that we're able to incorporate these context mechanisms into an inference process. And in this particular work, we focus on the Frank question answering system, which looks more at inferring answers that cannot be found by traditional information retrieval methods, where you will have to sort of infer novel knowledge in order to answer the questions. So Frank basically stands for functional reasoning for acquiring novel knowledge. And we combine inductive and deductive reasoning approaches. So to answer a question would recursively decompose a query using inference rules, and then dynamically construct an inference graph for that specific query. Search through diverse knowledge sources, from general data knowledge graphs such as Wikidata and ConceptNet for common sense information, but then also domain-specific data such as the World Bank dataset for country development indicators, or music brains for information about music. And then once we're able to instantiate variables from these knowledge sources, we aggregate the information, recursively propagate them through the inference graph. So a question such as what will be the population of Europe in 2026 can be answered using some kind of regression on past populations of Europe, or looking at the predicted populations for countries within Europe, or some other non-trivial calculations. But then these are different kinds of inference methods that can be applied to solve it. So the key thing with this method of inferring answers is that we are combining deductive forms of reasoning using rules to decompose the problem into sub-goals, and then also applying inductive reasoning to make inferences from data using different kinds of ML algorithms. So a typical inference graph that's generated from the Frank system looks like that, where you can see the nodes representing specific inference points in the process, with the leaf nodes showing where data has been instantiated, and you can see the rectangular nodes showing the kinds of operations that have been applied. And this is, for instance, answering a question, what's the population of England? And on the right side, you can see what we call an A-list, which I'll talk about in the next slide. So key to the way we do inference in Frank is the use of a representation for each of these nodes, which we call association lists, so A-list for short, and they simply represent attribute value pairs. And they provide a flexible normal form that allows us to represent data from different knowledge sources, as well as the queries that we are trying to answer. And the idea here is to extend the concepts or the whole idea of triples, which you find in most knowledge graphs or in RDF representations. So the kinds of attributes that we would find in triples are the subject, predicate, object, but we extend these to capture additional attributes such as time, uncertainty, operations, as well as variables that we want to operate on. And one notation that I'm using in this talk is that of being able to identify specific attributes or distinguished attributes within an A-list. So omega will show that we are looking at this specific attribute omega within the A-list A. And finally, we can have variables as the values for attributes, with the exception of the predicate attributes, which we don't yet capture as, or can't have values which are variable. So an example would be for the A-list you see down here, which simply says the population of France in 2026, where that value is unknown, X, and the task of this process will be to instantiate the variable X to get our value. And the operation you are looking at here is value, which is to get the value of the population. Now, when we talk of context, we are looking at information about the user institution within which they submit the query. So it could be the device type they're using, whether it's a mobile phone or a computer, the location, the date, time, their preference for speed over accuracy. So there are a wide variety of things that a user might be interested in with respect to the question that have been submitted. And these are things that we want to keep in mind or incorporate into the inference process to make sure that the answers we are going to return are relevant to the user. So to do this, we add another attribute to the A list, which we call the context attribute. And it's basically a tuple, representing the user and institutional context respectively. An example will be the context attribute C here, which shows that the gender for this user is female, nationality is British, place is, the location is in the United Kingdom, device type is a phone, date time is 2020, April 30th. And we treat the context attribute just like we treat all the other attributes when we are performing inference, which is that we propagate them into the child nodes when we decompose them with different rules. That allows the context to sort of propagate through the inference graph. So we keep this information as we process each of the nodes. So how does context affect the inference process? Now, it first of all acts as a constraint on the question. That is, for a given question Q and a user's context C, the inference session is conditioned on the question that's applied, that's used in the inference session is conditioned on the question, meaning that, on the context, meaning that the answer we are going to get will be restricted to whatever the context is. And that's our objective here. Secondly, context gets to affect the inference process. So there are two key processes there, which is the decomposition and the aggregation or propagation step. So at each decision point in the inference tree or inference graph, we have to select different rules to apply. Given a specific context for an A list that is being decomposed, we condition the selection of that rule on the context of that A list, which means that if the user, for instance, is interested in, or if we realize that the user has a stronger preference for a specific kind of process, or has preference for, say, more accuracy over speed, we would choose rules that provide that level of accuracy compared to a more a different process which might give us a rapid answer but might have a lot more uncertainty. Similarly, the selection of the aggregation function that would aggregate sub nodes or sub goals to the parent goal would again be influenced by the context attribute for the list that is whose child nodes are being aggregated. So again, we can parameterize these operations by the context values. And then finally, at the leaf nodes of each of any inference graph is the step where we retrieve data from a given knowledge source or from diverse knowledge sources and try to combine them. And what we do in the front system is that we try to translate the A lists into native queries for those specific knowledge sources using wrappers around the APIs that they expose. Now, in order to incorporate context, what we do is that we add the relevant filters to the query. So if we are querying for the population of London, and we realize that the context of the user, say the UK or in England, then we would add additional filters to that query to constrain it to data from a specific domain. So here, what we do is we extend or we add additional filters to the native query to ensure that the context is reflected in the query that's presented to the knowledge sources. And finally, the whole idea of context in this particular application is one of, that is diffeasible in the sense that generally context adds latent information, which is not necessarily explicit in the query. So we introduce that information there if it's not there. However, if the user's query is explicit about specific data or about specific constraints, then those would take priority, or those would override the default that we would ordinarily have selected. So an example is the query was the population of London. If the current date and time, I mean, given that there's no temporal information in the query, we can default to the current year as the time. So this would become the query, this will be interpreted as was the population of London in 2021. However, the second query where the user's query is explicit about time, there's no need to use the default date and time. We would default to whatever is in the query itself. So to evaluate this, what we did was to look at classes of queries that we could test this with. Given the absence of any existing benchmark data set that we could use, we compared the kinds of results or the ability to query or answer these questions correctly, given the context that's given in the table above, with a version of the inference system with context and without the context information available. And we noticed that in most cases, without context, the queries are quite vague, and you're unable to get any reasonable answer in reasonable time. However, although we are able to get answers from almost all the query types that we tested here, and in most cases, the queries are sort of relevant to the user. So a question such as C20, where you're asking for the prime minister, simply by looking at the context information, we're able to restrict that the set of possible prime ministers to those that will be relevant to the user. However, when we look at C21 and C22, we end up getting the same answers for who is a mayor as Sadiq Khan, and who is a prime minister as Sadiq Khan. And obviously one of these has to be wrong, and C22 is the wrong one. However, this is an artifact of how knowledge is represented in Wikidata, the source for which, from which we got this fact. And that's because the granularity used to represent the whole concept of mayor and prime minister is not as finely tuned as, or it's not finely defined as we would expect for this query. So the same concept or the same predicate is used to represent the mayor and the prime minister, which is I think the head of government. So although we can separate these conceptually within the queries, the knowledge sources do not provide a fine level of granularity that we would need. But then we're able to apply these to different kinds of queries where we are doing qualitative queries, as well as quantitative ones where we require some kind of prediction. In this particular case, we're able to use the level of accuracy required to choose between different kinds of regression operations that are applied. So in this question in particular, what will be the population, what will be the GDP of Brazil in 2025? Without any kind of context, the graph you see in A here uses simple regression or linear regression. That's sort of the fastest that the system can do. However, once we incorporate context where the user is expecting a higher level of trust and higher level of accuracy, we default rather to Gaussian process regression, which offers sort of a more accurate answer compared to the noisier linear regression. And you can see that at the leaf node, again, we're able to combine data from multiple sources here. So in summary, we have focused on trying to get a mechanism that allows us to incorporate context into the inference process. For QA, we capture both user information as well as situational information in the context. And we also try to inject the context into the key steps involved in the inference process. The code for the inference system that we have applied here is found on GitHub. And we are looking at ways in which we can improve the preference elicitation from the user during inference by making it a lot more interactive. Then also, improving the personalization of the inference process by incorporating a lot more contextual information. And then also trying to get more extensive evaluation, with different kinds of usability testing. So I'm happy to discuss this with anyone who has interest in this area. Thank you very much.
Thank you. We have a question in the chat, in the Rocket chat. I'll read it. From Camtrack. How does the system perform with competing or non-deterministic contexts?
Yes, so at the moment, we will try to incorporate as much information into the inference process as we can. If it's competing, it's yeah, at the moment we wouldn't have any way of choosing between the context unless there is some additional information that allows one to override the other. However, what we don't expect to get the answer right always, right? The idea is that we try to expose, like I said, whatever decisions the system is taking in the inference graph. So you as a user have the ability to interrogate what the system has done by stepping through the different, inference decisions that have been made. And one of the things we are hoping to do is to identify some of these conflicting decision points. So if they are diverging, if a decision that has been taken will result in sort of a divergent graph where you have two separate inference processes that are happening that you can't merge. You want to be able to retain that in a separate way and sort of highlight it to the user that at this point, you couldn't merge information from these two sources. But then you can decide which of them you think will be a better one to use. A project that we have ongoing now is one where we build in the interactivity so that at that decision point, we can ask the users feedback that there are these two inputs that are coming in. Which one do you think would be better since they sort of conflict or we can sort of merge them? Yeah, but it's quite a challenging one to deal with.
Right. I'm just so even okay. So even if you're not dealing with, say, multiple contexts, even within your own context, like on, I think it was slide 13, you showed some data there, and I was noticing, let's see this, yeah, right here. Let's say you have a time. That time is not specified as PST or what time of day are we really talking about here? And so you could have multiple localization issues there, or with something like even London, right? That may be apparent which London you're referring to, but we know there are more than one London. So even in the context that you're in, how do you deal with ambiguity and vagueness within a single context?
Yeah, so you're actually right. There is the engineering difficulty, especially when we are dealing with very noisy data that we can't always anticipate, especially a formatting where they come, such as time. But then also things like ambiguity in the terms themselves. And I think one of the presenters mentioned earlier on when dealing with sources like ConceptNet, where the same term can have very different meanings in completely different contexts. And it's really hard to narrow or pick the exact one you want given your specific context. So yes, it's quite a challenging one. We have a student who is looking at the natural language aspect of it, where we try to do some kind of disambiguation of the terms using additional information that is present in the query. But we think the best approach to this is to do it during inference, where we can interrogate the user and ask for help, in the sense that you can't automate all of these things. At some point, you need to get that disambiguation performed during inference. Yeah.
Right. So do you have any kind of metric that lets us know what the uncertainty looks like, or what the vagueness, some measure of vagueness or uncertainty that's going to be given in the answer right up front, so that a confidence factor or something that the user will be presented with right away, because obviously this is not information that's presented at 100% certainty, right?
Exactly, yeah. So one of the key things in the inference framework we have is the ability to capture uncertainty. So we have this notion that for all the knowledge sources that we query for data, we set a prior uncertainty. It could be a very large uncertainty that we don't trust this knowledge source as much, and improve that uncertainty in a Bayesian way as we query for more information from the source. So one of the attributes in the A list is the uncertainty attribute, which captures for numeric data, for instance, the variance or the deviation that we expect from for that particular knowledge source. So it's some kind of error bar that we measure on that source, and we propagate that through the graph and give that as an uncertainty value to the user, saying that for this answer that we're giving you, this is how confident, or this how much we are confident in this value.
Okay.
Yeah.
Okay, thank you. So with this, we close this session, and hand it over back to Philip to sort of do the discussion and wrap up session. And thank you for the speakers.
Right, thank you, Pedro. So Kwabena, would you mind stop sharing? Okay. All right. So I would like to say one thing actually before we go towards the wrap up. So AAAI asks us that anyone who talks at the event either provides a photo release field form, or actually we have to edit that part out of the recording. So this even holds for people that ask questions. So I messaged two of you that have done this. So it's up to you. Like we have no intention to push anyone to do anything. But yeah, if you would like to be in the recording with the questions, we would need the release forms. Okay, so and with that, I would like to go now towards the wrap up part. So Alessandro will lead this part, and then we can go ahead. Actually, the idea is that each of us provides some of our views, and then we can open the floor for further discussion.
All right, thanks, Philip. Can you hear me well?
Yes. Yeah.
All right. Okay. So first of all, I think it's been very intense discussion today, from the presentations of the technical papers. Of course, the keynotes that we had, the very interesting panel. I wish we had 3 hours for the panel to ask many questions and have more interaction. But of course, it is the nature of these events that you live, and there are so many ideas, so many questions still floating in your mind. So I will try. So I'm not trying here to be exhaustive, but I will try to capture what, at least for me, was one of the leitmotifs, one of the core, I would say, underlying arguments of the workshop. So I want to start from, actually, I think it was a tweet, or maybe there was just a quote from an article by Oren Etzioni, where he was saying, common sense is the dark matter of AI. And so, of course, that applies to AI in different tasks of AI, like natural language understanding. And so, and I've been thinking about this tweet for quite some time. And, if common sense is the dark matter of AI, or natural language understanding in this case, what can these, statistical models that we have been talking about today, no matter how large they are, tell us about this non-visible matter if their only focus is surface properties of language? So they don't capture what is actually this underlying common sense dark matter. But actually today, I started thinking also on the other version of this question that, I always assume as not a problem, probably because I'm biased, because I come originally at least from, applied ontology, integration between ontologies and computational lexical resources and semantic approaches. So I think that is also true that if common sense is the dark matter of natural language understanding and AI in different downstream tasks, even knowledge representation, at least interpreted in a classical way, will tell us nothing about this dark matter, because we are focusing on the explicit aspects of knowledge, not in the implicit, tacit properties of common sense, because they are not manifested in ontologies, in these, let's say, common knowledge bases and graphs that we all know about. And so, I think that in this regard, the talk by the keynote by Joshua Tenenbaum was kind of important because actually it may be that cognitive inspired approaches are really at this point the key to unfold some of these underlying structures like causality that we can capture explicitly, but at the end of the day, capturing them explicitly doesn't explain how we can see them widespread in the tasks that we train our AI systems on. And I'm not only actually talking about focusing on learning in children, but in AI there is I would say a sub-discipline and a group of interest even in AAAI on cognitive architecture research. So the capability, so I would say the focus on trying to model cognitive aspects of human intelligence that can then be replicated at the machine level, both in terms of knowledge representation and in terms of learning. So I'm going to stop here, but I just wanted to to give you a little bit what I've been thinking about since the start of the workshop, and yeah, not with no intention to be exhaustive, but I think I hope at least is some food for thought and discussion.
Am I next?
Deborah, go next. Yes, please.
Okay. So this was great. Speakers were amazing. And one of the things that Josh said kind of crystallized something that was coming up through a lot of the workshop for me is something like our representations have to be up to the task. And so what does it mean? What is our representational structure of the future? Some people in the language model said words might be enough, especially if you get big enough. I, come from an ontological background, and I don't quite buy into that. And I think Josh posed that probabilistic programming at least might be a start. I'm not positive that humans generally do probabilistic reasoning. I think they do some kind of approximate reasoning. So I think many of us need to rethink what our knowledge is stored in and how we support intuitive reasoning, causal reasoning, probabilistic reasoning, or intuitive psychology. So kind of all these different kinds of reasoning, and how we do that at scale and in some kind of time appropriate manner. So I guess even though I've been in knowledge representation now for 4 decades, kind of longer than I want to admit, I think we have to kind of think about it again and think about some kind of fuzzy-ish, probabilistic-ish hybrid reasoning, and the representational structure is appropriate for that. So I'll leave it there.
Thanks, Deborah. I think we can continue counterclockwise in my screen at least with Pedro and then Philip.
Okay, thanks, Alessandro. I was struck by one of the the topics of the panel were, the idea that, the language models exhibit this of parrot-like behavior where they just say something that is what everybody says. And then, what Yejin said about basically, the sort of idea of common sense of trying to sort of justify what you said. And so, if we have a system that can give the right answer almost all the time, and then can justify it a few of the times, maybe we're not so bad off. And then we just need to learn how to justify, or how to make the system justify the answer. And that seems kind of unsatisfactory. That, maybe I can also parrot the justifications and kind of go one level deeper and still not have common sense, but appear to have common sense to even more people, because I can give the justification that everybody gives for that same answer. And so that sort of left me thinking something's kind of missing, and that, there's something about the justifications that is not just that it seems like a reasonable justification to most people, but in fact it's a correct justification. I don't know what the solution out of sort of regressing that, to more levels where, you can sort of parrot justifications, and maybe one can actually do that with language models and, build a system that sort of appears to have common sense. And maybe that's enough. This was a kind of a intriguing thing for me.
Yeah, so I believe you're primarily talking about Dave Ferrucci's starting,
Yeah.
right? So yeah, so I thought this was very interesting. I saw this quite a lot in Dave's way of talking about common sense and just the overall sort of machine intelligence. And I also saw these in a way quite a bit in Josh's keynote, the kind of the need to have, or this argument that we probably need to think about like deeper, more rich cognitive models that are sort of defeasible and sort of coherent with themselves, or basically they kind of stay faithful to what they say over time. So I thought this was one interesting observation about this sort of consistency of argumentation. I also found, to me, this also related to one of the parts of Yejin's presentation, where she talked about different moral judgments on the same situation being able to coexist. And it was very interesting, and I think this seems to me like the right way to go, is that there is rarely an absolute truth about something, but it's rather a sort of each, like the stance on a certain topic actually is supported, or actually is triggered by a rich viewpoint behind that. And I thought that her, I believe, 12 or so different stance attributes are quite an interesting pointer there. And this reminds me of, I think also there was something in this direction from, of course, Josh's presentation had a lot of these theory of mind, essentially, or basically mental models about mental models of people, where it's very often about things that are not even exactly there, but we somehow have implicit expectations about. And I think these are all aspects that we are only starting to understand. And it seems like it is not satisfactorily done yet with language models. Right. So I think those are some of the key takeaways that I had on this note.
Yeah. I mean, I had another takeaway that is kind of the influence of the, machine common sense community on the rest of the, say, semantic web, where, there's all very different ways to represent knowledge. I think the traditional, ontologies and knowledge graphs is kind of fine-tuning this of very symbolic and logic representation. And we're seeing from the common sense that basically all the big ontology that we need on top of the innumerable instances that we have maybe should be represented in a completely different way. And the idea that we should develop ontologies maybe should be looked at. Maybe we can adopt the common sense knowledge graphs, which are really very different beasts, and try to graft them on top of things like Wikidata. Basically say, replace the 2 million classes that exist in Wikidata with something that comes from this community, and use that to make sense of the gazillion instances that are there, instead of this very messy ontology that exists in Wikidata, and that seems fraught with all the problems that machine common sense is really starting to solve in a much more robust way.
And if I can add something to this comment by Pedro, earlier when I was mentioning cognitive approaches, I actually forgot to mention cognitive linguistics. So actually, I think in one of the last papers, I think by Alessio, there was a mention on affordances, so the representation of this type of conceptual knowledge. But let's talk about, for instance, conceptual schemas, Gestalt schemas, works by Talmy, by Fossonier, Langacker. There's pretty much no work on extending computational lexical resources, and I include here graphs and also lexical with this type of information. And I think, especially for common sense, being able to distinguish, being able to parse a sentence by looking at figure ground, causality, of course, and other type of schemas may reveal additional information that now is not captured by classical approaches. So I think now we can, I would say, freely interpret as the remaining minutes of this wrap up, also as a open mic to people still in the audience to comment, give us their feedback, related or not with the conclusions that we try to do so far. Yeah. So please.
I see 2 questions from the same person in the Rocket chat. Camtrack.
Yes, I'm actually seeing them as well. So let me see. So the first question is, how does the system perform with competing or non-deterministic contexts?
That's an old one.
We already asked this one.
Okay. Okay. Yeah, that is. So the computational epistemic justification. Okay, AG coordinate justification. So I don't see any other question here, at least on my.
Yeah. I think it was Pedro brought up the. He was a little concerned about the justification of the system, that it was a little spooky going on there. Was it Alessandro? Someone, I can't remember who it was that was, there was a little concern with that. And so I can't help but wonder, I'm on the epistemic logic side of things. And so we look at this this notion of justification all of the time, right? And can we build computational models of justification? So rather than just a system parroting some kind of justification, would it make sense for these knowledge graphs to be able to pull on some of the more classical epistemic justification models? For instance, coherence model is one of these things that we talk about in philosophy, and in computational philosophy, we talk about this. So rather than just, I guess beyond just simple systems that give explanation, I'm speaking specifically about the notion of epistemic justification, which is something a little more rigorous.
Okay. What anybody wants to comment on this? It's not super clear to me, how would you, so how do you distinguish in this context the justification, the epistemic justification from the explanation? Because of course, when we talk about explainable AI, we are considering these days a way to unfold what the AI algorithms have processed in a human understandable or readable format. So in the case of the epistemic justification, you would like also to unfold the underlying logical structure of the argumentation?
Well, yeah, because at the end of the day, unfolding it, however you choose to look at it, is going to, those things are going to boil down to assertions, and they're going to boil down to propositions in one form or another. If you want to boil down to some kind of rule, you want to boil down to some kind of proposition. However you choose to represent that final result, that thing has to be logically consistent, and it has to be supported by other notions in the same domain. The old school classical definition of justified true belief, we've heard of that thing. It's a very, very old kind of a concept. Well, if a system that gives me a bunch of propositions, however they're derived, whatever kind of learning methods are used, at the end of the day, those things have to be rational. They have to have an epistemic justification to them. It can't just be an explanation. Some explanations are not rational. And like you said, someone could have a stock, justification that's just parroted, that it might be meaningless or gobbledygook, at the end of the day. It's just some political or marketing statement that's thrown in there as justification. I'm talking about something a little more rigorous that ties together the coherence of the statement that's being made in the context of the domain a priori or posteriori knowledge, if I might use those terms.
Sure you can. And I think I'm not sure if this is linked to your question, your comment, but at the very, I think one of the questions, one of the points of discussion after the first keynote by Jinji Choi was, do we really need? So is it still relevant to talk about the logical structure of the knowledge that we inject? Isn't language enough? Isn't the way we formulate these rules or this declarative knowledge in linguistic forms enough? And so, I don't have I don't have an answer to this. I see why the debate these days is going to that direction, because of course of these amazing results that we see in language models. But even from the standpoint of thinking about removing, so if we remove the language out of the reasoning, is anything left? Because some people these days think that there's nothing left, so there's no logic that we really need to inject into the system.
Right, and most of the speakers, most of the speakers today made the point that those natural language models, they really do need some kind of external verification and validation. That they kind of struggle on their own. Maybe they are. It's necessary, but not necessarily sufficient. And so various speakers were struggling with what do we do to verify and validate some of those language models. And I'm suggesting that, before we throw the symbolic representations out totally and get rid of them, that maybe they have a useful form in the way of epistemic justification and being able to put some kind of constraint on the language models. And one of the speakers that was talking about the structures that are available, that are immediately available to infants. They were doing the examples with the blocks and the intuitive physics. Maybe the point that you just made, where if we subtract the language models out of that scenario, the structure that is left, and there is a structure that is left, is the thing that we're talking about. Someone has brought up the concept of dark matter in common sense, and maybe that's what it is. Maybe it's just that structure in and of itself that we're talking about. And it's reasonably possible to think that the epistemic justification stuff deals with that. And I know maybe that may not be everyone's cup of tea here, because we're not all doing computational philosophy, but maybe that's an area we could look at. Because the philosophers they've been talking about how you justify knowledge for centuries, right? And I guess the thing that we're looking at here is, are there computational methods that back up those models that we could then apply to the language, to the natural language models?
Thanks, Cameron. I think a
Yes.
very interesting points of discussion. So anybody else who wants to jump in here?
I'll jump in again. Just going back to the title of the workshop, common sense knowledge graphs, and trying to actually, I don't know if one could try to define common sense knowledge graphs, but common sense knowledge graphs and other knowledge graphs seem to look very different. And the common sense community calls knowledge graphs things where the nodes are text and the edges are labeled with a few relations, in the order of dozens. This is what we see in ConceptNet or Atomic and so on. The knowledge graphs in the other world of data have thousands of relations, and the nodes are concepts. And so these knowledge graphs are very, very different. And I wonder whether this idea that the relations are a few relations that are sort of labeled is also just a transitory thing, and we're going to go into some representation of knowledge where even the relations are not so labeled edges, but are linguistically labeled. And so they look more like OpenIE extractions than sort of RDF triples, as we develop systems that can understand the nuance of the relations. Because we seem to sort of have taken the point of view that the nuance of the concepts can only be captured using sentences or text. And that's why we replace no concepts by text. So it's sort of interesting to think that the knowledge graphs are really very different entities in the two different communities, and how this will evolve seems an interesting question to me.
Yeah, can you hear me?
Yes.
Yeah, so I would say, we went through this with ConceptNet a little bit. So I would say that, ConceptNet has a couple dozen relations, but there's nothing really special about them. There's nothing really special about the ones in Comet or these kinds of things. They're just intended to be a small set of relations that has pretty good coverage for inferences that you might want to make. And so absolutely in the future, we would like to go to much, much larger set of relations, and if you have a small set of relations, then you can kind of use redundancy between those small, between, you know, sticking a large number of concepts into a few relations. You can use that redundancy in inference. And that's what we did. You know, that's one thing that makes the inference in ConceptNet maybe better than it would have been otherwise. Also, I think there are different, you know, there are different ways in which common sense knowledge is used versus kind of factual knowledge. And in the beginning, you know, we just asked people to type in common sense statements like you sit in a chair or water is wet. And we just worked on that thing. And then we thought, oh, okay, more is better. So let's put in, you know, Wikipedia, and let's put in all these other sources and stuff. But that's really mixing two kinds of knowledge. You know, it's really mixing the factual knowledge, which in some sense, maybe we shouldn't have done that, because maybe it would be better to keep the pure common sense knowledge off to the side somehow, and then let all these other language models and database models do all the precise fact-based reasoning, and then, you know, use, and in common, I think the you know, logical reasoning, deductive reasoning is more suited for, you know, these knowledge bases like Wikipedia and more factual stuff. Whereas I think with common sense knowledge, really what you want is kind of reasoning by analogy, which is you know, somewhat different. So so that's how I would kind of you know, divide these things up. So I think there's logical reasoning, which is fine. We need all kinds of reasoning. We need probabilistic reasoning, which is not the same as logical reasoning. And then I think common sense reasoning is not the same as probabilistic reasoning either. You know, and so I think we need all of those three kinds of reasoning. So maybe that's where the important distinction is.
So one of the comments in the Rocket chat is about negation relations. And one of the things that Yejing brought up was contradictions and counterfactuals. Maybe we want to talk a little bit about where negation and actually Josh brought it up too, of also typicality. So like the jumping picture was like way too high, but you still recognized it as jumping, but probably not typical jumping. So where does that fit in?
Yeah, I think it's it has also to do with the old AI controversy about open and closed worlds. Because if you ask the question open world, if you ask the question closed world, you get different answers. So you have to decide which point of view you're taking. So and I think so I think that's kind of the thing, because negation, you know, you can make a certain argument with negation in a closed world that you can't in an open world.
Maybe just a little comment on the negation. Last year we published a paper with my team here on a workshop of empirical methods of NLP, and we were basically, you know, injecting knowledge from first ConceptNet and then CSKG on a specific neural network for Commonsense QA, and then we found out looking at the experiments, you know, that we were performing poorly, especially on questions that had negation. And why? For many reasons. But first of all, negation of what? Sometimes you have the negation of the full sentence, the negation of an event that hasn't happened. So categorizing the type of negation, it was one of the first problems. And the second problem is that, of course, again, as you know, as just been said, you know, open versus closed world. How do you possibly incorporate the knowledge of what is not true?
Yeah, so on a related note to the negations, I've been wondering also when Henry was saying that, you know, the set of relations that's in there now, you know, could be expanded further. And I think if you look at ConceptNet, there are a few relations that really point to this. Like, for example, has context, which is one of those catch-all relations that doesn't really tell you much. And for example, when we were looking into Wikidata, we found, you know, relations that correspond to has context, but kind of make it much more specific. Like, for example, the profession of something is one context, or, you know, the genre is another context. So my point of wonder here would be, you know, what are some families or what are some types of knowledge that we don't see in ConceptNet or in this common knowledge graph right now, that we would like to go for? And I guess negations is possibly one, which is somewhat captured in ConceptNet, to be fair, but I feel it's obviously not exhaustive. Then I assume affordances would be one item that we have that we don't capture at all actually right now. I would say, like so for example in CSKG we capture sometimes, we use the new property called may have property to say that, you know, for example, I don't know, a wall may have property white or gray or whatever. That would be sort of defining the domain of possible values. And so I think those are some, ideally something more about, well, I don't know. I guess those are some that we are missing. I'm wondering really what is the full. Oh yeah, I think another big missing piece is just defining the validity of the common sense a bit better, because right now we have mostly triples, but we don't really indicate a lot what is the context around them. So, you know, when are they valid and when are they not? And we actually tried to work on this for a little while, but I think our conclusion was that actually defining the context in a deterministic way is really difficult for common sense. So it always boiled down to sort of, well, it's most likely to be, you know, at this time of the day or this location, but you know, there are so many exceptions, and then there are exceptions of the exceptions. So defining the context of validity actually seems to be quite a big challenge. So I don't know, those are some things that I think we are missing in mostly all common sense knowledge graphs these days. I don't know if there are any others that come to mind that we should go out and look for.
I think in Niket Tandon's Webchild, I think he actually did, if I recall correctly, have a special knowledge base for exclusive OR relations. And so that was so he could, you know, do negative, you know, he could handle negation, you know, because you could make an inference with exclusive OR. In ConceptNet, there's about 4% negative statements the last time I looked.
I added typicality into the Rocket Chat thing because I think that's not at least broadly represented. And although some things have a notion of context, I think there's a wide variety of context, and rich context, I think, remains. But Ken Forbes brings up psych and microtheory. Ken, do you want to say something there?
Sure thing. So interestingly, a long time ago, OpenPsych was put out. They have 4 different versions out there that you can still download and use. We've been building on that. We use it every day. It has microtheories. It has a lot of higher order knowledge. It's got a really rich ontology, great microtheory structure, disjoint the statements, tons of those. So all these things you're talking about, it's already there. So, and by the way, we've made it available in a form that's also open license, Creative Commons attribution. So if you look on our website, or just Google NextKB at Northwestern, you'll find it. And we also got various programs of ours that will let you browse it and experiment with it, plus files you can load into whatever knowledge-based infrastructure you have. So, you know, why not put that to work? It also includes the work we've done on qualitative reasoning, including spatial reasoning, visual reasoning, a large-scale lexicon, and mappings to FrameNet. So all that stuff is, you know, freely available. So help yourselves and help us extend it.
And Ken, that's OpenPsych and your extensions, right? That's not the full psych?
No, because the full psych has a bunch of things that are proprietary to commercial customers and language materials that they view as kind of like crown jewels. Okay. Now, based on the version of Research Psych that we had, which is basically the same as Real Psych, our language coverage in NextKB is about as good as the Research Psych coverage in the last version we looked at. So our lexicon is already quite broad. And, you know, FrameNet has some problems. So for those of you who've used FrameNet, you may have noticed that they never actually talked about anything other than declarative sentences. None of their examples, none of their valence patterns have questions or commands. And they just never looked at that. If somebody paid them to do it, they'd love to do it. They were eager to do it. But no, that's not there. So you have to be very careful in using their valence patterns for reasoning.
I think one of the things that if I could offer as far as I thought it was missing from my observation of all of the presentations on these conceptual graphs, knowledge bases, I wanted to hear more of the mathematical foundations behind some of this stuff. Like, for instance, you guys are bringing up Open Psych and Psych, the mathematical foundations behind that kind of knowledge representation. I was really looking for more along those lines and more of the rigor that's associated with that kind of math. Is that just out of the bounds of something like this kind of conference?
Well, okay, so let me try that. So if you think about a large knowledge base, yes, you're going to have stuff that's radically inconsistent across microtheories. Right. So for instance, Research Psych has the Marvel Comics universe, the DC Comics universe, Lord of the Rings. And so if you have a version of the knowledge base that doesn't use microtheories properly, for instance, this actually happened to us. We were asking about a military problem, tactics problem, and suggested Frodo Baggins. This is not what you want. So you have to, the reasoning when you're doing it across microtheories makes life a little bit more complicated, and doing standard verification and validation at scales where you've got millions of facts, right, is rather daunting, right?
Right. Oh yeah. So I guess the notion of if we mean the same thing, I'm thinking of algebras, microalgebras. That's what I tend to call those things. And you have multi-domain algebras that you're dealing with, and you're having to validate and verify that. I understand the computational complexity involved in that, and I guess I want to hear how that's characterized. Just the subject matter. We seem to deal with it at the graph level, but not much of the mathematical foundations for the graphs that were involved.
Well, there's not in the ontology world more broadly, not common sense ontologies. Right. There are people whose life is merging ontologies and proving ontologies consistent.
Right.
They've done a lot of great work on that, but they've really tightened down the logical specification to make that tractable.
Right.
I think for most common sense reasoning, that's not really going to happen.
It's not going to happen. Fair enough.
I have a question. So actually I have a question that's on the opposite end of what Cameron asked. So have you guys applied NextKB for reasoning on downstream tasks? Like, have you,
what?
I don't know, have you tried to apply NextKB or OpenPsych on like a downstream reasoning task? Like, I don't know, question answering or whatever other.
Yeah, so in fact, we've done analogical QA training. It's used in a kiosk that's used to help people get around the computer science department. So it's kind of a daily use application. The analogical QA training basically gets you near state-of-the-art performance with basically much less examples, okay? And we get that in part because there's this nice ontology you can map to. The NextKB ontology is also used in our sketch understanding software, which is actually deployed and people are using it in classrooms. They draw their sketch. It gets compared by analogy to a teacher's sketch. And all those representations are automatically constructed by visual reasoning and produced into that ontology. So it is in daily use.
Right, but okay. I mean, that's great. Actually, I'm really happy to hear. I was marginally aware of NextKB. I was not fully, deeply aware. So how does it relate to tasks like the ones that we're discussing today? Let's say linguistic tasks, or visual tasks, or any tasks at the intersection of the two.
Visual tasks.
What does it require? What is required?
So visual tasks, we are state of the art in a bunch of visual problem-solving tasks. In fact, our Ravens model is better than most adult Americans at Ravens progressive matrices, right? So visual, we're in pretty good shape. If you think about what the contents, you look at Wikidata, what is that? That's a lot of ground facts. We've not bothered adding a bunch of ground facts because we'd like to slurp those from other sources. For instance, Wikidata and Atomic. So Atomic has a lot of interesting information that we'd like to distill in there. Okay, I finally got a student who's starting to work on that. The part that's missing that was not in OpenPsych that is in ResearchPsych is a lot of axioms for reasoning. So classic example, can planet Earth run a marathon, right? That's something that you don't know explicitly, but it's very easy to reason through. Planet Earth is inanimate. To be the thing that's doing running of a marathon, you have to be a living being. And so no, the planet Earth can't run a marathon. And it's those axioms that are both missing from OpenPsych. I miss them terribly. And there's one of the reasons why I came to this and to the tutorial was hoping that there'd be some nice resource out there where people have focused on gathering those things up. As to the best of my knowledge, there isn't one. And I think that's probably the biggest gap.
Just a little note. So from the wrap up, I think we are already in the happy hour, tentative happy hour. I don't know if you have a drink with you, but you may have. I still have water from today. And so also we downsized considerably to 23 people. So I believe that even though we don't have right now a formal conclusion, we can keep going with the discussion. I will personally have to jump out in 10 minutes, but yeah, feel free to continue to discuss. Just also feel free to drink something.
And also feel free to let us know if you would like to see some next steps. Sounds like Ken wants somebody to collect a bunch of resources.
I would have loved, now that I hear a lot about what Ken has been doing with OpenPsych, to have like a paper by Ken in this group on this workshop, maybe on the second
in the chat.
On the second version of this workshop, maybe next year or something.
Is Doug Lenot still around?
Oh yeah, definitely.
Okay.
He gave a great talk at the DARPA Machine Common Sense PI meeting. I don't know whether his talk is open to the public, but it was on lessons learned from building psych from 1984 to 2020.
Yeah.
And I have to say, it was really illuminating. And I don't think I've used psych for as many years as Ken has, but I've used psych for some number of years with benefits and challenges. And it was really interesting.
Yeah, I remember when psych was just a toy and just a thought. He was struggling to keep funding. Well, it was always well funded, but I just remember it when it was nowhere near as respected as it is today.
This is a good question. Somebody asked this question in the chat. Oh yeah, okay. So, Alessandro, are you going to set something up?
I think we can think about some form of continuing this discussion. I mean, over Slack maybe is one tool. I'm not sure if it is the only one, but definitely, I mean, if there is interest and momentum, we should keep discussing, because that's one of the goals workshops like this, right? Also, my small biographical note, my first conference ever was FOIS in 2001 in Maine, in Algonquin. And there, Doug Lennart actually had one talk, I think it was a keynote. And I first presented my paper on integrating on Dolce and WordNet. So, you know, back in the day, at least for back in my day. In fairness, if I can say something also about OpenPsych, I also, you know, I remember I evaluated research psych many years ago, and then I always had problems of finding, you know, publications that were up to date with respect to the stage of development. I understand that most of these is also due to the fact that there were a lot of you know, expansions of OpenPsych that were driven by industrial projects or government projects. But I think that is, in a sense, at least in my view, a little bit of a downside.
You know, part of the problem is that publishing content in computer science is not a thing you do very much, right? In biology, you say, well, here's an organism and here's how it works. If you say, here's a theory of a piece of common sense, it's not so exciting, right? Dan Weld once joked that we should start a new journal called Content. But it is very much against the grain, because in some sense that's just data, right? It's not process. We value algorithms more than we value representations.
I don't know. In some of the natural language processing environments that I've been in and out of, some things like lexicons and thesauri, ontologies, they're considered proprietary and competitive advantage. And in some senses, you know, organizations don't want to share a lot of that work that's been developed. And so things may be further along than you might imagine, but they're proprietary and they don't publish. You know?
Oh yeah, well that's the difference between research psych and OpenPsych, right? I mean, research psych has a lot of the proprietary stuff, but you have to have a license for it and you can't pass it out on the street corners.
Right.
So, you know, our sketch understanding software and other software gets passed out all over. We can't use research psych. We had to go to OpenPsych and start rebuilding from there.
Well, we ran into a similar situation with Watson, right?
Yeah.
Some of the knowledge, the ontology, some of the things that were I knew to be developed because I was involved and know people that were involved. Those things just weren't made available to the general public, and so you know, we don't. We can't benefit from developing a more general theory off of it because it's proprietary stuff.
So Prismatic, the knowledge base, even though it's built on top of an analysis of mostly open source stuff, there is some licensed material in there. Yeah. And so they don't dare distribute it. Microsoft, same thing. They had a natural language system that parsed the entirety of their online encyclopedia and Carta and did natural language question answering. Tried to get the knowledge base for that. Turns out it had a whole bunch of stuff from a proprietary dictionary in it. And so they were that close to releasing it, and then decided, nope, licensing will kill us.
Yeah. And so those are implementation things. And I can't help but, you know, it brings back my earlier question. There are mathematical foundations for a lot of this stuff. Even when it crosses domains and we're talking about different kinds of knowledge. And like you said, there's a lot of folks that have done work in model theory and category theory and those kinds of things. And that's kind of what I was hoping to see, whether we have gotten closer to something that's more widely known along those lines, you know, the foundations for that. And we didn't. So for whatever reason, maybe it was too terse for the kind of audience that we have. But at some point, someone has to document these more general theories, because I think that gets us closer to, you know, our keynote speaker for these sessions that just did that was an excellent talk. And that kind of reasoning gets us closer to the AGI problems that we're trying to get to ultimately in the field. But so much stuff is proprietary. They're really good stuff. You know, the deep stuff is proprietary. So what do you do?
Yeah.
Right. So yeah, thank you guys for the very fun discussion. So in parallel we'll be talking with Alessandro and Deborah, so we need to head.
Yeah.
But this was great, and thanks for all the pointers and all. And
thanks for hosting this.
Yes, yes.
Yeah, really fun.
Bravo to the organizers.
Thank you. Thank you.
Good workshop.
See you guys later at another one.